Now see, particle means it has, momentum, it has, some impulsive force. When it hits something, it can collide with things. I'm pretty sure you are made of particles. You can hit somebody, you can feel that something, all right? You have momentum when you move, correct? So you have particle-like behavior. Wave-like behavior will be things like, imagine when you create ripples on water, or when you talk, sound waves are going. That's a wave. Even light goes like a wave. You might have heard this. The light from the sun comes or reaches the earth in the form of electromagnetic waves. It travels in that empty space and the energy reaches the earth in the form of a wave. So the ripples on water is also a wave, where the medium stays as it is. Only the energy goes from the source to the destination. In particle, they can interact with other matter, they have momentum and they can collide. All these things happen in particle behavior. Correct? Yes, the Telegram link is there in the description box. So yes, wave behavior, they can interfere. Waves can interfere. You might have heard, like when two people are talking, both their sounds are heard. And in a noisy class, teacher would be always saying, hey, stop talking, stop making noise, etc., etc. Everybody is making noise. All their waves interfere. So even light waves can interfere with each other. They can produce constructive interference. That means their crests meet together to produce bigger crests. Or destructive interference. That means crest meets with trough to cancel out each other. Correct? Okay. Now what happens is, guys, that when waves can interfere, they can also undergo many other such phenomena. You might have heard about words like diffraction, refraction, right? How many of you have heard this? Yes, is this enough for NEET? Definitely, bacha. Concentrate on the class, guys. Concentrate on the class. Yes. Yep. Yes, Lonji, what is your comment? You can ask me later on also, but right now I would want you to concentrate on the class as well. Yes, you would have heard all these phenomena. So these are associated, these are the traits, these are the symptoms of waves. Just like when you treat a patient, you will ask symptoms. Oh, you have fever, okay, you have cold, you have temperature, that means you have this. Okay, you have this, you have that, that means you have this. So if something is diagnosed with waves, it will have characteristics like interference, refraction, etc. If something has particle-like behavior, it will have momentum, it will interact, it will collide, and all such other things. I hope this is clear. Now it has been found that light can undergo and show both kinds of properties in different experimental setups. Light can interfere, so yes, wave. Light can also provide momentum, so particle. So light has dual nature. What does light have? Dual personality, so dual nature. In some experiments, it shows this. In some experiments, it shows other type of behavior. Hence, it is said to have dual nature. I'm hoping you understood it till here. Great. So let's see if you can arrange these characteristics into different parts. Which of the following are particle characteristics? Which of the following are wave characteristics? Just look at these terms, and from your prior knowledge or just by common sense, try to rearrange them. Yes, come on. MTG fingertips plus PYQ enough for 150. Warren squares, please watch my previous session, the strategy one. There I have mentioned which books and the strategy to be used for 150 plus. So just those books will not help you, let me tell you that. Okay, so Sandhya saying CEF and Prem saying ACE saying particle. Okay, momentum is wave. Really? Food news? Think again. Okay, wave is BDF saying Gokul. Jai Shakti saying AC is particle, BDF is wave. Interesting. Many people sticking to some similar kinds of answers. Come on, lock your answers, guys. Be true to yourself. Can we score 100 plus if we start from now scratch? Yes, you won. That is the whole aim. That's why I conducted the strategy session, gave you a plan. I told you how you can get 150 plus with proper timetable, with proper technique. Now you have to attend these classes, only these classes and the strategy that I have given. If you follow that, you will get 150 plus in physics. That means 600 plus in NEET examination. Alright, so let's have a look at whether you guys are correct or whether you guys are wrong. The correct answer to this question is wave parameters will be diffraction. Diffraction is a parameter or a characteristic of a wave. Diffraction is basically a property. Those of you who do not know it, don't worry about it. Diffraction is basically nothing but bending of light. Bending of a wave. Bending of a wave around a corner. The light spreads, it bends. That is called as diffraction. It can only happen with waves. Interference, constructive, destructive, only with waves. Refraction, again, this is also bending of light, but not because of corners or anything, but when the medium changes. This is bending of wave around corners, or basically holes or apertures. This is basically bending when the medium changes. This is when the medium changes. That's when refraction occurs. Whereas momentum, obviously, momentum is mass into velocity. Mass is particle behavior. Impulse will happen only when impulse, remember guys, impulse is change in the momentum. Change in the momentum, obviously with particle. Collision, particles collide. They do not interfere. Particles will collide and momentum is conserved. So all these are particle behaviors. Very good. Good evening, Sanaji. Good evening, everyone. Very good. Excellent. So ACE is particle. BDF, many of you said this. BDF is wave. So BDF is wave. ACE is nothing but your particle. So that's how it works. All right. Great. Now that you know what is the clear distinction between wave and particle, proud of you guys. Keep it up. And looks like some of you have already lit the chat box because you are feeling great about getting the correct answer. Very good. Keep this up. Now, the next thing is, what is the particle of light called? What is the particle of light called? The wave of light is called electromagnetic wave. There is a separate chapter in 12th standard. Have you heard of it? Light wave is electromagnetic. The particle of light is called photon. Again, I'll repeat. What is the particle of light called? Photon. The wave of light is an electromagnetic wave. Very good. You guys know the name. So, what is a photon? If I talk about it, light, you know, the wave nature of it is electromagnetic wave. The particle nature is nothing but called as a photon. Now, what is this photon? Has anybody seen a photon? The answer to that is no. Is photon a sphere? No. Nobody knows how a photon looks like, but I can sense a photon when it falls on the retina of my eye. Your eyes can sense photons. When it falls, you are able to see everything around you. Correct? Now, this photon is a carrier of energy. Every day you might be getting milk packets at home. Correct? So there is a milkman who comes and gives, okay, this is a packet of milk. Okay, there is a packet of milk. Okay, here is next packet of milk. Every day you get it. Correct, guys? All right? Correct? But it's not like, you know, there is a stream or there is a canal of milk and that milk is slowly entering into your house. Okay, let me just open the tap and let me just take the milk. No, it's not like that, right? You get packets of milk exactly like that. Exactly the same way, energy of light also travels in packets. Energy of light also travels in packets. Very good, Lone. Packets of energy. Correct. So, every photon has a fixed energy. It has a fixed amount of energy, and energy of light does not travel continuously like a flowing river. Like a river which is flowing, water is flowing continuously, whereas you pack it into bottles or pouches, then it is a packet of water or a pouch of water or a bottle of water. So energy of light goes in packets. Very good. Very good. Now, the next point that you should know is that these packets of energy differ in size. Some packets are small, some packets are large. Some packets are small, some packets are large. Can you guys tell me what would the size of the energy packet depend on? Come on, let's see how many of you can do this. Come on. Tell me this, guys. Shiva, this is NEET English channel, bacha. Alright. The difference between proton and photon. Very good, Prem Kumar. Proton is in the nucleus. It's a particle. Correct? It's also a particle. It's in the center of the nucleus. It has mass. It can be seen. It is like a decently sized particle inside the nucleus. And it has positive charge. Photon does not have charge. Photon does not have charge. You cannot, see that photon so easily. At least, there are no experiments as of now to see that photon. I hope this is clear. So photon is chargeless, mass is also not there, but proton has a mass, it has a charge, it is in the nucleus, it's quite considerable in size. Yes, it depends on frequency. Very good, Madhumita, very good, Tejashwini, who all have told that. Prem Kumar, yes, not quanta, but it has a fixed amount of frequency. Yes, definitely. So each photon, which is a packet of energy, the energy packet's size depends on the frequency. Big frequency, big energy packet. Small frequency, small packet of energy. Big packet, big frequency. Small packet, small frequency. That's what it is. Also, with what speed does this packet travel? With what speed do these packets of energy travel? Obviously, it's light. It will travel at the speed of light only. And how fast is light? 3 lakh kilometers per second, which is 3 into 10 to the power 8 meters per second. That's the speed of light. So these energy packets travel really, really fast at 3 lakh kilometers per second, and it is independent of the frame, meaning whether you sit on Earth or whether you sit on the boiling sun or whether you sit on Jupiter or you are in a lift, you always see these packets traveling at the same speed. Very good. They travel at the same speed. Satya Prakash, you can read the Satya Ritika, you can see the title. This is basically modern physics, chapter 1, your wave particle duality, photons, photoelectric effect. Very nice. Independent of the medium? No, it depends on the medium. It depends on the medium. So if you change the medium, obviously the speed of light will change. It depends on the refractive index. So speed of light in any medium will be speed of light in vacuum upon mu. What is this mu called, my dear warriors? What is this mu called, my dear warriors? It's called as the refractive index. It is called as the refractive index. Correcto? Amazingo? Let's go ahead then. The energy of a photon. Now photon is nothing but your energy packet. It's nothing but your energy packet. This packet of energy is also called as the quanta of energy. Like when you have some money in the wallet, each coin or each note is a quanta of money. This quantity, the smallest number of that quantity is the quanta of energy. So this energy packet is also called as the quanta of energy or the packet of energy. That packet or that quanta or that minimum value of that energy which is there with each and every photon or each and every packet is given by energy of a photon is given by nothing but h into f. You can see very clearly, if the frequency increases, energy increases. If frequency decreases, energy decreases. Correct? Great. This h is nothing but called as your Planck's constant. This is called as your Planck's constant. The value of that is approximately 6.6 into 10 to the power minus 34 in SI units. That's MKS units, right? Very good. But we all know that speed of light is also related to the wavelength and frequency. How? Observe. Guys, I hope you know speed of light is also frequency into wavelength. Frequency into wavelength. This is basically one wavelength. This is basically one wavelength from here to here is a wave. This is a wavelength. Speed of light is frequency into wavelength. Everybody agrees with this? So can I say frequency is c by lambda? Frequency is c by lambda. So can I not say this is also equal to c by lambda into h? So hc by lambda. This becomes your complete formula. So let me just block this off. Energy of a photon is h into frequency, which is Planck's constant into frequency, or Planck's constant into speed of light divided by wavelength of the light. Now, If I ask you to calculate, now you will be like, sir, it is so boring to calculate. H 6.626 into 10 to the power minus 34. Speed of light 3 into 10 to the power 8. Wavelength in some other unit. It's difficult, no? I think there is an easy way to calculate it, and you can use this calculation shortcut for avoiding complicated calculations. What is that calculation trick? Here is the trick, guys. The energy of the photon usually is very small and is not generally expressed in joules. Instead, you use a smaller unit called as electron volt. And when you use that unit, instead, all these terms, constants is already calculated for you. You just remember this number 1240. 1240. And then here you put a lambda. This lambda, if it is in nanometers, then the answer for this energy will be in electron volt. If you do not have lambda in nanometers, but you have lambda in Armstrongs, then you put 12400 and then it is electron volt. Either this or this. If this is in Armstrong, 1 extra 0. If it is in nanometer, then no extra 0 apart from that. Exactly, Lone. Exactly, everyone. Very good. So this is a shortcut trick. Most of the times in NEET exam or any other exam, you will see lambda will get cancelled with 124. So most of the times you will see it will be like a multiple or divisible with this 124. So you will see some easy calculations many times. So this is a small trick which you should know. Great. So now we have learned about quanta, the energy, speed of light, how is it related to wavelength, and what is the formula of energies of a photon. Great. Moving ahead to some more properties of a photon. Somebody was just asking me. Somebody was yes, the value of HC in electron volt, Kausika, is 1240, not H into C. H into C's value is not 1240. HC is in joules, converted into electron volt, then it is 1240. Okay? Yes, Siva Kumar, but I'm not taking a big chapter so that everything looks confusing. I'm taking small parts of big unit like modern physics. So I'm teaching a part of modern physics today, which is wave particle duality. You can see the title, I mean. Okay? Great. Now the next point is, somebody was asking what is the difference between proton and photon. So guys, quickly you should be able to tell me that photon, does it have positive charge, negative charge, or is it neutral? Does it have positive charge, negative charge, or is it neutral? Come on, put it up in the chat box, spam the chat box, guys. Is photon, not proton, photon. Spelling is very similar. R is there in proton, that's it. So photon is neutral, positive or negative? Obviously it is neutral. Then you will be like, sir, what is the difference between neutron and photon? What is the difference between neutron and photon? Neutron is also chargeless. Photon is also chargeless. Then what's the difference? What's the no mass, no charge. Very good, Ashika. See? Very good. Conversion between joules and electron volt. Yes, I'll come to it. 1 second, Prem Kumar. Let me just finish the slide and then remind me. Okay. So, guys, neutron has a decent amount of mass compared to the atomic scale. But photon is massless. There is no mass associated with it. So that's why you will see that the rest mass of the photon is assumed to be 0. Very, very crucial. The rest mass is assumed to be 0 for a photon. Photons are neutral. Very, very important. And they are stable. It's not like a photon will break, it will explode, it will create some crazy amount of explosion. No. And because it is chargeless, because it is massless, hence it will not even get deflected even if you apply electric field or magnetic field. Only charges get affected by electric or magnetic field. No mass, no charge. And it is stable. I hope this is clear. Very good. Somebody was asking, sir, what is the conversion factor from electron volt to, joules? So, my dear students, if you want to convert electron volt into joules, this is the conversion factor. 1 electron volt is basically nothing but 1 electron's charge. What is the charge of an electron? 1.6. 1.6 into 10 to the power minus 19, right? So instead of E, just put the value of E. That's it. That is in joules. So this is usually the conversion factor that you're going to stick to. I hope this is clear. So 1 electron volt is these many joules. So 1 joule will be, take the number on the other side, that many electron volts. I hope that is fine, Prem Kumar. Great. Great. Now, is rest mass and normal mass same? No. Rest mass and normal mass is completely different. Now, understand, a normal mass might be the mass when it is in motion. Rest mass is when it is actually at rest relative to you. So, a normal mass when something is moving will be slightly different. Now, why is it different? That comes in a separate class, or you can say separate branch altogether. That is relative mechanics, which was given by Einstein. Let's not go there. Okay, you have to stick to NEET level. Correct? So guys, just understand that the mass also can change if speed changes. That's a crazy different theory given by relativity, Einstein's theory. You can definitely read upon that when you are done with the NEET exam. Now I know you will be very fascinated. You will be like, sir, teach about black holes, sir, teach about relativity. Yes, it's not even there in the syllabus, sir, but it is fun. Yes, it is fun. But do you have time? You please tell me that. So focus on the syllabus. Okay, momentum of the photon is given by. Momentum of the photon is given by. Now, any particle will have momentum. Remember that? That's one of the characteristics, a trait of a particle. So, photon being a particle of light, it should also have momentum. Then you will think, can I write the momentum of a photon? Can I write the momentum of a photon as mass into velocity? Yes or no? Just put it in the chat box. Do you have to write notes? Ajit Gaming, very good question, bacha. If you want, you can make running notes, but don't copy everything because I'm going to give this to you on Telegram channel. So don't worry. All my handwritten print will also come in the Telegram. Some of you are saying yes, Sara saying no, Sandhya saying no, Kanan saying no mass, very good. Prem also saying no mass, very good. The answer is no, bacha log. You cannot use this. Where is the mass? Mass is 0. How can you use this? You will get momentum as 0. That is the crazy thing. Then experiments were done and it was actually found that the momentum of a photon is given by h by the wavelength. The wavelength of the light is denominator, h is Planck's constant, that gives you the momentum of the photon. Very crucial formula. Now if you want, you can also rearrange this a little bit, like multiply it with speed of light, and because you have multiplied, divide it also with speed of light. CC cancels and you will get the same thing. Wait a minute, what is hc by lambda? What is hc by lambda? I just gave it to you. hc by lambda is energy of the photon, so hence it will be nothing but energy of that particular photon, by c. This is also another way of writing the momentum of the photon. I hope this is clear. Ajit, I think I just answered it, bacha. Just rewind back. I have answered it. Okay, Telegram channel name is there in the description box. In case it is not there, after the lecture, I will add it. Okay, I'll just ask the team to add it in case it is not there, but it should be there. Okay. Everybody fine with this? Great. Let's do some questions based on whatever you have studied. Particle-like behavior of light arises from the fact that each quanta of light has some definite dash and a fixed value of dash, just like a particle. Here, x and y refer to the particle of light, meaning photon, arises from the fact that each quanta, that is each packet, has some fixed dash and definite dash. What are those blanks? Come on, my warriors. Yes, Kansita. Momentum is basically h by lambda, and I have just written down the derivation. You can even rewind a little bit. Even in a live class, you can go back a little bit and replay the same part, even at 1x, 2x, 3x speed. Okay, I think those options will be there. Okay, some of you are saying D. Many of you rather are saying D. Very few are saying C option. Okay, very good, Minimoy. Glad it is there in the description box. Please join the Telegram channel to get the notes. The correct answer is energy and momentum. It's not energy, frequency, angular momentum, energy, shape, volume. No. It is not frequency. It is energy and momentum. Every packet has a fixed momentum and fixed energy. Every packet has a fixed momentum and fixed energy. From that, they understood, oh, these energies and these momentum depends on the wavelength, and these wavelengths depend on the frequency. Yeah, the frequency is the same, agree. But they first understood that each packet has a fixed energy and a fixed momentum. That's what led them to believe that, oh, it has particle-like behavior. Because frequency, although it is the same for a packet, frequency is not a particle characteristic. Frequency is a wave characteristic. So a lot of people think it is C because for a packet, frequency is also fixed. But remember, if frequency is not a particle behavior. Frequency is not a particle behavior. Hence, option C will not be correct. D will be correct. Yes, frequency is for wave. Very good, Gokul. If the wavelength of photon is doubled, then the energy and the momentum will be both halved, both doubled. This is halved, that is doubled, that is doubled, this is halved. Come on, figure this out. I hope Reena, this is clear. Why it is not frequency? Prem Kumar, I hope you understood. Very good questions you guys are asking. I'm very proud of you guys. Perfect. If you guys are asking why it is not Sina, that means you are thinking, sir, frequency also was same, then why is it not true? So now you understood. Frequency is a wave characteristic, not a particle characteristic. Very good, guys. Keep it up. Can we say that for a packet of photon, momentum and energy are constant? Yes, exactly, Harish. Exactly. It has a definite and a fixed energy and momentum. Exactly. Yes, Harish. Okay. So guys, let's see how many of you can... Yes, if you just watch my lecture alone for these topics, that is more than sufficient, Siva. I'll be doing problem solving sessions separately. That will be more than sufficient. Okay, both double. Most of you are saying both double. Some of you are saying doubled and half. The correct answer is both halved, guys. Oh my God, what just happened? What just happened? Let us have a look. Guys, the energy and the momentum. So let's talk about energy. Energy formula is hc by lambda. If you talk about momentum, momentum is h by lambda, correct? Now it is clearly mentioned the wavelength is doubled. Read the question carefully. The photon's wavelength is doubled. If the wavelength is doubled, lambda will become 2 times. So this ratio, this whole thing, how many times will it become? Half times, na? Momentum will become half times. If lambda is in the denominator, it becomes double, then this ratio or LHS will become half time. If this was on the top, then this would also become 2 times. Here also, if this becomes 2 times, obviously this becomes half times because wavelength is in the denominator. Inversely proportional. Understood? Everybody made a mistake. Tell me, is it a difficult question? Honestly tell me. Honestly tell me. No, right? It was not difficult. These kind of questions will come in NEET exam. Yes. And you might lose marks. So that's why you should attend these classes. I don't want you to lose marks. Very direct questions will come. And yesterday I have given you the ratio of easy, medium and hard questions. This will come in that 30%, 40% category of easy questions. Okay? Great. Let's move on to the next one. Now radiation pressure and radiation forces for different materials. Radiation. What is the meaning of radiation, guys? Yes, very good. Yes, very good, Siva. You remember those percentages. That means you have paid attention to the strategy. Very good. It's very important that you know the strategies. Radiation is basically light or basically electromagnetic waves or electromagnetic waves. When light falls on you, do you feel force? Like, oh my God, it's like water falling on your face. Like when you stand under a waterfall, doesn't the water hit you? Haven't you got hit by water when you stand inside a waterfall or just a shower? The water hits your face. Or you might have seen dentists using a jet spray. Using the jet spray to clear your or clean your teeth. Have you seen that? So, there water applies some force. It has some pressure. Does light also apply some pressure? The answer is yes, but you don't feel it. Reason, because it is very, 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 very small. You generally experience forces around you in newtons, kilonewtons, meganewtons, or even point newtons, but not in nanonewtons, micronewtons, piconewtons. Those are so small forces that you hardly will feel that pressure. So hence, understand, you generally do not feel the pressure of light, but it is there. At atomic level, if you talk about the small atoms, bechara, those people na, they will get lot of pressure. For you, it doesn't matter, you're huge. It's like you are an elephant and you're throwing water on an elephant. Nothing will happen to that elephant. But if you take a bichara small ant and you throw water on it, it will be like floods for him or tsunami for that ant. So for the atoms, that pressure also matters. I hope this is clear. So there is pressure, or there is basically force on atomic level which you can experience. Now why is this force or why is this pressure there? Simple fact. If imagine this was a photon. Does a photon have momentum? Does a photon have momentum? Yes, it does have momentum. Now let us say there is some kind of a surface. There is some kind of a surface over here. That surface can absorb it or it can reflect it. There are two things that can happen. Whenever light falls, it can get absorbed, like you are wearing black clothing, like this blackboard is black, right? So you can see the light will get absorbed onto it. But if you take a mirror or a whitish object, it will reflect also some of the light. So hence, the surface can absorb or reflect, anything can happen. Just I'm showing you one scenario where the light falls onto it and it gets reflected. So has the momentum changed? Come on, tell me. Did momentum change? Momentum, did it change? Yes or no? Momentum is a vector quantity. Please do not forget that. Momentum is a vector quantity. This is your new momentum. This is your new momentum of that photon which got reflected. Has the momentum vector changed? Yes, definitely. Yes, it has changed. So when momentum changes, what happened? Isn't there a force acting on it? Isn't there a force acting on it? Right? Remember, whose law is this? This is Newton's second law. Definitely Newton's laws of motion. If you remember it, if there is force and if you take the area of the surface, the force acting per unit area, the force which is acting per unit area, what is that called? Pressure. What is that called? Pressure. So isn't there a pressure because of light? That is why it is called radiation pressure. Understood the concept behind it? Everybody with me? Yes, change in momentum is impulse. Impulse upon time is force. Correct. So changes in the momentum, also rate of change of momentum causes force, and that force upon the area gives rise to pressure. Very good. So this is called as radiation pressure. Now the formula for the radiation pressure is very, very simple, guys. See, if it is absorbing, all the light gets absorbed, then the intensity of the light, if it is I is basically the intensity of light. Intensity of light. Now the intensity of light is having the units of watts per meter square. That means how much energy falls on that surface per unit time per unit surface area. If you take 1 square meter, in 1 second, how much energy falls on it? That is the intensity of light. If the light is bright, more intensity. If the light is very weak, dim light, bedroom lamp, then very less intensity, very less energy is falling on that surface per unit time per unit area. That is the meaning of intensity of light. It depends on that intensity. Why? Because more intense the light, more photons means more change in momentum, more force and more pressure. So guys, the formula for the pressure, okay, so I'll just put it over here. So formula for the pressure, radiation pressure is just I by C, and the radiation force will be nothing but the radiation pressure multiplied by the area. So that comes out to be I by C into A. That's your radiation force. So these are again very important formulas. Radiation pressure is I by C and force is IA by C for absorbing. No problem, bless you Joseph. You can watch the missed part after some time. Great. Now, yes, this is power by area. You can see energy per unit time per unit area. So that's how intensity has been defined. Oh, can I also say, my dear students, intensity is proportional to the number of photons number of photons falling per unit time. Can I say this? Yes or no? Think about it. Can I say intensity of light is proportional to the number of photons? If more light particles come, the light is very intense. If very few particles come, then the light is less intense. Yeah, I can say that. So I A by C for force, I by C for pressure. Guys, what if it is not absorbing? What if it is reflecting? What if it is reflecting? Can you quickly tell me what will be the changes in the formula? Let's see how many of you are smartly able to think what will be the new formula if the surface is a reflector, not an absorber. This is for absorbing surface. What if it is a reflecting surface? Come on, let's see. Come on, guys. Let's see how many of you can answer this. I'm waiting for all the warriors on the NEET English channel to answer this. No, it's not about the sign. Vijay and Prem. The reason why I'm not worried about the sign is because I'm just interested in the magnitude of the pressure. So if it is a reflector, it will go there and come back. So the change will be twice. Why is it twice? Think carefully. If it is absorbing, the momentum mv or whatever is the momentum becomes 0. But if it is reflecting, it goes there and comes back. So if it was just getting absorbed, the change is 0 minus P. But if it gets reflected, final minus initial, P minus P is 2P. P minus P. You would have done these kind of questions in 11th standard. If you just go and stop, change in the momentum is 0 minus mv. If you turn and come back, change in the momentum is mv minus mv. Minus because direction is opposite. So sign will change. That will make it 2 times. Hence, yes, you will get the answer as 2I by C and 2IA by C. So 2 will come. That's the only difference. Okay? So if you absorb, it is 1 times. If you absorb and again then release, the change is 2 times. That's what you should understand. So in case of a reflector, the changes in momentum are basically twice as of absorbing surface. Twice as of absorbing surface. Very, very crucial. Keep all these things in mind. Let's move on to the questions. Radiation pressure on any surface depends on, let's see how many of you are able to answer this question. Come on, quickly spam in the chat box. But it does not obey the conservation of momentum. No, Ash A. Photons do obey the laws of conservation of momentum as well as energy. Laws of conservation of momentum and energy are universal laws. There is no exception found till date. So everything in this universe will obey law of conservation of momentum and also law of conservation of energy. Always. Okay, Ash? So when photon hits an atom, that momentum of the photon gets transferred to the atom and even that atom might start moving. So when light falls on an atom, the light also starts moving, or it might get transferred to an electron. The electron might get higher energy and it will jump to, maybe higher orbits. All these things can happen. All right? B or C? The correct answer is B. Very good. Many of you answered B. Some of you answered C. It's dependent on the nature of the surface and light use. Because, see, if you talk about, radiation pressure is nothing but I by C or basically 2I by C. So it depends if it is absorbing or whether it is reflecting. Definitely is dependent on the nature of the surface. It depends on the nature of the surface. That means whether it is absorbing or reflecting. The second point, if you notice, intensity of the light use. Definitely intensity is there over here. So intensity also matters. It's dependent on frequency. Where is frequency here? There is no frequency over here. Nature, yeah, it is there, but frequency is not there. So intensity and the nature, that's all, guys. D, no, depends on nature of the source. No, does not depend on the nature of the source. It can come from a lamp, it can come from a candle, it can come from a LED, doesn't matter. Light is light. So it does not depend on the source. Okay, it does depend on the nature of the surface, but not on the source for sure. I hope this is clear. Okay, what if the surface is partially absorbing? Then only that much part of the intensity will be considered. Let's say out of that intensity, half the intensity is getting absorbed, half is getting reflected. So in this formula, you will use half the intensity for the contribution of the pressure due to absorbing formula, and the remaining half you will use it for the reflecting formula, and you will add both of them. So we'll take them separately, that's all. We'll take them separately, we will take individual contributions, that's it. Okay, fair enough. Let's move to another question. Let's see if you can solve this. Light of intensity 9 watts per meter square is incident on a black surface. Then the pressure on it will be. Okay, and we'll be doing lots of problems, Sandhya and so many others. In the next few sessions, you will see that after completing 1 or 2 sessions, we'll be doing problem solving sessions on this as well. Great. Let's see how do we do this. Light's intensity is this on a black surface. Black surface means absorbing or reflecting? Black surface means absorbing or reflecting? Obviously it is absorbing surface. So the pressure on it, the formula will be just I by C. What is I? I is 9, C is 3 into 10 to the power 8. So 9 by 3 is 3, 10 to the power 8 will go on the top as minus 8. Do you see this Newton per meter square is so small, it's so negligible, guys. Yes, C for captain. You see that? Captain Shreyas. Yes, that's my name out there. Very good. Option C is the correct answer. Very good, Pandya. Very good, Cat. Very good, GV. Very good, Jai Shakti. Prem Kumar. Very good, Crazy Fellows. Very good, Reena, Sikram, Sara, Shagun, Gokul, Akila, Surya. Very good, guys. Very good, Maha. Very good, Ashika. Excellent, guys. So it's very small. You will barely feel it. 10 to the power minus 8. So small, yeah. So small. What will you feel? Nothing. Okay. Now, de Broglie. Let's go to de Broglie. He did a very interesting thing. You know what interesting thing he did? Very crazy thing he thought. He thought that light has dual nature. 100, 300 years people thought, whatever, light is a wave. Light is a wave. Maxwell showed it, Huygens showed it, Fresnel's experiments, Fraunhofer, Huygens, and so many others, Young, all these people, what did they say? Light is a wave. So there was one group of scientists saying light is a wave. Then Einstein, Planck, and other people, they said no, light is a particle. Then it was again accepted, okay, light has both behavior. So if light can show wave and particle behavior, light, which can show electromagnetic as well as photon type behavior, then can mass, matter, like proton, electron, neutron, which we know is particle. Why do I know it's particle? Because it has mass, because it has momentum, because it can collide, it can interact. So I know it's a particle. Can that also show wave-like behavior? And to his surprise, later on it was found that yes, they can also show wave-like behavior. But what kind of wave is that? No, don't use I by 2C for reflector. For reflector it is 2I by C. Be careful, Siva. Yes. If it is reflecting, you can use 2I by C. Yes. Correct. So basically he thought that even particles can show wave-like behavior, but those waves are not electromagnetic. Are they electromagnetic? Are they sound waves? Are they waves on a string? Are they waves on water? Are they light waves? No. What are those waves called? Okay, let's think about it. What are we talking about? Matter. Matter means proton, electron, neutron. All these are particles. Their wave. So matter wave. Oh, it's a new kind of wave. Very good, Christo. Very good. Understood. So he talked about matter waves. So let's talk about this. So when we have matter, example, proton, electron, neutron, etc. These are particles of matter. These matter show dual behavior. So they have particle-like behavior. Which we already know. It's nothing but momentum is mass into velocity. Their kinetic energy will be half into m into v square, which can be also written down as p square by 2m. That's the kinetic energy. Correct? All these are formulas for particle-like behavior. He saw they also have wave-like behavior. they also have wave-like behavior. So what is the formula for that wave-like behavior? Simple. Do you remember the formula for momentum of light wave? Momentum of light wave, in case you have forgotten, no issues. I'll show that to you. Let me just put it in some different color maybe. Alrighty, let's just use green here. So when we talk about light, then it has two kinds of behavior. One is that wave behavior where C is equal to F lambda and all of that. And then it has particle behavior where the momentum is H by lambda. Momentum is H by lambda. Very good. Very good. Very good. So he thought, why not interchange the two? Why not interchange the two? And to his surprise, it came out to be correct. So what he did was, for a wave, he just brought lambda over here, P over there. So the wave nature of matter, which is then called as matter wave, that wavelength is H by P. That's it. Or you can just say H by mass into velocity. Here you can use it because it's a particle. So for particles, mass into velocity works. So H by P. That's what it came out to be. And this is the correct answer. If you want, you can use momentum as this formula over here. You can see right over here, if I rearrange this, P square will be 2mk. So P will be equal to root of 2mk. So you can use this value over here also if needed in the problem. So that is the wavelength of the matter wave. So whenever a mass moves, you will see it will have momentum, it will have a wavelength. Lot of people get confused. Sir, what is this wavelength? I didn't understand. Sir, what is the meaning of this matter wave? Okay. See, imagine some mass is moving. Just imagine some mass is moving with some velocity. It definitely has some momentum. It has some, it can create some impact. It can it can collide with something. But when I say that it has wave-like characteristics, does not mean it moves like this. How many of you thought that matter wave means the particle actually goes like this? That is completely wrong. Can we say matter waves have mass? No, matter waves don't have mass. The particle of the matter wave has mass. The particle nature of the matter wave has mass. Matter wave is just a wave. It's just a energy, flow of energy. That's it. So a lot of you were even taught, when I was studying, I was told matter wave means it goes like this. And then I was like, oh. Then the teacher explained me also this. Because H value is very, very small. What is the value of H? 10 to the power minus 34. So that's why the wavelength is also very small, 10 to the power minus 34 meter. So the wavelength is so small you cannot see it. I was like, oh right, we cannot see it. Then later on I understood that is not the case. There is more complex theory to it. So the matter waves can't be seen like that. There are experiments to see the matter waves or to feel or to detect those matter waves. You need dark room setup, you need crazy amount of accurate instruments to detect these matter waves. So that's a whole different ball game. But understand, matter wave is something which you cannot feel around you because those are waves. Those are wave nature of matter. When you see a matter hitting you, that's the particle behavior which is contacting you. That's the particle behavior, not the wave behavior. Wave behavior is completely different. Okay, clear? Yes. Is this valid for only moving particles? Yes. When you have a particle at rest, will it have a matter wavelength? Yes or no? Will it have a matter wavelength? Yes or no? Very good questions you guys are asking. Yeah, I'm proud of you. Very, very smart students you are. So I'm wondering, why did you say and how you guys are getting such less marks when you put up in the polls? I feel that you guys deserve 150 marks, guys. Like, I felt very sad when many of you said, sir, I'm getting less than 100 marks. 84% of the students said, sir, we are getting less than 100 marks in NEET physics out of 180. I was so sad because of that. I felt that, no, these students, I don't think they are, average or below average. I think they are smart, just that they don't know what to study, how to study. So that's why I'm here, guys. Yes, so when a particle is at rest, there is no wavelength. There is no matter wave. Very good. Excellent. So let's see if you can solve some questions. Matter wave is associated with matter when it is, okay, oh, I think I'll leave the answer maybe. Can 2024 students also watch it? Definitely, Sarah, why not? Please watch it. Yes, Resmi, my kids. My kids are going to do wonders now, isn't it? Okay, I hope you guys are subscribed to the channel, especially the new timers out here on NEET English channel. Make sure you subscribe. Yep, that's very important so that you do not miss any of the classes. And also go ahead, smash the like button in case you haven't done that yet. What are you guys doing? If you got 140 in the previous mock test of physics in Vedantu, that's very good, Siva, very good. I'm pretty sure you will reach 160 also in days to come. Many people are confused between C and B. A, definitely not Sandhya. Think about it, I just told. When it is at rest, how is there a matter wave? No, right? So, think like this, my dear students. Matter wave is associated with matter. So, lambda is h by p. So, when p is not 0, lambda is also not 0. So, when it is in motion, with the velocity of light only, wrong. When it is in motion with any velocity, correct. Why light? Why light? What has light got to do with anything? Nothing. So it need not move with the speed of light. Even if it moves with 3 meters per second, 5 centimeters per second, 100 kilometers per hour, any velocity, it's okay. Alright? So hence the answer is C. Matter waves can undergo interference? Yes, Kailash, because it's a wave. So waves can undergo all those things what any light or sound wave can do. Constructive interference, destructive interference, diffraction, refraction, all those things it can undergo, guys. All those are wave-like characteristics. Should move, that's it, exactly. Let's see if we can solve this. Alpha particle and proton. Alpha particle means helium, which is ionized. Okay. Proton are accelerated from rest by a potential difference of 200 volts. By a potential difference of 200 volts. After this, the de Broglie wavelengths are lambda alpha, lambda p. What is their ratio? So when these particles accelerate, what will happen? They will gain momentum. And when they have momentum, what will happen? They will have wavelength. So question is, what is the ratio of the wavelength, guys? That's the question. Let's see if we can solve this. So first of all, let's see if I know the formula for wavelength. The wavelength formula in general is h by momentum. Just some time back, I just showed you momentum is root of 2 mk. Do you remember this? If you have forgotten, let me take you back. Momentum is root 2 mk. I just showed you this over here. If you want, I'll block all these results. These are very standard. This is very important over here. Okay, so I can say over here that since momentum is root 2 mk, I can also say that this is the kinetic energy which it has got because of acceleration. When you accelerate a charge, the kinetic energy that it gets is always the charge multiplied by the potential difference. This is standard formula from electrostatics. If you take 1 coulomb of charge and accelerate it by 1 volt, then the energy that it gains is 1 joule. Do you remember this was also the definition of volt? 1 volt is 1 joule per coulomb. Or when you take 1 coulomb of charge and accelerate it by 1 volt, the energy that it gets is 1 joule. Remember it? Remember it, guys? This was the definition of volt also. So this will then become root of 2mq into delta V. So if that is P, therefore the wavelength will be h by root of 2mq delta V. H is a constant, 2 is a constant, mass is different, Q is also different. These are the only two different things. Who are the different things? Mass and charge. So wavelength is also different, voltage is the same. So can I not say lambda is inversely proportional to root of mass and also proportional to root of charge? Root of mass and root of charge. So lambda of alpha by lambda of, what is it? Proton will be, take inverse ratio. Here I will have mass of alpha and mass of proton on the top. Here I will have charge of alpha and charge on proton on the top over here. Okay. So mass of proton and mass of alpha. Guys, this ratio is 1 by 4 because alpha particles has 2 protons, 2 neutrons. Proton is just 1 proton. So there are 4 particles here, there is 1 particle here. Over here, proton, what charge does it have? 1e. What is the charge of alpha particle? 2e. So e anyways gets cancelled. So I'll be left with 1 by 2 and here 1 by root 2. That is lambda alpha by lambda proton. So lambda proton by lambda alpha will be 2 root 2. Root 2 is nothing but 1.4. So it will be 2.8. So it will be 2.8. That is the answer. Let's see, where is it? Option number B. Very good. Many of you said B. Very good. Root 4 into 2. So this was a good problem on your de Broglie wavelength and acceleration. These kind of questions are very common in NEET examination. Let me tell you that. Let's do the next part, and that is photoelectric effect. And I have some wonderful animations to make you visualize photoelectric effect. So guys, today is the time where you're going to actually visualize the photoelectric effect. Ready for it? Sir, how there is charge into potential difference, Satya? So the logic for that, see, let me remind you, 1 volt, okay, is nothing but 1 joule upon 1 coulomb. 1 joule is 1 coulomb into 1 volt. Okay, that's how it works. So the energy that the particle gets is basically how much charge you take into how much potential difference you accelerate it with. Hence, that kinetic energy which the charge gets is the charge into the potential difference. This is the formula for that. Is there in electrostatics? So it's a previous topic. So I was assuming you knew it. Anyways, I'm telling this to you right now. Okay? How 1/4 came? Sikarama? Proton. What is the mass of a proton? What is the mass of a proton? Just assume it as something now. Just assume it as something. Let's say M. So what will the mass of alpha particle? 2 protons, 2 neutrons. Proton, neutron, roughly same mass. So it will be 4m now. Mm will get cancelled. So 1/4. Everybody got it? Okay. I hope this is clear. 1/√2. Why is it 1/√2? Root of 1/2 na bacha. Root of 1/2. What is root of 1/2? Yes. So root of 1/4. What is root of 1/4? It's 1/√4. 1/√4 is 2. 1/√2 will just come over here because this is root of 1/2, right? Because I can just write this as 1/√4 into 1/√2. Root 4 is 2, root 2 is root 2. That's it. So then I flip it. I just flip it. So 2 root 2 goes on the top, and that's what the value you get. Okay? I hope this is clear. Good evening, Kumaran. Thank you so much. Okay, so Marieshke, please watch all my lectures. You have to watch all my lectures. That's the only way you can improve physics. It will not happen in one day. You have to make a promise that you will attend all the classes. Okay? Neutron or outside the nucleus or inside? Neutron is inside the nucleus. Nuclear particle, neutron is there inside the nucleus. Okay? Fair enough. Let's go on to now the next part. Now, photoelectric. Photoelectric. Photo means light. You take a photo, light, okay? Electric effect, electrons are coming. Because of light, electrons are coming. Achha. So that is photoelectric effect. Now you can see that thing happening right over here. Can you see this is photons, this is light. Light falls on a surface, electrons come out. Photoelectric effect. But then to bring these electrons out, is not so easy. You have to do something. You require to pull them out. Okay, you have to pull them out. So you require some energy. So at least some energy is required. So when light of high frequency, why high frequency? Think about it. Why this sufficiently high frequency is asked? Because energy of a photon is HF. More the frequency, more the energy, then only it can pluck out. It can pick that electron and throw it out. That's when the photoelectric effect occurs. These electrons that come out are called as photoelectrons. These are called photoelectrons. The one which is falling onto it, that is nothing but photons. Or basically light. Light falls on a surface. Electrons are ejected. Those are called as photoelectrons. As simple as that. Very nice. I have a beautiful simulation as well. Oh my god, here I am teaching. Very nice, guys. Guys, go ahead, smash this fatafat like button. This has to go above at least 200. What is this? Okay. Now I'm going to show you this simulation as well, where there will be a battery, there will be a surface, there will be a tube, there will be light falling. I can change the color of light as well. Okay. Yes, I can change the color of light as well. Hopefully, yes. And I can also change the intensity of light as well. So I'm going to do all these things and we're going to see what is going to exactly happen. There are also some graphs which you are going to study over here. Very, very interesting setup, guys. Okay. So let's go to that in a bit. But for now, let's understand this photoelectric effect setup. In this setup, you have a tube. What do you have a tube? It should be vacuum tube. Why do you want vacuum tube? Why not any, just take a surface and just make light fall on it? The problem is when these electrons come out, they will collide with the air molecules, nitrogen, hydrogen, oxygen. And when they hit them, they might produce undesirable effects. So you don't want all that headache. So that's why you use a vacuum tube. Clear? Okay. Next, you use a metallic surface. Now you'll be like, why do I use a metallic surface? Why not rubber? Why not wood? So this is how you have to think, guys. How you read experiments, correct me if I'm wrong. Oh, there is vacuum tube, there is metallic plate, okay, there is light falling, there is a window, okay, it's connected to the battery. No, that is not how you study. You have to think, why this, why that? Then you will learn and then you will not forget. Because you have convinced yourself. So convincing is also an art. And convincing yourself is a even bigger art. So why metallic surface, guys? Why metallic surface? Electron rich. In fact, the electrons are readily available. It's not just rich with electrons, it is also readily available because conductors, metals are having free electrons, so they can be plucked out easily. Imagine you have to pluck out some seeds or some fruit from a farm. If the fruits can be easily taken, you will be very happy. If it is somewhere inside the ground like a potato, you'll be like, oh my god, I have to dig that mud, then I have to take out that potato. Leave it, I just don't want it. Okay. Instead, if the fruit is just hanging, you'll be like, I'll just pluck it very easily. So same thing happens in case of metals. It's easily pluckable. You can easily take it out. Okay, that's why metallic surface. Why this window? So that light can fall. Okay. Why this circuit? What is all this nonsense? Battery. Oh my god, voltmeter, ammeter, so many things are there. Why all this? Okay, one by one. What will the job of the voltmeter be? To see what is the voltage which is created, correct? Between these two terminals. It will measure the voltage and we'll see some interesting things. What is the job of the ammeter? Acha, these electrons which are ejected out, the photoelectrons, they will be collected over here. They will be collected over here at the collector. This will be the emitter, this will be the collector. This will be the emitter, this will be the collector. The collector plate will collect all these electrons. What will they do collecting? Will it just keep collecting and keep it in a basket? No, right? It will flow. Where will it flow? In the circuit. So the electrons will flow. It's not that you're plucking out the electrons and then it is like, oh my god, I'm so sorry, now electrons are not there. Sorry, bye light, I can't give you more electrons. No, it doesn't say that. Why? Because these electrons travel through the circuit and come back. These travel through the circuit and again come back. So it's like somebody is, feeding onto it continuously. So there is a current which is set up, there is a voltage which is set up, and then what is the job of this battery? What is the job of this battery? The battery is there to assist it or to oppose it. Why assist and why oppose? We'll come to it in a bit, but you can help the current. So if you connect the battery in the proper way, then you will see it will help in the current. So current will increase. If you connect it opposite, then the current will decrease. So how you connect the battery also matters, guys. Whether you are helping it. So when you help it, it is called as forward bias. When you help it, it is called as forward bias. When you reverse it to slow the current, it is called reverse bias. Everybody clear with the setup of photoelectric experiment? Everybody clear? Everybody is sure of each and every part over here? Something like a semiconductor, it's not a semiconductor, but yes, it is not a semiconductor, but this is how it works. Very nice. Excellent, Madhumita, Rashmi, Prem, Ashika, Siva, Miki, very good, Sarah, very good, Vijay, very good. Excellent target. Now, let's do some question just to warm you up. This is basically a fact-based question. It's there in NCERT, it's there in your HC Verma and any standard textbook. This photoelectric effect is a really fast phenomena. How fast is it? So when the photon falls onto the metallic surface, the electron gets ejected out. How quickly is that electron ejected out? Does anybody know? Can you tell me this? Come on, guys. Bhandra, what should I explain, bacha? Yes. Option C. You can always replay Bhandra. So what you're going to do is just slide the slider below and just replay the part whichever you want help with again. Okay, great. There is almost no time lag. It's not in seconds, it's in nanoseconds. The Tata Nano car, right? Nanoseconds. So 10 to the power minus 9 seconds. Hardly any time. Exactly, 10 to the power minus 9. Very, very, very small. Within a blink of our eye, that's it. There will be thousands, millions of electrons which will be coming out of it. Yes, now we'll be coming to the setup, the experimental setup. So guys, Bhadra, understand that in this setup, light is falling from here. It's falling on the metallic surface just like it was falling over here. The electrons are ejected out, they are collected. These electrons flow through the circuit, come back over here. The light keeps falling, the electrons keep flowing, and there is current setup. You can measure the voltage. The battery helps, or it basically lowers the current depending on how you have connected the battery. That's all. That's the setup. As simple as that. Okay, is that fine? What is the time lag? The time lag is basically the time difference. Like when it hits till the time it comes out. Light falls and then the electron comes out. There is a lag. So how much difference of time is there? So when it starts hitting the surface till the time it comes out, the lag is 1 nanosecond or less. Okay, I hope this is clear. Now the next thing is the threshold frequency and associated concept, that is work function. Let's talk about this. What is this threshold frequency? Remember, just some time back I was telling you, you need high energy, high frequency photons, only then photoelectric effect occurs. Why is that so? The reason is, when, look at this guys, when you talk about the energy of a photon, when the energy of a photon is equal to hf, if imagine the frequency reduces, the energy of the photon will reduce. If the energy is not enough to pluck it out, so when a fruit is hanging on the tree, you need some effort to pluck it, right? If you are like, sir, I'm so weak, even if somebody touches me, no, I will faint, sir. Then sit, man, aram se, you take rest. You need some amount of energy. You need to climb up the tree a little bit, and maybe you just need to stretch your arms, pluck it, apply some force. Only then the fruit will come in your hand, right? Correct? So same way, you need at least some bit of effort to pluck that electron out. Otherwise, it will not be able to come outside that surface. So then that minimum energy of that particular photon, for which the photoelectric effect just begins. Below that, nothing. Above that, yes. So that is the critical least value of the energy of the photon. Then that frequency is basically called as your threshold frequency. So the electron emission takes place when the frequency of the light is above a certain critical value. That critical value is f0. That critical value is called as the threshold frequency of that surface, of that particular surface. This is that minimum energy. You can also write it as hc by lambda naught. Can you guys guess? Can you guys guess what is this lambda naught called? Obviously, this will be called as the threshold wavelength. This will be called threshold wavelength, of course. Is that clear, my dear students? Yes. So photoelectric effect occurs when frequency is more than f0, then it occurs. If by chance f is less than f0, then it doesn't occur. You can see over here, light is falling, still nothing is coming out because that energy of the photon is not enough to pluck it out. Hence, no photoelectric effect will occur in this case. Here, photoelectric effect occurs because f is more than f0, the critical frequency. Everybody clear? Excellent. Very nice. So this is something again which you should know, obviously. So I'm just going to highlight this, block this results, and I'm going to keep it over here. Now that minimum energy of the photon which is required to pluck it out obviously depends on the metal. Just like mango fruit might be very difficult to pluck, maybe bananas might be more difficult. Same way, when you pluck that electron from copper, it might be difficult. From aluminum, it might be very, very difficult. From maybe gold, it might be very easy. So it depends on the material. So every metal will have a different threshold, agree or disagree? Because it might be difficult or easy depending on how the metal is, how the atoms are, how many electrons are there, where is it stuck, how well the forces are, how is it binded to the atom, so many things. But it depends on the material. So hence I have mentioned that it depends on that metal. Read this line carefully. It's a characteristic of that metal. It depends on the metal. Different metals have different critical frequency. So that energy is called as the work function. And the symbol for that work function, is phi. So phi is that minimum energy of that particular photon required to pluck it out. So it is HF naught. So phi is basically HF naught. That's the minimum energy required to pluck it out. That's the minimum quantity of energy, and it is obviously dependent on the metal. Depends on the metal. And let's try this out. Look over here. Okay. So I have some decent intensity of light. Okay. Can you see right now? Let me make this as 0 volts. Okay. Little difficult. Okay. This is 0 volts. Can you see light falling onto it and electrons coming out? Light falls. Do you see electrons are coming out? So is photoelectric effect happening over here? Yes. Great. It is happening. But do you see all the electrons are not moving with the same speed? Why is it so? Do you see some electrons are moving really fast, some electrons are slow, some are very slow? Why is that? Can you guys think? What is the reason for that? The reason for that is not all electrons are lucky. When these electrons get plucked out, when they are taken out, some of them will collide with each other, some of them will be stuck somewhere. Because of that, they might lose some energy. So because of that, some energies are lower, some electrons are with higher speed. Some electrons which are not so lucky, they might hit each other, they might collide with each other, they might get stuck somewhere. Because of that, they'll lose some energy. But there are some lucky ones, very lucky. So those people will go with very high speed. So there is a range of speeds. Do you see that? There is a range of speeds over here. Very nice. Next thing, I will change now the color. If I make it from violet to red, will the wavelength increase or wavelength decrease? Answer in the chat box quickly. Like afternoon traffic, yes. So will the wavelength increase or decrease if I shift from violet to red? Come on, my warriors. Red, long wavelength. Violet, short wavelength. Correct. So longer. So will the energy of the photon increase or decrease? Will the frequency increase or decrease? Think about it. Obviously, if the wavelength increases, if I shift from here, frequency will come down, energy will come down. So the chances of these electrons coming out will also reduce, na? The chances of these electrons coming out will also decrease, correct? Because when the wavelength increases, frequency, energy, everything will go down. So as wavelength goes up, frequency and energy comes down. Let's try this out. I'm just going to shift it over here. I made it blue. Okay, I'll make it green. Oh my God, guys, there is no effect. Photoelectric effect stopped. What does it mean? Somewhere in between, I have threshold wavelength or threshold frequency somewhere over here. See over here, photoelectric effect started. Photoelectric effect has started. Do you see that, guys? Photoelectric effect has started. I can just try out some different wavelength. Okay, still it is going on. If I make it slightly more, maybe it stops. Yes, there you go. Somewhere in that green zone, it has stopped. Great. If I change the metal from sodium to, I don't know, maybe calcium or something, or maybe, I don't know, copper. Okay, let's try. For copper, it's still not working. So I need to change the wavelength and see. It's still not working. Still not working. Oh my God. Still not working. Still not giving any photoelectric effect. Still not giving anything. Still not giving anything. Oh my goodness. Oh, there it started. So for copper, you can see it needs very high energy. So it depends from metal to metal. So the threshold wavelength or frequency depends from metal to metal, my dear students. Did you see that? I just changed the material over here. I have the option, I can choose the option. For sodium, it came out to be somewhere in that green color. So each metal has different. So you can try this out later on. I will share you the link. So don't make me try all these things, sir. Show it for this, show it for that. Yeah, we can do that, but I want to move ahead. Okay, you get the idea. That's all. I want you to get the concept over here. Great. So you got the idea of work function and all of that. Now, what is the effect of, what is the effect of different colors on the electron which is coming out? Understand, when you go from red to violet, red has long wavelength, so frequency is very less, or energy is also less. But when you go to violet, from red, orange, yellow, green, blue, violet, then for violet, wavelength is less, frequency is more, energy is also more. Because of that, what happens, if you are using longer wavelengths or shorter energy, the chances of electron coming out are also less. But if you use higher energy or short wavelength, then the chances of electrons coming out are not obviously more, but also the electrons coming out are of higher energy, because you are giving only more energy, the electrons will also come out with higher energy. So obviously the kinetic energy of the electron depends on the frequency of the light. Do you guys agree or disagree? Do you guys agree or disagree? Everybody with me on this? So as you increase the frequency of the photons, obviously the electron's energy will also increase. Okay? I hope this is clear. And this can be also seen over here. So if I choose light of higher frequency, you can see, look at this, electrons suddenly coming out of higher energy. Higher energy electrons are coming because this wavelength is small or frequency is higher. But the moment I reduce the wavelength, increase the wavelength or reduce the frequency, the electrons do not have so much of energy. You can see that very, very clearly. Okay, right over here. So maybe we can solve some questions based on this coming up on your screen. All right, sodium and copper have work functions 2.3 and 4.6. The ratio of the wavelength is approximately. I want everybody to spam the answers in the chat box. I'm so glad, Harshini Amrasu. I'm so glad. And this is how the classes will be. Sir, if we speak about threshold wavelength, it's the maximum range, unlike threshold frequency, which is the minimum range. Yes, it's the maximum. Yes, so because wavelength and frequency are inversely related, so for frequency, if it is minimum frequency after which it starts, for wavelength, it will be a maximum wavelength, till which, you will get, photoelectric effect. Yes, kinetic energy is the promotion to the frequency, yes. A lot of you are saying A, let's figure out if the answer is A. No, the answer is B, guys. Let's see what mistake you made. Maybe you made that ratio opposite. Anyways, the ratio of the wavelength is approximately, we all know work function is hf naught, so it is hc by lambda naught, or rather work function is inversely proportional to the wavelength. So hence lambda 1 by lambda 2 will be phi 2 by phi 1. Phi 2 is 4.6, phi 1 is 2.3, so hence it is 2:1. Order is very important. This will be considered for 1. This will be considered for 2. Order is important. So be careful, guys. Okay, so a lot of you got 1:2. I think you wrote 2.3 on the top and 4.6 below. That's all. Very nice. Inversely related. Exactly. Hello, Sivagami. Welcome, Bachalog. Next concept, stopping potential. Now you'll be like, what the hell is this stopping potential? Okay, I'll tell you. See, simple, guys. There is one plate over here, there is another plate over here, correct? Light is falling onto this plate. This is your light. This is your light. So because of that, your electrons are getting ejected out. Now, answer the following. Electrons are coming out of it like this. All electrons do not have the same speed. Some have very large speed, some have very small speed. So all kinds of electrons are there. If by chance I make this terminal positive and this terminal negative, what do you think will happen? If I make this plate positive and this plate negative, what will happen, guys? Will these electrons get accelerated or will they get decelerated? Answer in the chat box. Sivagami, my name is Captain Shreyas. You can see that right over here. Captain Shreyas. Yeah? Okay. What do you think will happen? Come on, answer in the chat box. Think logically. This plate is connected to the positive side of the battery. Just think about it. This side is connected to the positive side of the battery and this side is connected to the negative side. What do you think will happen, guys? Accelerated. Think again. Think again. Sure. This is positive. This is negative. Sure. Pakka? Deva says decelerated. All right. Well, the correct answer is obviously accelerated, guys. Positive will attract the electron. Electron is a negative charge, no? You guys forgot, yeah? Electron is a negative charge. Negative and positive will attract. Negative and negative will repel. So it will get accelerated. Definitely, it will accelerate. It will accelerate. So even the weak electrons will go very fast. Weak electrons will go fast. So what do you think will happen because of this? What do you think will happen because of this? When more electrons flow, what do you think will happen? Will there be more current or less current? Will there be more current or less current? No, this is not reverse bias. This is forward bias, guys. This is basically then forward bias. Forward bias. So because of that, there will be more current. Agree or disagree? There will be more current in this. Exactly. Now the reverse of this. Now the reverse of this. I take the same plates. I take the same plates. Again, the same light is falling. The same light is falling onto the surface. Again, these electrons are coming out like this. Each electron might have different speeds like we have discussed before. These are all electrons. So now if I connect this to positive, this to negative, obviously negative will decelerate it. The electron negative charges will decelerate. Positive will pull the electrons backwards. So obviously it will get decelerated. Decelerated. And if it is decelerated, it is called as reverse bias. It is reverse bias. Agree? Very nice. I will teach 11th portions also, Sharmila, very soon. Okay, very nice. Now I want you to focus. Okay. If it's getting decelerated, then Bichara, these electrons which are going with so much josh, just like you guys, you also have high josh, you are going with so much energy. Somebody comes and demotivates you. Some relative comes or some random person comes and tells, hey, what is this? You cannot study, man, go to hell. Okay, scolds you left, right, center. You will be like, yo, what is this guy saying? Okay, forget it, I will not study only. Same way, reverse bias, decelerated, demotivated, gone. Even those electrons which were with high energy, they will get demotivated. They will not reach only the other side. So the current will reduce. So there will be obviously less current here. There will be less current here. And what will happen if you increase the voltage? If you increase the voltage, if you make it more negative, it will be further decelerated, further reverse bias, further less current until it becomes zero. Until it becomes zero. Prem Kumar Siva agrees with me. Yes, demotivation faced in real life. So until it becomes zero, it's like stop. That's it. Enough, done. I'm going to throw my books and I'm not going to study at all. So there is no current which is flowing after a point. So what have you done? You have stopped the current. So if the reverse voltage, reverse bias is increased, then what will happen? It is decelerated further. It is decelerated further. There is less current till it becomes zero. It completely stops. So that reverse voltage is called as stopping potential. What is it called? Stopping potential. Everybody clear with this? The symbol for that is Vs. You have stopped it. That voltage which is required to stop it is called stopping potential, guys. Excellent. Now, what have you done in stopping potential is you have absorbed all the kinetic energy. So all the kinetic energy is getting absorbed. Each charge is nothing but E. Each electron charge is E. The stopping potential is Vs. So the kinetic energy is EVS. This is that maximum kinetic energy which gets absorbed when you just stop it. So it's like you're stopping it. So charge into voltage is energy. Remember, I just told you this? Forgot? I just told you over here. Where did it go? Somewhere back. Somewhere over here. Charge into voltage is energy. Exactly the same formula is used over here. All right? Exactly the same thing is used over here. Yep. So charge into voltage is the kinetic energy. This is the formula for the stopping potential. Yes, yes, the place which you illuminate is then called as the cathode. Yes, Siva. Okay. Now, if you have understood it till here, tell me what will happen if you use forward bias and keep on increasing the forward voltage. Like, sir, that is good. More current will come. And you're like, sir, I will use even more voltage. Very good. Even more current will come. Sir, what if I keep on increasing that voltage? There comes a problem. There comes a problem. You know what problem? There will be not enough electrons to reach there. There will be a saturation. See, a teacher can motivate. Teacher can motivate. Teacher can motivate. Okay? But after a point, you will also reach saturation. How much can I further motivate? That's it. Your performance will peak. Correct? So same way, if you are given forward voltage, the current will also increase, but there will be a saturation. So if in forward bias, for some reason, if the voltage is increased, then what will happen? Forward bias is increasing, acceleration will increase, more current, but till it reaches some kind of a saturation. Till it reaches some kind of a saturation. Don't believe me? Okay, I will show it to you. I will show it to you right over here. Let's take something like, okay, sodium only, let's say for example. All right. Now what I'm going to do is I'm going to apply forward voltage and we'll see the current versus battery voltage graph. I hope you guys can see this. This is current versus battery voltage ka graph. Do you see there is some current right now? Some small current is there. Some small current, 0.067 amperes current is there over here. Zero voltage is there. This side is forward. This side, you see the negative values. I know it is little small, guys, but believe me, these are negative values, these are positive values. Don't have to know the exact values, just look at the nature of the graph. I will increase the voltage. See where that red dot shifts. I'll increase the voltage. See what is happening. See what is happening. More electrons are going, and it goes till here. Okay, almost it has reached saturation, hardly anything is happening over here. Okay, great. So current has increased. I know the graph is not so accurate, or it is not going slightly up. Actually, it should have gone up, but nevertheless, okay, you can see over here more electron speed is there. More electron speed is there. If I reduce the voltage, then you can see the electrons are not going in so much amount, so the current is not as much. Okay, what will happen if I reverse it? What will happen if I reverse it? Look at this. Oh my God, see, they are coming back. Oh, it stopped. It stopped. Do you see the graph, how it looks? Do you see how the graph it looks? It stopped over here. So you can see after a certain point, the electrons are not even able to reach there. It goes till there and just stops and comes back maybe over here. See, when I apply negative voltage, you can see it is just coming back. It's stopping it. So this is how it works. This is how it works. Now you will be like, sir, what if I increase the intensity? Fine, increase the intensity. Let's say I increase the intensity. It does not matter. The stopping voltage does not depend on the intensity. Just when you increase the intensity, more electrons will come. More electrons will come because more intense light is there. But it does not change the amount of energy of each electron. Just because I increase the intensity, you can see more number of electrons are coming out. That's it. But it has not changed the energy of any electron, because energy depends on the wavelength or frequency. So even if the intensity is less, doesn't really matter. So stopping voltage will depend only, stopping voltage, all right, it depends on the nature of material and the frequency and other things, but not on the intensity. Then you will be like, sir, what does intensity actually do? Fine, let's say I make it forward voltage or something like this. If I make the light more intense now, it's just that more current will flow. That's all. See, if I increase the intensity, more current will flow over here. That's all. That's all. I hope this is clear. Is that understood? So you can see current versus probably light intensity. You can see that graph. So if I change the intensity, you can see as I reduce the intensity, the current also reduces. As I increase the intensity of light, the current also increases. That's a beautiful graph right over here. What a beautiful way to study this, guys. Okay, so I have kept the animation also over here for both forward bias as well as reverse bias. It's there in the PDF as well. It will be available to you. And this is the graph that exactly what we are looking for. You can see our graph also looked almost like this. Almost like this. So when there was nothing applied, there was some current. As you increase the forward voltage, this was forward bias, then you saw the current slightly increase and reach saturation. You can see it is saturated over here. Saturation is reached over here. If you apply reverse voltage, then you can see the current reduces till it stops, till it becomes 0. If you increase the intensity, current increases, but stopping voltage does not increase. So you can see this is of different intensities. It doesn't matter how high the intensity is, stopping voltage does not change. It's just that the current is proportional to intensity. Current is directly proportional to intensity. So if you draw current and intensity graph, it will be like this. Cool. Let's go to the final aspect of this particular session. Saturation point once more. Okay, I'll just tell you why the saturation happens. The saturation happens because why does the saturation happen? That's because all the photo electrons reach the other side. So further increase in voltage doesn't result in more electrons. Hence, there is no change in current. So all the electrons which were being ejected out, all of them are reaching there. That's it. Even the weakest one is able to reach there. There is no further increase in the electrons. That's why there is no change in the current. That's all. But the moment you increase the intensity, then more photons fall, more electrons come out. Hence, more is the saturation current. So the current increases when you increase the intensity of light. I hope this is clear, Siva. Clear, says Vijay. Amazing go. Yes, Sarmila, Srikaram. I will be taking 11 topics. I will be doing 12 topics majorly now. 11th also, I will do the major topics once, and then we will do the remaining ones. Don't worry. Yes, Sharmila, Srikaram. Yep, bacha log. Yep. So feel the electrons. See guys, I hope this simulation has created that feel in all of you. So when you increase this forward voltage, these electrons get accelerated. When you make it opposite, these electrons, even the most energetic electron, Bichara, is not able to go there. That's what is happening. So if you feel it, that's it. And when I decrease the intensity, it's just that the light number of photons is reducing, electrons also is reducing. That's all. Just feel the situation. Very good. Now, Einstein. Last equation, guys. The last equation. And this is very important because there will be problems on this. It's obviously there in chemistry as well. So, Einstein won the Nobel Prize for the photoelectric equation. It's a very simple equation. You will be like, sir, for this he won Nobel Prize. Really? I thought it was for relativity. Actually, he did not win it for relativity. He won it for the photoelectric effect. And this equation is completely based on energy conservation, nothing else. So, what is this equation? Let's have a look at it. Just think of energy, guys. Light falls. Replay everything. You should probably be able to close your eyes and be able to feel what is happening in photoelectric effect. Light falls, electron is plucked out, you need something, and the electron is ejected out. Correct? This is the process. So can I say the energy of the photon goes into plucking that electron out. That means the work function. And the remaining goes as the kinetic energy of the electron. Remaining thing goes as the kinetic energy of electron. If I give 100 laddus, if I give 100 gulab jamuns, out of that 20 gulab jamuns, you just eat it to take out the electron. Remaining 80 laddus or gulab jamuns is there with the electron. Something like that. So that's all. That's all. Yes, I am taking full concepts Bhadra of NEET. right? These are NEET lectures. 99% of the concepts will be clear here, which are important from NEET perspective. Maybe there could be 1-2 lines here and there, but that I leave it up to you. That will not be important so much. That's why I might be skipping 1 or 2 lines here and there, but 99% will be covered in these lecture series. So focus on that 99%, which will give you 160, 170 marks. That 1-2 lines may not even come. Okay, great. That's all. This is the equation for which he got Nobel Prize, right? You'll be like, sir, even I could have written. I'm not even getting full marks in NEET. Still, I'm able to think about this. Okay, no problem, guys. So, energy of a photon is hf. Work function is phi. Kinetic energy of an electron, I can just put it as Ke over here. But I just told you what is the work function formula. It is nothing but hf naught. And kinetic energy, I just gave it to you right over here. See, kinetic energy is EVS. It's nothing but EVS. So I can just use it over here. So E times of Vs. So usually we use this equation or the above equation for photoelectric equation. That's it. This is your photoelectric equation, as simple as that. How easy it is. Nucleus will come after some time, na bacha, after 1 week. Okay, first let me complete sequentially. This will come next chapter. Which will it be? Think logically. Atoms. After that, what chapter will come? Nucleus. Obviously, before nucleus, I will do problem solving session of which 2 chapters? This chapter and atomic structure. Very much similar concepts are also there. Photons is there, HF is there so many times. So we'll do problem solving on that. Then comes nucleus and semiconductor. That also we'll do. Hai na? Clear? Let's do some questions now. Photoelectron stopping potential depends on. White will not reflect all the light, bacha, but most of the light it tries to reflect. Yes, so white will reflect most of the light. That's why petroleum take the color white to avoid heat. Yes, you use basically light colors. So light colors basically are good reflectors. So that's why you reflect all the heat so that it does not catch fire. Exactly. D or C? D or C? Come on. Saran, I will be taking classes at least 3 days a week for now, and as time permits, because there are some recordings going on, as soon as those things are done, I will probably come to 4 or 5. Okay, so right now I'll try to maintain 3 lectures somehow. Okay, great, per week. Okay, the correct answer is actually A. It is not C or D, guys. Some of you said A. I was just seeing your chats. So stopping potential depends on, just use our photoelectric equation. HF is equal to HF naught plus E into Vs. Rearrange it. HF minus HF naught is equal to E into Vs. Just divide by E. So H by E into F minus H by E into F naught is equal to stopping potential. Now if you look at these equations, you will clearly understand that frequency, yes, you can see frequency over here. Next thing, F naught decides the nature of the material. So yes, both are there for stopping potential. Intensity, not even there. Frequency alone, no. Nature alone, no. Both are there. Both of them. Hence option A. Not just frequency, even F naught. Remember, F naught decides work function. Work function depends on the material. Now let's talk about atoms and atomic structure. Now let me tell you, atomic structure is such a big topic and it has a big history. Every person has given his or her own version of what atomic structure is. Like you see in some movies, like one person says, oh, this is what happened. Then they show from some other perspective, you know what, this is what would have happened. So same way, atoms were perceived very differently long time back. Long time back, people thought there are these small particles which are, you cannot divide them. That's it. These were called as kans, or basically just tiny mini particles. And then later on, people understood that, wait a minute, even these particles are made of even more tiny particles. And then those particles are made of even more tiny particles. So that's how the theory progresses. And a lot of people have made contributions in the atomic structure. And these theories have gained a lot of momentum in the last 200 years, I would say. So in the late 1800s and 1900s, you will see a lot of theories of atomic structure being populated and being very, very popular. But people knew about tiny particles much, much before Christ. You can see 500 BC. That's when people postulated about, tiny mini particles. And only in the last 200, 300 years, you can see things gaining up pace. So let's see how many of you know this general knowledge question, guys. Who discovered electron? Type it. Who discovered proton? Type it. Who discovered neutron? Now, let me tell you, these kind of questions can also come in NEET as match the following. Like they can give you a table A, B, C, D or something P, Q, R, and here scientist names, here the discoveries. It might be simple, it could be difficult, and then options will be given. A goes with P, B goes with R, Q goes with C or something like that. So you will have to select one of the options. So match the following type of questions also come sometimes in the NEET exam. Alright, so students have started answering. Jayashree, the homework questions answer, right, is there in the Telegram channel. I have posted the solution of the homework question. So please download that PDF, join the Telegram channel. Link is there in the description box. Goldstein, Chadwick is neutron, J.J. Thomson is very common. Yes. So Thomson was the guy who discovered electron in 1897. That's really, really far away. Okay, long time back. Rutherford was the person who discovered proton in his famous gold foil experiment. So I have my own version of this gold foil experiment. I think Rutherford wanted to gift something to his wife. He bought a lot of gold, and then I think he fought with his wife one day, and then he's like, why to give my wife this golden ornaments? So he's like, okay, let me make a gold foil and let me pass alpha particles. So he was a legend, and then he saw one new particle being discovered, and that was proton. So that's what legends say, but I don't know what is the reality, guys. This is what the legend story is. Okay, so he put gold to very nice use for the sake of humanity. So guys, I don't know whether you guys are going to do something like that crazy. I don't know. Okay, then you also had Chadwick, who basically discovered neutrons. Okay, so neutrons was discovered by Chadwick in the year 1932. That was the last discovered particle in the three of them. So electron first, then comes proton, then comes your neutron. Now the first theory, which is very significant, is Dalton's theory. But Dalton's theory did not give a very good picture of atom, but nevertheless you should know about it. So what Dalton said is that, let's go through this one by one. All matter is made up of tiny indivisible particles. They are called as basically atoms. So atoms are nothing but tiny indivisible particles. Obviously this is wrong, we know that. Actually speaking, this is wrong. You can divide an atom. It's made of small furthermore particles. All atoms of specific element are identical in mass, size, etc. and properties. However, atoms of different elements are having different properties. So all atoms of a specific element have identical properties. All atoms of different elements have different properties. Makes sense. All the water molecules are very similar. All the molecules of gold are going to be very similar. All the molecules of hydrogen gas will be similar. And you can see hydrogen will be different from water molecule. So that's what he said. That is perfect. So we give him marks for that. It's like we are the teacher over here and this is a student who is writing something. And we are like, no, this is wrong. I know this is wrong. Okay, this is fine. You get +1 marks. So you feel happy about it, right? Giving marks as a teacher now or cutting marks as a teacher. Okay, so no points here. First point over here. Okay, great. Atoms can neither be created nor destroyed. Furthermore, atom cannot be divided into smaller particles. This is wrong, guys. Atom cannot be divided is wrong, and atom cannot be created, destroyed. This is wrong. We know that in nuclear explosions, etc., mass can be created, mass can be destroyed. Nucleus can be created, and all those sorts of things can happen. So that's why this is also partially wrong, saying that atoms cannot be destroyed, and also you cannot further divide it into smaller particles. So 0 marks for this point. Are you happy? As a teacher, giving 0 marks over here, 0 marks over here, 1 mark over here, guys. You being the evil teacher now. Yes, friends gamer, you can. Atoms of different elements can combine with each other to form whole number ratios in order to form compounds. That also makes sense. Like if you want to make a water molecule, then 2 hydrogens mix with 1 oxygen. It's not like 1 hydrogen and half a hydrogen mixes with 3/4 of oxygen, or half a hydrogen mixes with 1/4 of oxygen to give, some compound. No, whole numbers only. So this is fine. We give him full credit, full points for this particular thing. They can mix in fixed whole numbers. So this is perfectly fine. Atoms can be rearranged, combined and separated in chemical reactions. That is also correct. Like whenever chemical reactions occur, the atoms can separate, they can combine with another molecule, another atom to form newer compounds, or the compounds can be broken down. So this is also correct, and you can give marks for this. But these are only few things about the atom. There were so many other things which were not explained by Dalton. Okay, like the flow of or the conduction of electricity, or even the gold leaf experiment, or the hydrogen spectra and Zeeman effect, and so many other things which could not be explained via Dalton's theory. So that's when the next theory comes. But before that, let's see how many of you are paying attention. All atoms of a given element have identical dash, including identical dash. Put up the answer in the chat box. Savanan, nice to see you, bacha, and hopefully this is not your last. You keep on attending the classes till the end, because this is a continued series on the NEET English channel, guys, for all of you, and you should call your friends too. This is an exclusive NEET English channel. We already have a J English channel. There is a NEET English channel out here. So Pandya saying A, Pravina saying A, Ashika saying A, Sampath saying A, Morpati saying A, everybody saying A. Very nice. Looks like you guys are all very attentive students. Very good, guys. Keep it up. A lot of questions theory are going to come up. Very nice. I want to see this. I want to see this till the end of the class. Very good. Correct answer is properties and mass. They have all the atoms of a given element like gold, silver, iron, or anything, even calcium or hydrogen. They have same properties and same mass. Weight, volume, nah, they can be different weight. I mean, you can have more gold here, you can have less iron there. No. Volume and properties, no. Temperature and pressure, how is that true? Properties and mass. Okay, now talking about the different atomic models. So we are going to first go towards the Thomson's model, and then we are going to go towards the Rutherford's model. Okay, before going to the Thomson's model, one thing I want to mention is that long time back people knew that there are conductors. What is a conductor, guys? Bus conductor? What is a conductor? Bus conductor? No, electrical conductor. What is the meaning of electrical conductor? It conducts. What does it conduct? Electricity. What does it mean by conducting electricity? When I say electricity is being conducted or electricity is flowing, that means there is some current flowing in it. When current is flowing, it's nothing but the flow of charges. And the conventional direction of the current is the flow of positive charges. The direction of the flow of the positive charges. But it was proved experimentally by many people that actually when current flows, the positive charges do not move. So the positive charges do not move, but it is the negative charges. It is the negative charges which actually move. And the negative charges move in this direction. The negative charges move in this direction. The positive charges are basically going to be at rest. So if negative charges go here, it's as good as saying positive charges are going there. If negative goes here, it's as good as positive going there. Is that understood? Everybody clear about this? Negative charges go here. So actually it's as good as saying positiveness is going the other way around. So they knew this, that the flow of current is because of the negative charges in it. They just didn't know that it was electron. They just knew about a concept called as negative charge. They just didn't know that it was an electron. Is that also understood? Very nice. Now, if this much is clear, in your head, understand one more thing, that if electrons can move very easily, it's because of the fact, or the negative charges can move easily, it's because of the fact that they are loosely tied. So the negative charges are able to flow because they are loose, they are free. They are free or they are loose. That's why they are able to move easily in that conductor. That positiveness is not able to move so easily. So it is like a fixed thing. That gave Thomson an idea. Oh, maybe atom is like a watermelon. Like in this very famous movie, Three Idiots. How many of you have seen that movie, Three Idiots? Where, the principal of the college, or basically the dean of the college, Bhuman Hirani, who is playing that role, he says, life is like an anda. Life is like an egg. Right? So you know what Thomson said? Thomson was like, life is not like an anda. Atom is like a watermelon. Atom is like a watermelon. That's what Thomson said. You cannot forget this statement now. Okay, great. Awesome. So many of you have seen that. So in that watermelon, the red part, everybody has tasted watermelon 100%. There are seeds which you just spit it out, and you might have heard weird stories as a kid. If you eat those seeds, then plant will grow in your stomach. Watermelon plant will grow in your stomach. And people used to get scared. But now you guys are biology students. You're going to become doctors. This is all not true. This is just chumma there to scare you. Okay? Anyways. So you have those seeds. Those seeds can be easily plucked out. And they can move here and there. So he thought the negative charges are like those seeds. The red part is positive charge. Red part positive. That seed is negative. Red part positive. Seed is negative. Those seeds can easily be plucked out and they can flow. That allows the conduction of electricity. It is also called as pudding model, plum pudding model, where those cherries or those teeny mini things are electrons and the rest of the cake is your positive charge. He also said that the amount of positive charge is distributed throughout that atom. It is spread. It's like a paste spread everywhere. It's like a gel or a paste spread everywhere. But the total positiveness is the total negative charge. That's why every atom is neutral. Every atom is neutral because the amount of positive is equal to the amount of negative. That's what he proposed. I hope this is clear. Everyone? Yes. Chumma means, what is the meaning of chumma? There are many meanings of chumma, but the meaning of chumma that I wanted to say, or I am trying to say, everybody knows. Come on guys, what is the meaning of chumma? Come on, all the Tamilians, all the Telugu people, all the students from Bangalore, Kerala should know this. Yeah, nothing. Very good. Nothing. Awesome. Great. Kiss. Sampath, which movies are you watching, man? Okay, nothing important. Very good. Looks like you guys know some definitions. Great. So that is nothing but your Thomson's atomic model. Positive equal to negative. Electrons can flow easily. The positiveness is spread everywhere. The teeny mini particles are electrons. That was Thomson's model. Then, in this Thomson's model, there were some problems. See, Thomson was a great guy. Thomson said, life is like an anda. He said, atom is like an watermelon. But there was a problem in his theory. What was the problem in his theory, guys? The problem was he could not explain why are the spectral lines coming, just like it happens when teacher is asking Viva questions. Explain why there are spectral lines in the form of series as in the case of hydrogen atom. Thomson was like, I don't know, ma'am. Sorry, ma'am. Then teacher was like, it could not even account for the scattering of alpha particles when Rutherford used the gold which was meant for his wife. Instead, he used it in the gold foil experiment. Why is it not able to account? Thomson was like, sorry ma'am, I can't say, I don't know. So then gone. Thomson's theory, tata, bye. Okay, understood? Very good. Is that clear? These were the limitations. What were these? Limitations of Thomson's model. You should know both these things. So one, it could not explain the origin of spectral lines. Second, it could not explain the origin or why scattering of alpha particles happens in the Rutherford experiment. So who explained? Like it happens in every Viva. There is one student saying, sorry ma'am, I don't know ma'am, I'm so sorry ma'am, I don't know. Then others, ma'am, miss, I know. So who was that guy? That was Rutherford. He came and he's like, I know, I'll explain. So Rutherford did an experiment, and let's see what that is. So before that, let me show. This was the model. This was a model. This is like a cake or watermelon of Thomson. These teeny mini dots are electrons. If what Thomson said was true, if you pass alpha particles, what is alpha particles? Positively charged helium nucleus, right? Doubly ionized helium nucleus. Then it just flows through it. There is no deflection. There is no turning, because overall it is neutral. Overall it is neutral. Wherever it is positive, that much negative. So it's basically a neutral body. So there is no deflection as such. But this is not what was found. This is not what was found. This is not true. This is not what happens. Actually what happens is this. This is basically now the Rutherford's model. Let's have a look. This is exactly how an atom's nucleus looks like. So this is a nucleus. You can see it's made up of a lot of protons and neutrons out there. It's heavily positively charged. And then the moment you turn on alpha particles, this is the gold foil. You can see this is the gold foil. See the way alpha particles are getting deflected. Do you see the way alpha particles are like, oh my god, what is this? What is this? This is like the principal of your school. These are the kids. The kids who are going from the side, they are going aram se, chill madi. But these people who are going near the principal, oh my god, principal is coming, run, 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 run. See this? This kid ran away, this kid ran away, this kid ran away, this kid ran away. That kid which will go directly towards that nucleus, sometimes it will happen, it will take a U-turn. Very rarely it will happen by chance, okay? It will almost take like a U-turn. So most of the alpha particles will go undeviated. Some alpha particles will get deviated slowly or slightly. Very few alpha particles will get deviated by a lot of amount. This proved that there is something heavily concentrated at the center of the atom. This means that there is something really heavy and very nice positive charges there, which is deflecting all these alpha particles. Very few alpha particles go head on, bang onto it. That's why they go U-turn. But otherwise, most of the atom is empty. That's why all these alpha particles are able to cross this atom. So you can see this as a whole. These are the nucleus. These are the nucleus. Most of these violet darts are able to pass, but very few of these violet darts are basically deflecting by small amounts. I hope this is clear. Exact example, Prem. Is alpha particle positive or negative? It is positive, MS Doctor. It's basically helium. Pluck those electrons. What does the helium have? 2 protons, 2 neutrons and 2 electrons. Take away the 2 electrons. What will be left? 2 positive charges. That's an alpha particle. 2 positive charges basically with 2 neutrons. That's all. I hope that is clear, guys. Okay. Susanta, I'll tell you one simple thing. There is an option where you can take the negative. Just take the negative of this. That's it. It's simple. Just invite those images. That's it. Everything will become invited. You can definitely make notes or you can take printouts. Okay. So now that you know what is Rutherford's experiment. So there is alpha particles, gold foil over here. It will pass. Most of it will pass. Some of them will get deflected by small amount. Very few will get deflected by a large amount. From that, he was able to conclude most of the atom is basically, empty. The whole of the positive charge is almost the entire mass is concentrated in a small central core. So most of the positive charge, most of the mass is concentrated in a small region. Most of it is empty, right? That is one of the conclusion. Next conclusion, the nucleus is surrounded by electrons. You can see these electrons are surrounding these, nucleus. These electrons are surrounding the nucleus, and these electrons are spread in the remaining part, leaving plenty of empty space over there. There is a lot of empty space. That's why those alpha particles were able to easily pass through the atom. Are everybody able to visualize this? Are you able to get the feel of an atom now? Next important thing is that he also proposed that, although I have not written it down over here, these electrons revolve because of the centripetal force, because of the electrostatic force or the centripetal force. These electrons are able to revolve around the nucleus. Whenever things go round what happens? There should be some force which provides the centripetal force. In this case, it's the electrical force. Negative, positive, attract. So the attractive force of electrostatics provides the centripetal force for its revolution, around that nucleus. That's what he said. He did not say anything about the orbits or anything. He just said the electrons just go around the nucleus. That's all. And the force is given by the attractive force between the electron and the nucleus. But even Rutherford failed. So first student was like, sorry miss. Then the other student, who was the other student? Rutherford. He was like, ma'am, miss, I know the answer. He proposed something, but even this failed. Even this theory failed. You know why? Because he was able to say that, okay, electrons revolve around the nucleus. Then the problem with that is, when the electrons revolve, because they are going in circular path, they are accelerating. Yes or no? Like Prem Kumar said, v square by r is the acceleration. Now because it is accelerating, it was also said by other theories, Lorentz and Maxwell's theory, which said that whenever a charge accelerates, it should emit radiation. Whenever a charge accelerates, it should emit radiation. That means it loses energy. That means as the electron revolves, it loses energy. It becomes weak, and it should fall into the nucleus. But that's not what happens. So according to the theory, because it is accelerated towards the center, then this should emit radiation energy continuously. Therefore, a revolving electron should emit energy, and hence the radius of the path should keep on going, decreasing, and ultimately it should fall into the nucleus. How can an electron fall into the nucleus? If electron falls into the nucleus, explosion, big explosion, everything will be destroyed. It's like a nuclear explosion, guys. That should not happen. It should not happen. That is very, very dangerous. If an electron falls into the nucleus, gone. That is not possible. So he was not able to explain that. Number two, Rutherford's atomic model, if it is true, then the electron can revolve in orbits of any possible radius. He did not say anything about the orbits. Yes, he did not say anything about the orbits. What about the orbits? So all possible radii are possible. Hence it should emit continuous energy spectrum. But how does hydrogen possess line spectrum? If it can have any kinds of orbits, then the energy which will come out of it will also be any amount. If energy also can be any amount, the spectrum which comes, we'll be talking about it, will be continuous. But actually it was found the spectrum is not continuous. It is like a line, distinct spectrum. Why does that happen? Rutherford did not have the answer. That is the limitation. Okay, so let's see how many of you are able to answer this question. Which of the following is not a part of J.J. Thomson's atomic model? Which of the following is not a part of J.J. Thomson's atomic model? All the new students who are joining in, make sure you hit the subscribe button and also hit the like button, guys, because you will otherwise not get notifications, and that's how YouTube algorithm works. You'll miss the classes. You'll be like, I know this class is at 5. You'll forget it. So make sure you stay subscribed and also hit like button. Both things are mandatory and necessary so that you do not miss any classes and also show your support to the channel. Okay, great. And if you have missed any part, make sure you go back a little bit and come back. What is the line spectrum, Leaf? Yes, I'm going to come to that. Spectrum, we are going to talk about it in detail. But for now, just remember the word line spectrum and continuous spectrum. It does not explain why line spectrum happens. According to that, because any radius is possible, any continuous energy is possible, so you will get a continuous spectrum. But that is not true. D for doctor? Very good. Which of the following is not a part of Thomson's model? What did Thomson say? Life is like an anda? No, he said atom is like a watermelon. Watermelon means completely full. No, it's not empty. So he said atom is hollow sphere. No, he said atom is completely full. So that is not a part of Thomson's model. Atom is a gel of positive charge. Yes, the red part of the watermelon is the gel of positive charge. Electrons help in conduction. Yes. Atoms have embedded negative charges. Those are the seeds. So these are the seeds. These are the seeds of the watermelon. These are the seeds of the watermelon. Okay, and this is atom is a gel of positive charge. So that is the red red part of the watermelon. Electrons help in conduction of electricity. That's something which I told you already. Next question. Rutherford alpha particle experiment shows that most of the alpha particles pass through unscattered, whereas few of them are scattered through large angles. From this information, what does it tell you about the atom? What does it tell about the atom? Atom is hollow, the whole mass is concentrated at the center, or nucleus is positively charged, or all of the above. Yes. Anda means egg. Okay, MS Doctor. Anda means egg. Okay. The white egg. Yeah. Okay. Great. D. D for doctor also. D for Ames Delhi, right? D also is Ames Delhi, guys. Yes, yes. Very good. Very good. Very good. Proud bacha. Super duper. Very good. Amazing. All of them. Because all of them, most of them are passing unscattered. That means empty space is there, or else they would deviate. Very few are deviating by a large amount. That's because nucleus is repelling them, and it is only there at some locations. So that's why all the mass is concentrated at a very small space, which is called as the nucleus of that atom. Very nice. Now let's go to Bohr's model. Now comes Dawn. First student said, sorry ma'am, I don't know the answer. Next student said, ma'am, I know the answer. Then he also got one tight slap. He was also not able to answer. Then comes the Dawn. Then comes the Dawn. Thalaiva comes like this. Who is the Thalaiva? Bohr. Who is the Thalaiva? Bohr. And he's like, listen, I will tell you guys how this question has to be answered. And Thalaiva is like, Bohr is like, listen, there are some things which I discovered. There are certain things which you guys are doing wrong. I will tell you what is the correct thing. Okay. So, postulate 1, that means his proposition was, electron in an atom could revolve in certain orbits only without emission of radiation. Remember, whenever charges accelerate, they basically emit radiation. But there is a but. And what is that but? The but is, if those orbits are basically stable, or generally called as stationary orbits. Stationary not because it is not revolving, stationary because it is stable, it is stationary energy wise, then it will not emit any radiation. Not emit radiation. Only in those special orbits. Why only in those special orbits? That's none of us concern. Don't worry about it. That goes into quantum mechanics. But he said that there are only fixed orbits. Meaning, think of it this way. If Bohr's postulate were not obeyed, then the electron can revolve here also, 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 here also. So it's like a continuous value of radius that it can revolve. But Bohr said, no, this is not true. Actually, what happens if this is the nucleus? Electron can revolve here, nothing in between, here, and then here. So only fixed number of orbits are there. Not any random orbit. Here it is not allowed. Here it is not allowed. Here it is not allowed. So that's what is being proposed. Everybody clear? Everyone? Understood? Let's move on to the next postulate. The next postulate is, in these special orbits, in these stationary orbits, in these stable orbits, the angular momentum. Now you will be like, sir, what the hell is angular momentum? I forgot. Just quickly revise. Okay, I'll revise. If you take, teacher would have thrown sometimes a duster on your face. Has anybody got that? Duster, pen, chalk. Chalk, I think, very common. The session started, Iman, at 5 o'clock. Yeah? So, thrown a duster on your face. Duster or chalk has some mass. It also has some speed. So, more the mass, more the speed, more the momentum. That's it. On your face, nice slap you will get. Yeah? So, if it was duster, more mass, more momentum, you will get hit badly. That is linear momentum. Momentum of translation, that is linear momentum. Correct, very good. Now imagine you take the duster or the chalk duster or that chalk, you hold it like this. You hold that duster like this and you hit it like this on somebody. You take it like this and hit it. Do you see there is momentum and it is at a distance? If I hold it here and I hit it on somebody's face, no, not much of impact. But if I hold that same mass over here, large distance, you will see large impact. Large distance, large momentum, large impact. So that is angular momentum. I am showing that momentum at an angle. That's angular momentum, guys. That's R into momentum. That is angular momentum. Clear? Pain is also more. Very good, Kanista. Very good. So that is angular momentum. So angular momentum is nothing but R cross P. R is distance, P is linear momentum. You can also write it as R into M into V, which is also MVR. One and the same thing, guys. MVR. That is NH by 2 pi. What is H? Planck's constant. Last lecture I have told you. 6.6 10 to the power minus 34. Right? In SI units. That's the Planck's constant. 2 pi. Pi is 3.14. What is N? N is basically called as your principal quantum number. What is it called? Principal quantum number. Like the electrons which revolve, they revolve in shells. There is the first shell is called K. The next orbit is called L. The next orbit is called M shell. The next orbit, or where the electron can revolve, is called as the N shell. For K shell, the principal quantum number N is equal to 1. The next shell, it is 2. Next shell, it is 3. Next shell, it is 4. And so on and so forth. You can use the remaining alphabets. K, L, M, N. So my name is Captain Shreyas Bacha here, right? People call me Captain or just Capto. Yeah, Shreyas. Yep. Very good. He said angular momentum is NH by 2 pi. That's it. Whenever it is NH by 2 pi, okay. You are not NH by 2 pi, gone. N is any integer. 1, 2, 3, 4, get on the dance floor. You know? So 1, 2, 3, 4. Only integers. Don't put 1.1, 1.3, 1.4. No, not allowed. Alright. Moving next. Bohr's model, third postulate, guys. Okay. We now know electrons go in orbits, fixed orbits, no radiation of energy. And in these orbits, angular momentum is NH by 2 pi. Now what happens when the electron goes from one orbit to another orbit? It gets excited or de-excited, excited or de-excited. What happens then? Yeah, many orbits are there, GV, but not all orbits will have electrons. It depends on the atomic structure or the configuration. What is the atomic number? So smaller atoms, few shells only might be filled. As you go big atoms, then more and more shells will be filled. Okay? But even the largest of the largest elements in the periodic table, hardly some 4 or 5 orbits, that's all. Okay, now what happens when an electron shifts the orbit? How can it shift the orbit? I'll tell you. Imagine it is in some shell. It could be, let's say for example, shell number L, and this is, let's say, shell number M. Let's say this is shell number K. As you go to higher shells, K, L, M, N, energy will also go up. What happens? Energy of the electron also increases as the orbit increases, radius increases. Imagine that there is an electron over here. Imagine that there is an electron over here, and there are two possibilities now. Electron can get excited, electron can get de-excited. If an electron gets excited, that means it has to go over here. It gets excited. If it gets excited and it goes over here, tell me one thing, should you give energy or should you take away energy? If you are going to, excellent. Let's say this electron loses interest, demotivated. It loses interest, it gets de-excited. This is de-excited. If it gets de-excited, it is going to lower energy. When it lowers its energy, it will release something. Like when you get demotivated, what happens? When you get demotivated, what do you release, guys? Frustration, right? Anger. You become angry. Same way, when an electron becomes de-excited, it becomes frustrated, it becomes angry, it releases photon. It releases photon. Okay, I hope this is clear. This will basically release a photon. Now, what you should understand, that whatever is the energy of the photon which is absorbed or released, energy of the photon which is absorbed or released exactly matches the energy difference between the two shells. So, if the photon gave 5 joules of energy, example, then the energy difference between these two shells will be 5 joules. If the energy difference here is 3 electron volt, when the electron jumps over here from this orbit to this orbit, a photon of how many electron volt? 3 electron volt will come out. Understood, everybody? So that is the reason why I say that the energy difference between the orbit is equal to energy of the photon, is the energy of the photon. So energy difference could be E1 or something, En1 minus En2. En1 minus En2 is energy of the photon, which is just hf. What is f? F is the frequency. F is the frequency of the light which comes out of it, or the frequency of that photon. Using this only you get this. So usually some books use nu, but I do not use that symbol nu because it is confusing with velocity. So I'm going to use the symbol f for frequency. In chemistry, nu is used because speed is not there in chemistry most of the times. But in physics, nu often resembles speed v. That's why we use the symbol f in physics. Everybody fine till this point? Okay. If you are in NEET AI Live, then don't buy test series, bacha. It is already a part of your curriculum, Vignesh. Okay, so it will be done. So don't buy the test series. Test series is only for those students who are not a part of Vedantu as of now. Thank you, Sarvana. J Advanced test. Oh my God, is it? Oh my God, oh my God. Okay, I will go live after this class for J Advanced. Okay, bacha log. All right, moving on. That is scary. I mean, 4th of June. Somebody just make a video, yeah, of me right now and just post it and tag me on Instagram and share it across. So guys, J Advance 4th of June, the dates have been announced. Okay, I might have to check it officially, but that's what the students are saying. So if there is a JEE aspirant, please make sure that you share this message and probably tag me on Instagram as well. Okay, thank you guys. Okay, now what about the radius and the speed and the energy? Radius and the energy. Thank you, Himanshi. That's my whole motto, guys. So when I came on this channel, the only reason was to make things very clear, to make things interesting for all the students. So guys, I don't want to teach physics. Trust me on this. I want you to enjoy physics. The moment I start teaching physics, then you will not enjoy it, you will not learn it, you will not score marks. So here I am there to make you fall in love with physics and help you get that required percentage, required marks in boards, in NEET exam, so that you become successful doctors. That's the only purpose of me on this channel. Physics you can learn from anywhere, but here I am making sure that you become doctors. That is a bigger purpose why I am here. Now, how do I calculate this radius? How do I calculate this speed? How do I calculate the energy? There are formulas, but what is the principle, or what is the theory behind it? What is the derivation behind it? We don't have to go too much in detail. Just have a look at how things are done, guys. Okay, observe. See, electron is going round. Electron is going round around the nucleus. The nucleus is positively charged. Okay. How much charge is there in the nucleus? How much charge is there in the nucleus? How much ever protons are there, that much charge. Because neutrons don't have any charge, right? Only the protons have charge. Okay. How many protons are there? As many atomic number. Whatever is the atomic number, correct? If it's hydrogen, it's 1. If it's oxygen, then it is different. If it is helium, it is different. If it is iron, it is different. So it is completely based on the atomic number. Very good. What is the atomic number symbol? Z. Z is the symbol. So can I not say the charge on the nucleus? Charge on nucleus. The charge on nucleus is basically number of protons multiplied by the charge of a proton, The number of protons is Z, the charge of a proton is E. This electron has a charge of negative E, so that's why this proton, this electron will attract each other. So definitely there will be an electrostatic attractive force. This is the force of electrostatics. This is the force of electrostatics. This force of electrostatics, how much will it be? K, your Coulomb's constant, into Q1 Q2 into Q1 Q2 divided by distance. Distance is also the radius. Distance is also the radius square, and this force will be by Newton's law, because it is going in circular path, because it is going in circular path, because it is doing uniform circular motion. Shouldn't there be centripetal acceleration? Shouldn't there be centripetal acceleration? So force is mass into acceleration, guys. Force is mass into acceleration, my dear students. Very good, very good. Now what I'm going to do, K is nothing but 1 by 4 pi epsilon naught. Q1 is ZE, Q2 is nothing but E, magnitude wise only. I'm just taking the magnitude of the forces, divided by R square, is equal to mass of the electron, is equal to mass of the electron. Centripetal acceleration is V square by R, is equal to V square by R. Everybody with me? This is equation number 1. This is equation number 1. The second equation, you get it from the Bohr's previous postulate, which I just gave it to you over here. Angular momentum is nh by 2 pi. Angular momentum is nh by 2 pi. So mvr is nh by 2 pi. This is your second equation. Now solving equation 1 and 2, you get the value of velocity and you get the value of radius. Solving these two, you get the value of velocity and radius. Don't worry about it. It is very simple to do it even at home. I want you to try it out just for boards, but for our NEET perspective, that derivation is also not important. When you solve it, what you get is very important. The final result. Now you might have seen the final result in many books given like this, and I have seen many students trying to by heart this. How many of you have tried to by heart this and successfully failed? How many of you have tried to by heart this and successfully failed? Okay, so Bhadra, what has happened over here? This was force. Force is mass into acceleration. Force is mass into acceleration. Force, remember Coulomb's law. K, charge 1, charge 2 by R square. Charge 1, ZE. Charge 2, electron, so E. Distance is R, I have put it. Acceleration, circular motion, V square by R. That's it. That is equation 1. Another equation is angular momentum. MVR is nh by 2 pi. That's all. This is just angular momentum equation. From where did I get it? From here. MVR is nh by 2 pi. Bohr's second postulate. This is nothing but angular momentum. Is that okay, Bhadra? Yes, many of you? Okay, so this has to be solved. I mean, you can solve it easily. Take the value of V from here, put it here, eliminate V. So V and V, you will just get R. Then put R from here, you will get V. So it's just simultaneously solving it. So guys, you don't have to by heart it. Aren't you relieved? Aren't you happy that you don't have to by heart this? That is like the most stupid thing that anybody can do is actually sitting and by heart, and many teachers actually tell that please by heart this, by heart this. No, you don't need this. Take the history of NEET, take the history of J, take history of J Advanced also, most toughest exam. Over there also they don't ask such questions. What they ask you instead is what is it proportional to? That is very important. The radius is proportional to n square by z. N square by z. That's all you should remember. And that constant of proportionality in this case happens to be 0.53, and then n square over here by z Armstrong. This is what you are supposed to remember. That's all. That it is proportional to n. N is quantum number, principal quantum number. Z is atomic number. This is in Armstrong. That's all. Got it? And also you just need to know this. Velocity is proportional to z and inversely proportional to n. That's all you need to remember. Nothing else is needed for solving NEET problems or even board problems. If they ask you, if they ask you for this n, this was the radius, For that n, what is the radius? You are just going to use the proportionality constant. We'll see some problems based on that. Okay, great. Now that you have understood it, now you'll be like, sir, what about the energy? Well, we'll talk about the energy also. When we see that there is an electron, going around in an orbit around the nucleus, what all kinds of energy can you think of? Put it up in the chat box. When I say the energy of an electron, when I say energy of an electron in orbit, what kinds of energy do you think are there with it? Yes, Sarvana, I definitely know, bacha. I teach with him on J English channel, right? Yeah. What are the different kinds of energy? Yes, Ashika. You can remember the constant, but generally they don't give you such questions on constants. Kinetic energy. Centripetal, no. Centripetal is not a form of energy. Centripetal is a force or acceleration. Yes, Malvika, very good. Kinetic and potential energy. There is nothing called as centripetal, guys. Please understand that centripetal is not a form of energy. Centripetal force is there. Kinetic, because it is moving. So motional energy means kinetic energy. Because this is a charge, what will happen whenever there are two charges? Electrical potential energy. So hence, there is kinetic energy because of the motion, and also there is potential energy. Kinetic energy will be half mv square, correct? And potential energy will be 1 by 4 pi epsilon naught q1 q2 by r. This is the formula for potential energy. When you substitute everything and you add them, this is what you get. The energy in the nth orbit comes out to be minus 13.6. Here you get z square, and downstairs you get n square, but the answer is in electron volt. This is the formula for the total energy of the electron in the nth orbit. This is the nth orbit. I hope this is clear, guys. Everyone with me? Clear? Okay, this is the formula. 13.6 z square by n square. Why that negative sign? I'll come to that in a bit. For now, just remember there is a negative 13.6 as a constant. Also, one more crucial thing that you should remember is that this kinetic energy of that electron is exactly the negative of this total energy. It's exactly the negative of this total energy, number one. And number two, the potential energy that you get is 2 times of the total energy of that electron. These are also some of the crucial things that you should know regarding kinetic or potential. So if you know total, you can find kinetic or you can find potential. You can find both of them using this. And this formula is right over here. Okay, double, and this is just negative of this. Very important. Kinetic energy is negative of total. Potential is double of total energy. These are the important formulas that you should know. Okay. Now, why is it negative? We'll come to that. Why is that energy negative? See, actually what happens is when you draw a chart or a graph of the energy of that electron, for different shells, this is how it's going to look like. This is basically your K shell, then you're going to have your L shell, then you're going to have your M shell, then you're going to have your N shell, and so on and so forth. Many shells will be there, and the last shell will come over here. What is it called? I'll come to it. The K shell has a principal quantum number n is equal to 1. This is n is equal to 2. This is n is equal to 3. This is n is equal to 4. What is the last number that you can get, guys? 1, 2, 3, 4, etc. What is the last number you can get? Let's see. Guys, think of the largest number possible. Everybody knows what is the largest number possible? What is the largest number possible, guys? K, L, M, N. 1, 2, 3, 4. What is the largest number? Infinity, right? Very good, Madhumita, Sandhya, Leaf. Very good, Prem. Excellent aim, MS Doctor. Very good, Lydia. Very nice, Ashika. Very nice, Dhanuraj. Very good, Shagun. Excellent, my warriors, Linus is Sumita, very good. So here n tends to infinity. Now when n is infinity, you'll be like, what is this, sir? New orbit is there. Actually, you know what it is? It's so far, it's like useless. It's like a useless electron. The atom will be like, what the hell, man, you are so far. You might as well not stay with me. It's as good as you're not there. It's like saying that, you know, you are not inside the house, you are somewhere really far, you are really far. It's as good as you're not having any kind of relationship, or you do not have any kind of talks, you do not have any kind of feelings, or you do not have any kinds of relations in the house. You're just really far away. That's it. You're not bound anymore. You're not bound anymore. So this is a free state. What is it called? Free state. It's free. Electron is free. This energy, when it is free, is zero. Here, the energy at infinity principal quantum number is zero. This is the highest value of energy. So obviously anything below zero will be negative. So all these will be negative energies. Negative energies. In these cases, it is bound to the nucleus. It is bound to the nucleus. Here, it is not bound. It is completely free. That's when n is infinity. Is that clear? So that's why it is negative. If it is more negative, it is more bound. So keep this in mind. More negative means more bound to what? To the nucleus. It is very much attached to it. So if it is more negative, no, don't get scared. It's good only. So more the negativeness, more is that attachment towards the nucleus. Yes, but only fixed orbitals. Yes, only for fixed values you can get these energies. You cannot have random values of energies. That's why these lines are there, guys. That's why these lines are there. Any trick to memorize the energy values of the bands? No, Prem Kumar. I mean, you don't have to remember all the values. Just remember 13.6 and 10.2, 3.4 and all of that. The first 2-3 values more than sufficient. Don't sit and by heart for KLMN till Z. No, don't do that. Just first 3 values more than sufficient. Okay? Everybody with me on this? So that too for hydrogen, because see, if it is helium or lithium, then again the energy values will change. Okay, so more negative energy, Sandhya, more negative energy, very important, more negative energy, meaning of out of minus 13.6 and minus 10.2, who is more attached? Who is more attached? Come on, put it up in the chat box. Come on, put it up in the chat box. Who is more attached, guys, to the nucleus? Who is more attached out of these two? Obviously, this has more attachment. This one is less bound. This one is less bound. Is that clear? Very nice. This is what I mean by it. This is more negative, this is less negative. So this will be somewhere here, this will be here. So as you go up, the negativeness will reduce, slowly it becomes zero. Very nice. Now, if I have some kind of electron over here and I send it to infinity, if I have some electron over here and I send it to infinity, the energy required to send that electron to the highest state, that means to make it free, the energy required to free the electron, what is that energy called? What is that energy called? Okay, if you don't remember the name, it's okay. Think like this. If the electron is plucked out, what will happen? The electron is plucked out. What will happen to the atom? It's deficient of an electron. What is that atom now called? It is an ion. It is now an ion, right? It's become an ion, right? So the energy required to make it an ion will be ionization energy. It will be called as the ionization energy. That's all. So imagine if over here the energy of the electron was minus 13.6. Just imagine. If I pluck out that electron and bring it here, how much energy do I have to give? Put up the answer in the chat box. If I pluck out that electron which had minus 13.6 electron volt and bring it to 0, how much energy do I have to give? How much energy do I have to give to that electron to make it free? How much energy do I have to give? From minus 13.6 to 0. So plus 13.6. Exactly. Exactly. So that ionization energy will be basically negative of that energy in that orbit. So if it was minus 13.6, it's minus of that. So it becomes plus because that's the energy which you give it. Very nice. I hope this is clear. Okay, so this is again one crazy formula. Are you going to sit and by heart this? Are you going to sit and by heart this, or are you going to remember this formula? Okay, no, right? You're not going to remember this. This is just there in your books. This is just to scare the kids in the night, okay, or even during the day. This is the one which you're going to remember. Okay, this is the formula in electron volt. Keep this in mind. Okay, maybe we can solve some questions based on this. Come on, guys, get ready. In which of the following systems will the radius of the second orbit be minimum? Out of all the orbits, out of all the atoms, where do you think the radius of the second orbit will be minimum? The meaning of second orbit means KL, L shell, L shell. In the L shell, what is the value of n? N is equal to 2. Okay, why different atoms are given? Oh, their Z will be different. Acha. What has the radius got to do with Z? Think like this. Radius is proportional to n square by Z. N square by Z. N is it is inversely proportional. Z is below, R is on the top. So inverse relationship. So if denominator increases, radius will decrease. So who has the biggest Z? Who has the biggest Z? Obviously this one. So this is max value of Z, hence least value of radius. But if the question said maximum radius, then what will be the answer? Right now the answer is B, yes. But if the question said maximum, then what will be the answer? Think like that. Think like that. If the question was maximum radius, Z will be minimum. Z will be minimum. Very good, crazy followers. MS Dr. Madhumita, very good. Epic Queen Deva, very good, Shagun. Then the answer will be H atom, hydrogen atom, because that has Z is equal to 1. Very nice, guys. Moving on to the next question, guys. Very good, guys. You guys are thinking a lot and you guys are carrying it along. You're playing along with me. That's fabulous. This is how you have to attend the classes. Very good. Keep it up. I'm 100% seeing so many students acing NEET now. Keep it up. Calculate the principal quantum number for which the radius of the orbit of the electron in B3 plus would be equal to ground state electron of hydrogen atom. Okay, so this is not a part of the question. Just ignore this. Okay, let's try to solve the question, guys. First of all, okay, what is given is the radius of the orbit of the electron in B3 plus. In which radius? For which radius? I don't know that. So radius of the nth orbit in BE, okay, in B3 plus should be equal to the radius of the ground state. Ground means below, right? What is the least possible value? N is equal to 1. So the radius of the first orbit in hydrogen. The radius of the first orbit in hydrogen atom will be some constant, don't worry about it. And here, remember, always radius is a constant into n square by z. So over here for hydrogen, n is 1. So instead of n, you're going to put 1. For hydrogen, z is also 1. So just put 1 over here. For BE, what are you going to put, guys? First of all, put constant over here, and n value I do not know, so just put n. What is the value of z that you are going to put? What is the value of z that you are going to put? What is the value of z that you are going to put, guys? Come on. The value of z that you are going to put is 4, right? B has z is equal to 4. Very nice. Constant and constant cancels. Constant and constant cancels. So you just have n square by 4 is equal to 1 by 1 is just 1. So therefore I just have n square is equal to 4. So n is equal to 2, guys. N is equal to 2. That is the answer. Where is it? Option A. Excellent. Very good, Roshni. Very good. Very good, Madhumita. Very good. So many of you answered Z was 4. Very good, Sri, Sandhya. No, Sampad, it was not 3, it was 4. Excellent, guys. Wow, very good. So I think you are getting confidence now. Let's see if you can solve this question as well. The potential energy of an electron is this. Then what is the kinetic energy? You will be like, sir, you just told that this formula is not important. Yes, it is not important. Just read the question again. You will understand why it is not important. If potential energy is this much, what is the kinetic energy? Very good, Shagun. You answered it first. Very good. I think Shagun has answered the next question also correctly, really quickly. Very good. And let's see whether you guys are correct or wrong. What did I just tell you? Potential energy is 2 times of total energy. And kinetic energy is negative of total energy. What you do now? You just divide these two. Just divide these two because I want to find relationship between potential and kinetic. So potential energy by kinetic energy will be minus 2 by 1. That's it. So from this, what do I get? Kinetic energy will be minus 1 by 2 times potential energy. Now it is clearly mentioned what the potential energy is. It is minus E square by 4 pi epsilon naught R. Minus minus becomes plus. It will become E square. 4 2s are 8. 8 pi epsilon naught R. That is your kinetic energy. Where is that option? Where is that option? Option B. Excellent. Not C. That minus sign gets cancelled. If you make a calculation mistake, you will get minus and also minus negative mark also. B for Bombay. Very good. Divide by 2, multiply by minus. Excellent, Sumita. Yes, that's how it is. Very good, NH, Sandhya, Vijay, Velsi, Madhumita, NH, Deva. Very good, GV. Very good. Very good, Sarah. Very good, Vijay. Very good, Kanan, Epic Queen. Very good, Sampath. Very good, MS Doctor. Excellent, bacha log. Okay, now let's go to the last and final few parts, and that is basically the hydrogen spectra. So this is one of the important things about Bohr's model, that it was able to talk about the spectrum of hydrogen and many such elements. Now, what is this spectrum? The spectrum is like a signature of an atom. Like you guys have a signature and it is very unique, right? Unless somebody deliberately tries to copy it, it's a unique signature. Same way, every element has its own sign. If you call hydrogen, it'll be like, hey, listen, this is my signature. If you call lithium, it has its own signature. If you call iron, it has its own signature. Now, what does this signature look like? You might be wondering. It is not like the sign that you are expecting. It is in the form of spectral lines. It is in the form of lines or colors which are very distinct or which are not continuous, but they are separate, they are discrete. Looks something like this. Looks something like this. You can see these lines over here. Something is missing over here. And you can see some lines over here as well. Some lines here as well. So these are the signatures. So I know you guys were thinking like, oh sir, there will be a nice signature over here. No, these are lines which are there or not there. This is called as a spectrum of line. Lines are there. Continuous, somebody was asking some time back, sir, what is the meaning of continuous and line spectrum? Continuous means it's continuously there from one point to the other. There is nothing missing, it's not in steps. This is line spectrum. You can see that. One line, second line, third line. If you take some other atom, these lines will be at different places. Number of lines could be also different. So for every element, these lines are different, differently placed, and it is unique. No two elements will have the same spectrum. Understood, guys? Every guys have copied their parent sign in childhood for leave. Yes, for getting leave, for report card especially. You know, report card, exactly. Like fingerprints also. Yes, very true. Yes, acing, I'll be doing semiconductor in just one session, but it will be a very big session. Are you ready for that? Pakka, you will be able to stay for 3 hours, everyone. Yes, crazy fellows, soon. But for now, at least concentrate on physics and chemistry. And for bio, as of now, if you want in Tamil, then you have the Tamil channel. Or if you want, the Hindi channel is also there. And if you also want a little bit of English and very little of Hindi, then you also have the biotonic channel. Yes, you will be able to stay. Acha, kya baat hai? Very good. Okay. Now, what is this spectrum dependent on? It's basically due to the electron transitions. Remember some time back, where did it go? Right over here. Yeah, see, an electron can absorb the photon and get excited, or it can release the photon and then it can get de-excited. So when a spectrum is formed because of absorption, what will it be called? Absorption spectrum. Obvious, right? Very simple. If a spectrum is formed because of photons, that means light is absorbed, that means the electrons get excited, that spectrum will be called as absorption spectrum. Correct? And if a spectrum is formed because photons are getting released, when will it get released? Because electrons are getting de-excited, then it will be called emission spectrum. It will be called emission spectrum. Okay, let's try this out. Okay, let's go to absorption and emission spectrum and see how this works again. Over here, just look over here. Here, do you see something is missing? Do you see things missing? That means what has happened, guys? That means what has happened? Absorption has happened. Absorption has happened. So definitely one can say that light photon was absorbed. Photon was absorbed, and because of that, the electron has gone to higher energy state. So the electron jumps and it gets excited. Very, very simple. That's why you can see missing lines. In the other case, do you see lines are only there at certain places? When will that happen? When will that happen? Like you can see over here, the electrons basically get de-excited. De-excited. That is going to release. What is it going to release, guys? It's going to release photons. What is it going to release? Photons. Dual nature was done in the first session only, Nidhi. The first session had dual nature. Okay? I think you have missed that. Please check it out. It was there somewhere in between. First part we did photons, then wave particle duality. Last part was photoelectric effect. Everyone fine? Now, the manner in which these transitions happen, they have certain names given to it. So there are series name. So if the electron jumps, de-excites from higher energy to the lowest energy, which is n is equal to 1, those lines are called Lyman series. What are they called? Lyman series. If the electron de-excites to n is equal to 2, those transitions which emit photons, those are called as Balmer series. If the electron jumps from higher energy states and gets stuck over here to n is equal to 3, then those photons which come out, they are in the Paschen series. If the electrons jump to n is equal to 4, then the photons which come out, the light which comes out, that belongs to Bracket series. How have these names been given? They have been named after the person discovering these series. Or who have made experiments to show these series. Lyman, Balmer, Paschen, Bracket. Let's see if we can answer this question. When I say the first line of Balmer series, from what to what transition am I referring to? First line of Balmer series, from what to what transition am I referring to? Let's see quickly if we can answer this. Yes, there are higher series like P Fund also, but this much is enough for NEET physics, trust me. Why did Lyman not find other series? I don't know, Dhanuraj. I'll have to go back in time and ask him. Lyman, why did you not find others, man? You just had to draw these lines. It looks so simple. But guys, those times are different and it's not easy to find it experimentally. Here you can draw the lines, but actually finding it experimentally, difficult. Yes. So guys, Balmer series first line will be from 3 to 2. 3 to 2. This is second line. This is third line. This is fourth line. This is fifth line. If I say first line of Paschen series, that will be n is equal to 4 to n is equal to 3. If I say last line of Lyman series, Lyman is here, last line is here, don't say 7, no, it's actually more, from infinity to 1. From infinity to 1 is the last line of Lyman series. Everyone? Get it? No, not 7 to 1. Crazy fellows. I knew many of you were like, sir, in the diagram it is 7 to 1. Understand? In the diagram I have not shown other lines. 8, 9, 10 till infinity. So infinity will be somewhere here. So from infinity to 1, that will be the last line of Lyman series. Got it? Everyone? Excellent. This is how the naming works. Now every transition is associated with an energy. So I'll just put it up over here maybe. Do I have some space somewhere? Oh my god, I don't have space. I'll just write it over here then. Okay guys. See, when the energy changes from one level to another level, then the change in the energy of the orbit, like I told you before, is associated with the energy of that particular photon. The energy of the photon is hc by lambda. Energy difference of that orbit I can use minus 13.6 z square by n1 square minus 13.6 z square by n2 square. All this is in electron volt. You make all the conversions, solve this. Everybody understood this step? Energy difference of the orbit, this orbit and this orbit, this orbit and this orbit. N1 and N2 are just the numbers, 3, 4, 5, 6, whatever it is. Minus 13.6 z square by n1 square, minus 13.6 z square by n2 square. When you take these numbers, solve it properly, then you get 1 by lambda. 1 by lambda is equal to, you will get some constant, you will get z square, and here you will get n1 square, and here you will get n2 square. Here you will get n1 square and here you will get n2 square. This constant is basically called as the Rydberg's constant. The symbol for that is R. I'll show you the value as well. And this is the formula which you're going to remember. I just put it up over here. Okay, I just put it up over here as well. You can see. Don't have to remember this. There is no need to remember this. This is the actual formula for the Rydberg's constant. Do not remember, not needed at all. This is what you are going to remember. 1 by lambda is Rydberg constant, 1 by n1 square minus 1 by n2 square. Let me put up over here as well. Just one second. Okay, this is z square. That's all you're going to remember. And the value of the Rydberg's constant, roughly 1.1 10 to the power 7. 1.097 will be more accurate, yes, but you can also write it as 1.1 into 10 to the power 7. That's okay. Yes, it looks like X-ray spectrum. Yes, it is. It is. In fact, X-rays are very much related to these spectrums as well. Okay, so this is a formula, but remember it is 1 by lambda, not lambda. Lambda is there below. Okay, and z square is there on the top. All right. Don't have to remember all of this. Okay, so I'm just putting a cross over here. Do not remember all this. Just remember these values over here. This is more than sufficient. This is more than sufficient. That's all. Okay. Let's move now to the last part of Bohr. Even Bohr failed, guys. Even Bohr was not able to explain certain things. So after that came, orbital theory, and then quantum theory, where you had orbitals. There were no fixed orbits. They were in the weird shape. There were probabilities and all of that. So that is the newest theory, but we do not have that. You have studied brief about orbitals in chemistry. That's about it. But you should know why Bohr's model failed. Because it failed, it violated Heisenberg's uncertainty principle. Number one. Number two, it said that you can precisely locate where the electron is, where the momentum is, how much. So it was violating that. And also it was not applicable for higher elements. For hydrogen it was okay. The moment you go to carbon, even lithium or even helium, the calculation of radius speed was wrong. So that means something was wrong in the assumption of Bohr. So it failed for higher atomic numbers. Third is it was not able to explain Zeeman effect, which is basically when you put magnetic field, there is splitting of spectral lines. Why do the spectral lines split? There was no explanation for that using Bohr's model. So that's why Bohr's model failed. Very important 3 reasons. Very important 3 reasons. Yes, only for hydrogen it worked, and even in hydrogen there is actually a 4th point. In hydrogen, when precise calculations were done, even for hydrogen it did not give exact value. There was a small difference even in hydrogen. So guys, that's why Bohr's model had some flaws, but still we studied because it gives a good idea of how things work. The last question of today's lecture, guys, the wavelength of the first line of Lyman series is lambda. The wavelength of the first line of Balmer series is how much? Zeeman effect, Sandhya, is nothing but the spectral line split when the presence of magnetic field is there. Meaning, do you see these spectral lines? These lines over here? If you apply a magnetic field, that means you bring a magnet, this line splits. This line splits. Why is that splitting happening? No explanation. So Bohr was not able to explain that using his model. That is Zeeman effect. Splitting of spectral lines when a magnet is bought. Okay? Cool? Alright. If it is wrong, why questions were asked from this topic? Dhanuraj, these are theories. It gives you a good understanding of how other things were working. Number 1, whenever a theory is there, it explains certain things, it does not explain certain things. That's what the constant battle of a student is. Correct me if I'm wrong. You are always like, sir, in projectile motion, you ignored air resistance, sir. Then why are we studying this? Blah, I'm not going to study this. That's not you're going to say. So think of it this way, guys. Maybe you're not able to see the bigger picture now. Just imagine a first standard student saying, or first standard student just learning addition and subtraction. Little does he know that addition and subtraction only half the times you can use. So many times you have to use derivatives and integration. If you go and teach him derivatives and integration, because this is reality, right? You need derivatives and integration for most of the complicated or most of the explanations. He will stop studying, quit. Just like Quit India movement, he will quit studies. Like, sorry boss, 1 + 1 = 2 is good enough for me. What is this derivatives and integration? Same way, if you guys start seeing everything now, you'll be like, sorry sir, NEET, tata, bye bye, I'm going sir. So that's why. Okay, chalo, the correct answer for this is option A. Most of you got it, GV, and somebody said D. No, it's not D, it's A. Let's see why it is true. The wavelength of the first line of Lyman, that means 1 and 2. So basically 2 to 1 transition. If you talk about first line of Balmer, Balmer means 3 to 2. Okay. So over here, 1 by lambda 1 will be RZ square. Okay. Is basically 1 by 1 square minus 1 by 2 square, 1 square and 2 square, n1 and n2. Similarly, 1 by lambda 2 will be RZ square, 1 by smaller number first, bigger number later on. That's it. Now just divide the two. Just divide the two, guys. Just have to divide this with this. That's all. You will see many things will get cancelled, like RZ square and RZ square. You will have lambda 2 on the top and you will have lambda 1 below. Okay, that's what you're going to get. And on this side, what are you going to get, guys? Here you will have 1 minus 1 by 4, 1 minus 1 by 4, and here, because this is downstairs, here it will be 1 by 4 minus 1 by 9. Now just solve this till you find the value of lambda 2. Find the value of lambda 2. Just check this, solve this and see if lambda 2 is 27 by 5 times of lambda 1. So let's begin, guys. Now we all know that everything around us is made of atoms, particles, right? Particles, the tiniest particles are atoms. The atom is further made up of smaller particles, namely 3 important things. One is the electron, which revolves. We have seen that in atomic structure in detail, right? Then the second part is nucleus. You know, and I hope you remember from the Rutherford's experiment, what did he say? The entire mass of the atom is not with the electron. It's with the nucleus. It's with the nucleus, correct? Okay. Now this nucleus is small, it's positive, and it is highly concentrated mass. Most of the atom is empty. If you think of the room as the atom, the nucleus will be a small dot in that room. It's that small, and the electrons will be going from the corners of your room. That nucleus gets that charge and the mass because of two smaller particles inside the nucleus. This is a rough picture of nucleus. Obviously, you cannot take a photo no matter what you do. It's just visualization. This is like out of creativity. This is how a nucleus looks like. It's made of tiny particles. One is proton, one is neutron. Why they got those names? Probably you'll get the idea from the first alphabet. P, proton, positive. N, neutral, neutron. Neutral, meaning it has no charge. Proton, P, positive. It is positively charged. So this has no charge, this has charge. Both of them, you can say that almost identical except for the charge factor and a small difference in mass. Otherwise, their masses are also very close to each other. Alright, I hope this is clear. Very good, guys. Please tell important chapters. Okay, I'll make a video on that, Naveen, on this Saturday. Okay, just give me some time. It will take me some time to make it because I have to ask my team to, get all those chapters, do the analysis of the previous papers and give the highest weightage chapters for all the 3 subjects. Okay, I will do that. Now, if you talk about more properties of proton and neutron, like which is inside the nucleus, look at these positive spheres. They are protons. The green ones are the neutrons. They do not have any charge. The symbol for a proton and neutron, guys. For neutron, the symbol is N. Neutron, N. Proton, P, obviously. And like one would expect, neutron is a neutral particle, no charge at all. But there is a mass associated with it. The mass of a neutron, don't have to remember the value. This is just to give an idea. Just remember the first 3-4 digits. That's okay. 1.674 10 to the power minus 27 kg. That's so small, guys. Your mass will be 50-60 kgs. Okay. Probably if you take out a nail or something, it is going to be in few grams. This is 10 to the power minus 27 kg. That's the mass of the neutron. Okay. If you talk about the proton, proton has a plus E charge. What does that E stand for? What is the value of E, guys? Come on, put it up in the chat box. Spam it immediately. Plus E. What is the value? It is plus 1.6. Plus 1.6 into 10 to the power minus 19 coulomb. Exactly. Good evening, Zubair. Okay. Bharni, I'll be doing all the important chapters before your board examination from the board perspective and few chapters of 11th. And after your board examinations, the remaining things will be done. Okay. That's how it's going to go, bacha. You cannot expect everything to be done in just 1 or 2 weeks because then it will be just hurried up and I don't want to hurry up and we have time till May. Don't worry about it. And if you're a dropper, you have even more time because you don't have boards. Mass is almost the same. There is a change only in the third decimal. This is 674, this is 672. The mass of neutron is slightly larger, very slightly larger than the mass of the proton, but otherwise they are roughly the same. You can see that over here. Everyone with me? Very good. Excellent. Thank you, Zubair. Love you too, bachalo. Okay, great. Next point that you should know about a nucleus is the different terms used with defining an element, like hydrogen, different from helium, different from sulfur, different from oxygen. How do you represent a sulfur atom or the sulfur element? There are 3 main things. One is the symbol, one is the atomic mass number, the second and the third one is the atomic number. Atomic mass, atomic number, and basically the element. So we will see that, but before that there is one more important thing, and that is the atomic mass unit, which is the unit of measuring the mass. Like you can see over here, guys, these masses are so small. Dealing with it is a problem. Imagine writing this 10 to the power minus 27, you will be like, to hell with these calculations, I don't care. So there is a smaller unit, and that unit is basically AMU, atomic mass unit, AMU. What is that? 1 AMU is 1/12 the mass of a carbon atom. Carbon atom's mass is very small. So 1/12, why 1/12? Because carbon atom has 12 particles inside the nucleus. 6 protons, 6 neutrons, so 12 particles. So 1/12, that you take it as a standard. And then you measure everything in terms of AMU. The value of 1 AMU is 1.66 10 to the power minus 27 kg. Guys, quickly tell me, is this mass very close to the mass of proton and neutron? Yes or no? Yes, definitely, Swayam, it will be helping you with the boards, but in boards you need to do some more things apart from just going over here, because boards is more of a theory. It's like a memory based exam, writing the answers neatly. NEET is more of thinking, your analytical skills, how you are spontaneously able to recollect some data points or use and apply the concepts. That's what NEET is. So approximately same. Great. So basically one can say that the mass of proton, mass of neutron is roughly the same, and it's very close to this value 1.66. You can see that right from here also. Look at this, 1.67, 1.67. Okay, very close, and this value is also almost the same. So it's 1 atomic mass unit. Very good. Excellent. Okay. Now, Hari, please concentrate, bacha, on the lecture. Okay. This is not the J channel, this is a NEET channel. Okay. Now, the next important thing that you should know, like I was telling, is the representation. There were 3 things: atomic mass number, atomic number, and the element name. So guys, the first thing is X, which is the symbol of the atom. If it's helium, I will use He. If it's sulfur, I'll use S. If it is oxygen, I'll use O. So looking at that symbol only, you get an idea. Oh, this is oxygen. Okay, this is hydrogen. This is helium. Like that. Then you have Z. Z is in that nucleus, how many ever protons are there? If you count them, that decides the chemical characteristic of the nucleus. That is the atomic number, which is just the number of protons. That's Z. Last one being atomic mass number. Atomic mass number is the total number of particles inside the nucleus, which I call it as nucleons. So when I say the word nucleons, this nucleons means all those things which are inside the nucleus, basically protons and neutrons. So this value, atomic mass number, capital A, is the number of protons, which is Z, plus the number of neutrons. This is also a very important formula. And the way you generally represent any given element is something like this. Look at this. X is that element, like oxygen, atomic mass number on the top and atomic number below. So just to give you an example over here, it is nothing but like if I have helium and I say 4 over here and 2 over here, that means this 4 is the atomic mass number, this 2 is the atomic number. So there are 2 protons and 2 neutrons. There are 2 protons and 2 neutrons. Together there are 4 nucleons. So together there are 4 nuclear particles, that means nucleons. Is that clear, my dear students? Very good. Is that clear? Excellent. Awesome. Assignment questions. Niranjan, I have already shared the assignment questions on the Telegram channel. Whatever last session I did, bacha, I already uploaded it on the Telegram channel, the NEET English Elite channel. So please have a look at it. When we do problem solving sessions, those problems with solutions as well as the homework questions and their answers are also uploaded. Great. Next thing that we can talk about is the 3 different relationships between all these elements. What are these 3 important relationships? Understand that. Okay, like you have brothers, you have uncles, you have friends. So elements also have some relationships. First relationship that you want to learn is isotope. Now in this relationship, they basically are very similar in characteristics, but they have different masses. Maybe like a twin brother or triplets, you might have heard of them. So all the 3 are very similar. They all like sweets, they all like to watch cricket, okay, or whatever. But one is very thin, one is really fat, another one is really fat. So that is basically called as an isotope. Hydrogen. Why is it called hydrogen? Because there is 1 proton inside the nucleus. Atomic number is 1, but mass number is different because here there is no neutron, here there is 1 neutron, here there are 2 neutrons, because out of the 3, 1 is the proton, remaining is the neutrons. I hope you get that. Same way over here. Oxygen, very similar. But what is different is the neutrons. So the mass number is different. That is called as an isotope. The next relationship is isobar. In isobar, their weights are same. Like your uncle might have the same weight as your cousin, might have the same weight as your friend. All are nice 60 kilos. Everybody is 60, 70 kilos. But one is your uncle, one is your friend, one is your cousin. They all are different. One likes cricket, one likes football. This guy likes sweets, this guy likes spicy food. So different in characteristics. So that is called as isobars. Look at that. This is hydrogen, this is helium. Completely different. This has one proton, this has two protons. But what is same is the number of nuclear particles. Nucleons. 3 nucleons, 3 nucleons. Proton plus neutron, the combination is the same. Total number. I hope that's clear. And same thing. This is carbon. Very different than nitrogen. Protons are different. But total nucleons, that is atomic mass number, is the same. You can see that right over here. Okay. Last one is isotone. When I say the word tone, N is being stretched now. When you say isotone, N stands for neutron. So in isotones, what is same? Neutrons. The number of neutrons is same. Look at these elements. 3Li7, 4Be8. Doesn't look similar, but what is same is the neutrons. 7 minus 3 is 4. 8 minus 4 is also 4. There you go, 4 number of neutrons. Same number of neutrons, isotones. This and this. 3 minus 1, 2. 4 minus 2, also 2. So 2 neutrons, so they are isotones. That's all. So isotopes, same atomic number. Isobars, same atomic mass number, that's the top. And isotones, same number of neutrons. That's what it is. Great. So what we are doing is, right now we are studying nucleus. What are the different parts of the nucleus? How do you show the nucleus? What is atomic number? What is mass number? What is neutron number? What is the relationship? That's what you are learning. One of the last things in this is the radius or the size or the density of the nucleus. Now, if there are more particles inside the nucleus, it will become big. Like, for example, if I take helium, it barely has 2 protons, 2 neutrons. So 4 particles are there. But if I take oxygen or carbon, carbon has 12 particles inside. So big. So obviously the size grows as you add more protons and more neutrons. That means what matters is the atomic mass number. Atomic mass number is what matters in deciding the size of the nucleus. And the size I can calculate by measuring the radius of the nucleus. Nucleus, if I take it like a sphere, the radius of the nucleus is dependent on the atomic mass number given by this relationship. What is the radius of the nucleus? It is A raised to 1 by 3. A is nothing but atomic mass number, R is nothing but the radius. So you can think as if this is the nucleus, this is the radius. There will be also some volume which will be 4 by 3 pi r cube. This constant of proportionality comes out to be R naught. This R naught has a rough value of 1.2 FM. If you are wondering what is this FM, sir, I've heard of radio FM. What is this FM? Here this F stands for 10 to the power minus 15. So it's so small. 10 to the power minus 15 Fermi. That's the level. You know, milli is 10 to the power minus 3. Micro is 10 to the power minus 6. Nano is 10 to the power minus 9. Pico is 10 to the power minus 12. Fermi is 10 to the power minus 15. That's very small, guys. This is the radius that you get. Now you can also calculate the density of the nucleus, how dense it is. So that density will be the total mass of that nucleus upon the volume of the nucleus. Okay. Now one thing I can see from here in calculation of volume, this will be 4 by 3 pi r cube will make it r naught cube into a raised to 1 by 3's cube. A raised to 1 by 3 raised to 3 will become a. So this just becomes 4 by 3 pi r naught cube into a, correct? So why not use that over here? So downstairs I'm just going to use 4 by 3 pi r naught cube into a. What's going to come on the top? What's going to come on the top? Total mass of the nucleus. Nucleus has particles. How many particles? Protons and neutrons. Just count them. Let's say 12, let's say 10. What is the 10, 12, 100, whatever? That is the atomic mass number. So that means the number of particles into mass of each particle. So mass of each nucleon into atomic mass number will give me the total mass of the nucleus. Correct? What happens? AA cancels, guys. AA cancels. So I'm just left with mass of the nucleon. This 3 goes on the top. The whole thing divided by 4 pi r naught cube. That means if this is just a number, it's going to be like, some value. 3 is a value, 4 is a value, pi is a value, r naught is a constant. So this is also going to be a constant. That means it is independent. It is just independent of the atom. Completely independent. Iron might be this big, sulfur might be this small, helium might be this small, but all of them have the same density. This is the proof for that. Yes, density of all the nucleus is constant. Hello Manaswini Banela, welcome Bachalo, good evening. Hello Danish, nice to see you guys out here. Keep attending the classes, make sure smash the like button and also hit the subscribe button. Very important, guys. I don't want you to miss any of the classes. Okay, very simple and important things about the nucleus. Moving on, oh, by the way, I have kept the printed material as well. So I hope you know you are going to get all my material on the Telegram channel. You will get the printed as well as my handwritten notes. Great. So let's see. What do you think is the relationship between these two and these two? Isotopes, isobars, isotones. What do you think? I want everybody spamming in the chat box, guys, right now. Come on, let's see how many of you are going to spam and get the right answer. Let's get you guys on the screen also. There it is. Okay. Come on. Figure this out. What do you think is the correct answer to this particular question? Option B says Salva Kumari. All right. What about others? Others, come on. Let's see how many of you are going to be correct about this. How many of you are going to be correct about this? Come on, guys. Figure this out. What is the correct answer? A, B, C or D? A, B, C or D? Yes, the correct answer is B, and our lovely warriors have won this. Very good. You can see over here 76, 76. So obviously atomic mass number is same because A is same. Here 30 minus 14 is 16. 32 minus 16 is also 16. So they are basically isotones. Basically N is same, which is A minus Z. That's it. Option B. Very nice. Perfecto. Now, let's talk about the next concept. We have talked about what a nucleus looks like, what is it made up of, how do you show it, how a nucleus is formed. Is it stable or is it unstable? Is there some energy involved? Is there some force involved? Let's talk about that before going to radioactive nucleus and all that, or nuclear reaction. Now, if there are two positive charges, yes, Pandu is here. A lot of you were requesting, sir, where is Pandu, sir? So there we have our amazing Pandu. And this Pandu starts wondering, proton do not like each other. It happens, right? In your school, you don't like somebody. Sir, I don't like sir. He always teases me. He bullies me. Or he's always rude. Or he's random. He's mad, psycho. And that person is also like, I also don't like you. You are doing this, you are doing that, you don't care, whatever. There is always a mutual repulsion, okay, between maybe some two people in the school or maybe in your society. Same way, two protons also don't like each other. What is the reason for that? Electric force. But proton and electron like each other. The moment proton sees the electron, it will be like, come to me. But electron will be like, listen, I can't fall into you, then there will be a big explosion. I will revolve around you. So the electron revolves around the protons or the nucleus using the electric force of attraction, right? Just like the earth revolves around the sun, because of mutual force of gravitation, right? But proton, they don't like each other. They're like, go away. How do they stay together? What's the reason for that? So in general, you can say that there must be something much stronger something more superior than the electric hatred force or the repulsion force which brings them together. Like if there are two enemies and then, teacher is like, you Pandu, come sit here. Oh, you Laddu, come sit here. Sit on the same bench as Pandu. Pandu and Laddu don't like each other. They hate, they repel. But teacher made them sit together, do the same assignment or project together. They don't like, but still they are together. For some reason, what is that force? Teacher force. Teacher force made Pandu and Laddu sit together. They were actually enemies. They don't like each other. So if two protons are staying together, there must be something superior than electric force or gravitational force. That is basically your nuclear force because it is inside the nucleus. And this nuclear force is the one which holds the protons and protons, neutrons and neutrons, or neutron and neutron, proton and neutron, proton and proton together. Teacher forces, correct? Just like you guys are staying over here on this channel because of teacher force, right? Correct. Maybe there is some person you don't like. Hope not. Hopefully all of you are friends, right? Correct? Great. Now, what is this force? What does it depend on? Gravitational force. What does it depend on? Mass, m1, m2, and distance. Okay. Electric force. What does it depend on? Charge, q1, q2, and distance. Nuclear force. Is there a formula? Well, there is, but you don't have to study it. Like, sir, thank God, one link less in our NEET syllabus. You just need to know the basic traits of a nuclear force. So, nuclear force depends on something else only, and it is basically the spin. It depends on the spin. It depends on the distance, but not so much. It's like, two particles are there, there is a nuclear force. You increase the distance between them, the nuclear force hardly changes, and if you increase the distance further, tuck, it drops. Suddenly it goes down. So it is there only in a certain region, and it is very small range for which the nuclear force acts. As soon as you increase the distance, immediately it drops down. So it's a very saturated force. It's a short range force, but it is very strong, very superior, stronger than gravity, stronger than electrostatic. And it does not depend on the mass or the charge. It depends on the spin. Very good. Manasuni, where is Champa? In love stories, today we are learning hate stories, so that's why Pandu and Laddu came. When we learn some love story, then I'll bring Champa and Pandu also. Don't worry about it. Okay. So I put up all the properties that I just explained to you in the points form. You will be using these points in your boards, or maybe they might just give you as an objective question. Which of the following is not a characteristic of nuclear force? So it is basically independent of the charge. It does not depend. It's a very short range force. It's saturated. It is not going to follow that formula Q1 Q2 by R square. So it's not a central force. Central force means it should follow that formula, Q1 Q2 by R square or M1 M2 by R square, that kind. It's not. Okay. So these are the main characteristics of the nuclear force which you should know. It's a fundamental force. Understand that. Just like you have gravity, you have electromagnetic, there is nuclear. Then nuclear also there are two more forces like short nuclear and strong nuclear, or weak and strong, but you don't have to go so much into detail as of now. Okay. Now what is the meaning of exchange force? Very good, GV. So like when you have two masses, there is a force. Just because those two masses are there, there is a gravitational force. In nuclear forces, what happens is there are particles which go from here to here, and there is one particle which goes from here to here and is like, hey, listen, I am there with you. It's like sending a messenger. Okay, we both have to attract each other. Okay. Then this guy also passes one chit, like it happens in school, na? You pass one chit, like, hey, listen, let's do this, let's do that. Listen, after the break, after the break, let's go here. So that is a chit. So they send messages like you send WhatsApp, na? Like that. Okay. I hope this is clear. Everybody with me? Let's now go to the ultimate question. Okay. Now, this is going to talk more about the stability. Let's more talk about the stability of the nucleus. Let's talk about even the, what is the mass defect and the energy associated with the nucleus. All these things are going to come from this particular slide. Now, what is mass defect? Everything we are going to talk, just understand what I'm asking and answer the question in the chat box. Imagine I take helium. Helium, what does helium have? Helium nucleus have? It has 2 protons and 2 neutrons. 2 protons and 2 neutrons, right? Okay. Karpana champ, you don't have to take notes in my class because all these slides will be available. Number 1. Number 2, you can make running notes only for the formulas or important things. It will be there in the slides, but just so that it enters your head. Don't have to make long notes. If you already have your notes, then just add the extra points that you learn. That's all. 2 protons, 2 neutrons. Okay, that's a helium nucleus. On the other side of the beam balance, I have 2 protons and 2 neutrons. Which one will be heavier? Which one will be heavier? What do you think? The helium nucleus, or the 2 protons and the 2 neutrons? Answer it in the chat box, guys. I'm waiting to hear your answers. Salva Kumari says the mass of the nucleus is less. So that means this will go up. These 2 protons and neutrons separately where you have placed it, this will go down. That's what she says. Emily says more, equal, same, equal. Interesting answers out there. Come on, let's see how many of you can get this. Is it going to be, which one will weigh more? Helium nucleus, protons and neutrons, or both will have the same weight? A lot of you are going to get it wrong. A lot of you are going to get it correct. So the ones who are correct are the ones who are saying option C. Yes, GV. Yes, I think you are the first one to tell it. Yes, you will be like, what nonsense. Let's bring Pandu and Champa. Somebody was saying, sir, where is Champa, sir? I'll bring Champa now. Pandu weighs 60 kilos. What is the weight of Pandu? 60 kilos. Pandu. There is Champa, his girlfriend. Champa, her weight is 40 kilos. Pandu, 60 kilos. Champa, 40 kilos. Pandu, 60. Champa, 40. What is their total weight? Answer in the chat box. Pandu 60, Champa 40. What's their total mass? What's their total weight? Come on guys, answer in the chat box. No, electrons will not contribute in the mass. We are ignoring that. 100, very good. Now, Pandu met Champa. He became very happy. He's holding her hand and walking in the park or just putting his arm around, and they both are walking nicely. They're dreaming. They're talking about something. This is imaginary Champa, guys, okay? So imagine this is imaginary Champa. This is imaginary Champa, okay? And now I ask you, what is their total mass? You're like, sir, 100, sir. Pandu's mass is 60, Champa's mass is 40, total mass is 100. Then you ask them to stand on the weighing machine. They stand together. They find that their mass is not 100. Their mass is 95 kilos. They will be like, what just happened? Then they're like, okay, wait, let me do this again. So Pandu goes and stands separately. He sees 60 kilos. Pandu steps aside. Champa comes. 40 kilos. Lights. Okay, 60 plus 40, 100. Now, both of them come, stand together. They both are standing together. Their weight, 95 kilos. They're like, what just happened? Where did that 5 kilo go? Mass defect. Something is defective. Mass defect. It is basically the mass defect. You're like, sir, how this mass defect? Where is that mass going? Somebody ate, huh? Sir, Laddu came and ate Pandu. That's why, sir, 5 kilos less. No, Laddu did not eat Pandu. You will eat Laddu, no? You eat Laddus. How can Laddu eat you? Okay? You cannot eat Laddu. Sorry, you can eat Laddu, Laddu can't eat you. So nobody has eaten Pandu or Champa, guys. So energy is the word. I am seeing the word energy. Very nice. This was the theory which Einstein proposed. I am going to come to that. But for now, what is mass defect? It is found the mass of the nucleus is always less than the sum of the masses of its individual particles freely. So protons and neutrons, if you weigh, it's always more. Nucleus is always weighing less. This difference is called as the mass defect. This is called as the mass defect. So basically the mass defect is the mass what you are expecting minus the mass which is actual, like it happens in reality also, right? Sir, I am expecting 170 marks in physics. Actually, sir, I got 150 marks only. So 20 marks is the mass Mark's defect. Mark's defect. Mass defect is what you're expecting. You're expecting 100 kilos, but you got 95 kilos. So 5 kilos is the mass defect. Agree, disagree? Agree, disagree? Got it? So this is mass defect. Excellent, guys. Expected minus the actual. Usually you will see it in many books that it is basically the mass of the, what do you say? You are expecting it to be mass of protons plus mass of neutrons minus the mass of the nucleus. That is how it is usually calculated also. Okay, mass of protons plus neutrons minus the mass of nucleus, which is actual. This is expecting. Total mass. By the way, this is the total mass. Okay, great. Now, like I was telling, that this mass goes somewhere. Where does it go? It goes into energy. That's what Einstein said. That's what Einstein said. See, Einstein said, when you destroy mass, you break that mass, top, gone, poof, something else is created. What is created? Energy. Energy is created. Mass is destroyed, energy is created. Somebody destroys energy, mass is created. Both are interchangeable, convertible. There is equivalent mass for some energy. There is equivalent energy for mass. Both are interchangeable. So what is the relationship between them is given by Einstein's famous equation, which is very simple. And most of you already have put it up in the chat box. Proud of all of you guys that energy which is created or destroyed is related to the mass which is destroyed or created into c square. This is the formula, but what happens is if you put 1 kg mass also, just imagine you take 1 kg and destroy 1 kg mass. Look at the energy which will be created. C, what is the value of C? 3 into 10 to the power 8. C is 3 into 10 to the power 8. So guys, if I take delta m is equal to 1 kg, C is 3 into 10 to the power 8, I will get energy as 1 into 3 into 10 to the power 8 square, which will be 9 into 10 to the power 16 joules. This is crazy, guys. Look at that energy. It's not 5, 10, 100 joules, 1 lakh joules. No, it is 10 to the power 16 joules. It's in trillions and millions of joules. So much energy will be created by just destroying 1 kilo of mass. It will solve all our energy problems. Now, this energy is very huge, but usually the masses which we talk about are also very small. It's not in 1 kilos. 10 to the power minus 27, minus 28, that's small. So the masses are that small, the energy is not this big, it is also very small. So what do? Convert mass into atomic mass unit. Remember the small unit of mass. C value you put and convert the joules into electron volt. Convert the joules into electron volt. Yes, for nuclear reactors and all that, this is the scale of the energy. Yes, Emily. So when you convert it, it looks like this. Delta M in atomic mass unit multiplied by the conversion factor is 931 mega electron volt. This is the formula which you will be using more frequently, but keep in mind this mass defect is in AMU, not in kgs. This was in kgs. This was in SI units. This is not SI. This is AMU converted into electron volt, not joules or SI unit. Very good. So when you destroy 1/12 the mass of carbon atom, which is 1 AMU, you get 931 mega electron volt. That's why nuclear reaction is very powerful and very energetic. You have to burn so much of coal to get that much energy. You have to lay so many solar panels to get that much energy. To destroy a few atoms here and there, that's it. So much of energy will come. That's why nuclear energy is very powerful, and unlike what people believe, where nuclear reactions are very scary, sir, very dangerous. Actually, nuclear reaction or nuclear energy is much cleaner and much more safer than the other forms of energy. In fact, it's said that a lot of animals, like especially birds, die because of windmills. Because of the wind turbines, a lot of birds actually die. And also solar energy is so costly to make because of the silicon requirements and all of that, because of the semiconductors. So actually speaking, nuclear, although it looks dangerous, causes much fewer deaths than coal related deaths, or the cost which is involved in other energy setups. It's crazy. Now let's talk about something called as the binding energy. Why is it not the major energy supply? Because people get scared. It's because people start protesting. Oh, I don't want nuclear power plant. It will cause explosion. Yes, nuclear explosions are dangerous. If you get exposed to nuclear reactions, then your skin will burn. You might die. But that is so rare. It's so rare that you might probably die breathing the air which is produced from the coal plants because of that carbon dioxide and carbon monoxide. That's how it is. But we cannot see that. You don't feel it because it happens over a period of 10, 12 years or 20 years, right? But nuclear reaction related death will happen instantly, so people are scared, but it rarely happens if you see the data. That's how it is. Okay. Yeah, people are reminded of Hiroshima, right? Okay. So, talking about binding energy. What is this binding energy? See, when I take these protons and neutrons and I put them together, the mass of the nucleus is less. So, let me just put it over here. That energy which is created is called as the binding energy. Let me explain this to you. I have certain protons and certain neutrons separately. They combine together to form a nucleus, maybe helium. Example, this is your individual protons. These are free protons and neutrons. This is your nucleus. I know that the mass of the nucleus is lower than the mass of the free protons and neutrons. So there is a mass defect. So as you can see in this transition, if this guy's mass, the total mass is m1, this guy's mass is m2, m2 is obviously less than m1, hence there is definitely a mass defect which is m1 minus m2. m1 is higher than m2, so there is a mass defect. So the mass has been destroyed. So here mass is, this delta M mass is destroyed. If the mass is destroyed by the principle of equivalence, something should be created. If the mass gets destroyed, the mass becomes smaller. What is created? Energy is created. So mass is destroyed. So energy is basically created. This energy which is created is called as the binding energy. What is it called? The energy released in the process of creating that nucleus is called binding energy. Why binding? Because you're binding, you're putting them together, binding them, putting them together. That's why binding energy. So mesons are basically those nuclear force related particles. You don't have to go there. Those are those exchange particles in nuclear forces. If you do PhD and all that, then you will learn more about it. Okay. Obviously, Harshu, it's not that real name. It's obviously students who call me out of love, and that's why I obviously I love students. I love teaching. So because if students are calling me, so that's why I put it in my name itself. In all my Instagram handle, Twitter handle, everywhere you will see the word captain. Okay. Now this binding energy is calculated by, this binding energy is just calculated by delta M into C square, where the delta M is the total mass of the proton plus the neutron minus the mass of the nucleus. This is how you calculate it, or you can also use 931 into delta M mega electron volt, whichever you want to use, this or this formula. Okay, great. Yes, minions have given me the name. Very true. Excellent. Now let's talk about something else, and that is basically binding energy per nucleon. Like, sir, what is this binding energy per nucleon? I'll give you a simple example, then you will get an idea. Imagine, let's bring in Pandu. Guys. Pandu donates some money to poor people. How much money he donates? 1000 rupees. 1000 rupees. To how many people? To, let's say, 10 people. 10 people he donates 1000 rupees. So each person one person will get how much rupees? How many rupees? 1000 divided by 10. That's going to be 100 rupees per person, per poor person that he donated. Very nice. Camera is not focusing well, I'm not sure, bacha. It should be. I've just adjusted it. I'll just adjust it again. Oh, I understood what was wrong. It was on autofocus. So when I move back and forth, it was changing the focus. So that was the problem. Thank you for reminding me. Okay. Now let's take Champa. Champa is also donating. So Champa decides if Pandu donates 1000 rupees, I will donate 10,000 rupees. So Champa donates 10,000 rupees. But she donates it to more people. 1000 people she gives it. So each person will get how many rupees? Each person will get how many rupees? Yes, autofocus is now off. Usually I keep it off, but today I think I forgot it. Now, yes, GB, correct. She will give 10 rupees per poor person. So 10 rupees. Now, if you are a poor person, would you like the donation from Pandu or Champa? Put it up, spam it in the chat box. If you are a poor person and you want some donation, where would you want to be? Would you want to take the donation from Pandu or would you want to take the donation from Champa? Selva Kumari says Pandu. GB says Pandu. Somika also says Pandu. Prem, Karpa, Sampath, Hamshi also says Pandu. Lenasis also says Pandu. Varsha, Vijay, Roshni, Murshida. Very good. Everybody says Pandu. Excellent. Although Champa gave a lot of money to many people, what matters is per person how much money did you give. So that brings us to the concept of binding energy per nucleon. Now I'll give you why this concept is even more important. Now see guys, this binding energy is the energy released. Now when more energy is released, where more energy is released, it becomes more stable. Just like, sir, I was very frustrated, very tensed. I was very angry. I don't know, I had mixed feelings. Very irritated I was. So you know what I did? I shouted at so many people. I did so many things. I was playing games. I released my frustration. And then I calmed down. So you release your frustration, you release your anger, and that's when you calm down. Same way, these atoms, these nuclei also, when they release the energy, they calm down. That means they become more stable. Everybody gets this? Everybody gets this? I know, Prem, you can argue with so many different factors like, sir, she gave more money to more people. I'm not going there, but this was just to explain you the concept of binding energy per nucleon. So now, when the binding energy is released, if you count it per nucleon, if more energy is released, that means it is more stable. If less energy is released, it is less stable. More energy is released per nuclear particle, it is more stable. If less energy is released per particle, it is less stable. That's what this binding energy per nucleon is. So you just take the binding energy and divide it by the nucleus, so number of nuclear particles. So binding energy per nucleon, this is the formula. This is nothing but delta M into 931 mega electron volt divided by atomic mass number. So if it is chlorine, you might most likely divide by 35. It's, hydrogen, it's just 1 or 2 depending on the isotope, and if it's helium, you might divide it by 4. So depending on the element, you are going to divide it by a suitable atomic mass number. So per nuclear particle, per proton or neutron, how much energy is given? It decides the stability of the nucleus. Now what scientists did, they took all the elements of the periodic table. Imagine how much time will be needed for this. All the elements you take, calculate the mass of the proton, calculate the mass of the nucleus, subtract the two, find the mass defect, multiply by 931, divide by A. For this is the binding energy per nucleon. Then take the next element. Again, calculate the mass defect, calculate the binding energy per nucleon. They did it for all the elements of the periodic table. So guys, you need to be really motivated, and really you need to have that, find a time to do all this. And they plotted a graph, and the graph came out to be like this. Look at this graph. For hydrogen, depending on the isotope, very close to 2 mega electron volt per nuclear particle. If you go to higher elements like nitrogen, carbon, oxygen, comes to somewhere between 6 to 8 mega electron volt per nuclear particle. It kept on increasing from sulfur to etc. to iron, and after iron, which is close to like 9 or something, 9 mega electron volt per nuclear particle, it starts dropping to higher elements. Somewhere around uranium, it goes down till as close as 7 mega electron volt or something like that per nuclear particle. From this graph, who do you think is the most happiest nuclear particle? Exactly, Prem has already answered it. For iron, it is maximum the nuclear energy which is released per nucleon. So guys, that is the most stable element. So these people will be jealous of iron. Yes or no? They'll be like, oh my god, look at him, so much energy released. These people will also be envious, or they will be jealous of iron. They also want to come down to iron because there is more energy per nuclear particle. So this graph also gives you the stability chart of the nucleus of any element. Okay, but don't think, sir, hydrogen is jealous of iron. No, why can't it become iron? Is it so simple? Is it so simple? Hydrogen says, hey, listen, come no, I have something secret. See, look at this chart, what I found. See, well, let's become iron. Let's become iron, will be more stable. That hydrogen will be like, get lost. I am hydrogen, I am going to stay hydrogen. Nobody, Papa, will listen to that hydrogen. They'll be like, tata, bye bye. Hey, I'm not going to listen. You need to literally force them. Hey, come man, sit here. Wait, I'll tell you, you will get more energy per nucleon. You have to bring all these people together. Hey, sit together, man. There is more energy released. You have to force them. And then they'll be like, what? Really? So much of energy per nuclear particle? And they will become iron. So you have to literally make in a lot of effort. And they'll be like, oh my god, I never knew this could happen. So these reactions take a lot of effort, lot of energy to bring them into that particular stable state. Sometimes it is natural. We'll come to that as well. Sometimes it is forced. Yep, very true. So Parnika, even now the focus is not clear? Really? I think it should be fine. Yes. So we are going to come to fusion and fission in a bit, but before that, let's talk about this question. Okay, what do we have? Two neutrons undergo nuclear fusion to form helium. Energy in the process is how much? Let's talk about it. Let's first write it down. Two deuterons. Deuterons means hydrogen, atomic number 1, atomic mass number 2. Two of them, so 2H1, 2 into 2H1 combines to give you what? Helium. So helium is He, atomic number 2, atomic mass number 4. It makes sense. 1 into 2, 2, 2 into 2, 4. It is a proper balanced reaction. Okay. Now, how do I find how much energy is released? How much energy is basically released? Simple logic. Observe all the steps. I'm going to explain you the details and then I'll give you a general formula. You will avoid all these steps. Okay? Observe. First, if you want to just form hydrogen, I will need one proton and one neutron which combine together to give you basically one hydrogen nucleus. One hydrogen nucleus, in fact, in the form of deuteron. This is the deuteron isotope, okay, of hydrogen. Now, since I want two hydrogens, okay, over here, so two protons plus two neutrons give me two deuteriums or two hydrogens over here. Okay. Now, energy per nucleon, observe this carefully. Per nucleon, for deuteron is 1.1. For deuteron is 1.1. Correct? In deuteron, how many nuclear particles are there? I will tell you, bacha. First, observe this. how many nuclear particles are there in deuteron? 2, right? 1 proton, 1 neutron. So how much energy will be released? 2 into 1.1, right? 2 into 1.1 mega electron volt. Very good. When there are 2 deuterons, not 1, 2, so this will get multiplied by 2. So 2 into 1.1, this whole number, what is it value? 2 2s are 4, 4 into 1.1 is 4.4 mega electron volt. Keep this on the side. Keep this on the side. Don't do anything now. Very good. Now look at the other particle, which is helium. Helium can be found by, again, take 2 protons, take 2 neutrons, and then it combines to give you 1 helium nucleus. In helium, per nucleon, the energy is 7. Now, how many particles are there in the helium nucleus? 4, right? 2 protons, 2 neutrons, so 4 particles. Per particle, 7. So for 4 particles, 4 into 7, which is nothing but 28 mega electron volt. Correct? Very nice. Now observe this. 2p, 2n. 2p, 2n. LHS is equal? If LHS is equal, what will be RHS? Equal. LHS is equal, RHS will be equal, correct? So let's use that. So 2H1 plus, how much was it? 4.4 will be equal to, what do I get over here? 4He2 plus, what is it? 28, correct? Let's just rearrange this. So I'm just going to keep this as it is over here, 2H1, okay, is equal to 4He2, correct? 28, oops, plus 28 minus 4.4. That is what I get on the right hand side. So what does this tell you? What does this tell you? This reaction is going like this forward. I should not put equal to, I'll put arrow marks to show that it is a reaction. I think this reaction is similar to this reaction. I think I just got the energy from this. So guys, what is the energy which is basically released? That energy is nothing but 28 minus 4.4, which is just nothing but how much? 23.6 mega electron volt. Exactly, guys. That's option D. Now you might be like, sir, this is a headache. So many things I have to do. Yeah, this is the logic. I have explained it to you in detail. But if you want to avoid that, there is one simple shortcut trick. So whenever you have to find the energy which is released, what you do is, look, what is 28? 28 is the binding energy. 28 is the binding energy of, what is this? Product or reactant? H, hydrogen is the reactant. Helium is the product. Helium is the product, correct? So what is 28? Is the binding energy, the total binding energy of helium, correct? So can I say it is binding energy of the product. And what is 4.4? 4.4 was the binding energy of hydrogen, which in this case is the reactant. It is reacting. So minus binding energy of the reactant. That's it. That's it. Exactly. Product minus reactant. Very simple formula. So you can avoid all this nonsense. If you want to avoid all this nonsense, you can just remember this formula. Easily you will get it. Isn't it amazing, guys? The difference of the binding energy is as simple as that. Now let's go to the next part. Very nice. Very nice, guys. The next part is basically the nuclear reactions and the particles that come out. You might have seen in movies, they carry some rods, uranium, thorium, etc. and they look as a shiny, bright, because there is some nuclear reaction happening. And these nuclear reactions are very dangerous. So they are often enclosed in lead boxes or very thick cement and lead, because they have properties of absorbing all the harmful radiations which come out of a nuclear reaction. Okay. So what are the kind of particles that come out? there are three major particles. One is called alpha, one is called beta, the third one is called gamma. So what is alpha particle? Alpha is basically doubly ionized helium. So usually the symbol for that is nothing but alpha, atomic mass number 4, atomic number 2. Mass number is 4, number is 2. The second one is beta particle. Beta particle is nothing but, simply put, an electron. The symbol for a beta particle, because it's an electron, mass number negligible, so put 0, but atomic number -1, because if it is there in the nucleus, imagine if an electron enters the nucleus, it will cause a negative effect. That means it will not add to the charge, it will reduce the charge, because it's negatively charged particle. So that's why -1. Okay. Last one is gamma. Gamma is nothing but the photon. Is nothing but a photon, not proton. Photon, which is basically light. Gamma has no mass number nor any atomic number. 0, 0. Exactly. Very good. Okay. Now, if I apply electric field or magnetic field, which of these will get affected by it? Put it up in the chat box. Which of these will get affected? Put it up in the chat box, guys. Come on. This is what chapter, sir, I'm studying. Very good, Sanjay. Oh, you have modern physics in 11th grade only. Which board are you in, bacha? Alpha will get affected, beta will get affected, but gamma, no effect. Gamma unaffected. Very good, Salva Kumari. Gamma is not affected, but gamma is the smallest. Alpha is the largest. Alpha is the heaviest. Beta is medium, and beta is actually fast. Gamma is the fastest. If you compare the speeds, alpha bulky, right? Big boy. Aram se it will go. Aram se. Heavy mass. Beta very small. Zoop, it will go. Gamma is light. Light will go the fastest. Nothing can beat the speed of light, guys. Fastest. Okay? But because it is so fast and it is so small, it can also penetrate a lot. Alpha, not so much. Beta, a little better you can say than alpha. Okay, guys? Alpha is the least penetrating. Beta is slightly more. Gamma is the highest and the fastest also. Awesome. Awesome. There are simple things that they do when there is a nuclear reaction. Okay. So I have put up all the three things over here. Observe carefully. If there is alpha decay, meaning a nucleus emits alpha particle, you will notice, because an alpha particle comes out, the atomic number, because alpha particle means 2 protons, right? So atomic number will reduce by 2 and atomic mass number will reduce by 4. You can see this is basically the parent. This is called as the parent, and this one is called as the daughter, the child nucleus, daughter nucleus. That's what it is called. That's what an alpha reaction does. Everybody clear? So 2 protons and 2 neutrons separate out, they become alpha particle and they're shooed away from the nucleus. Great. That's what an alpha reaction does. When you talk about beta, what is it doing is, inside the nucleus, there is one neutron. It splits into a proton and an electron. Proton and an electron. So think what is happening. A neutron is there, neutral particle. Suddenly it becomes a proton and an electron is just thrown out. So the moment it becomes a proton, what will happen? Charge will increase. So the atomic size will not change, but number will change, because protons is 1 excess. So that's why you can see atomic number increases by 1. There is no change in the atomic mass number, because neutron became a proton, roughly the same mass. The electron is just thrown out, which is called as the beta particle. Very nice. Now in gamma, you'll be surprised to see atomic mass number same, atomic number same, it's balanced 0, 0. A plus 0 is A, Z plus 0 is Z. Like what is this, sir? Nothing has changed. Actually something has changed, and that is at nuclear scale. So actually what happens is, this is an excited nucleus. Do you remember atomic structure? Different states of hydrogen like atoms in Bohr's model. Electron is in excited state, goes to ground state. What does it emit? Electron, when it goes from excited to ground state, remember Lyman-Balmer Paschen series? What will happen? It will release light, photon, same way a nucleus, not the electron, nucleus can be excited, very happy. It becomes unhappy, or okay, done. It releases what? Light. So this is basically your ground state. This is basically your ground state. So that's why you are getting a photon. Yes, electromagnetic waves. So Emily, usually the duration of the lectures is anywhere between 1 hour to 2 hours. Anywhere between that, depending on the chapter, depending on the many factors, what is there in that particular subtopic and all of that. Okay, there is no fixed rule. Okay, great. There are more properties. I have put it up in the chart form. This is particularly useful for your board examination. Please go through these charts and these data points after the lecture is over. Okay, but otherwise you have got an idea of what an alpha, beta, gamma reaction is and what these particles are, along with their penetrating powers and their deflections from electric fields. Correct? Okay. Now let's talk about two things. One is fusion, one is fission. Fuse, bring together. Fission, cut, break it. So fusion and fission reactions. So when two or more elements, they feel that okay, we can be together and then I can become a more stable nucleus. That's a fusion reaction. But if there is a nucleus, it likes to be separate and make smaller nucleus to become more stable. That's a fission reaction. So a good example of fusion reaction, here it is. Observe. There is one tritium, that's the isotope of hydrogen. This is a deuterium, hydrogen's isotope. They fuse and they combine to form helium, and one neutron is left out. Conservation of the number of particles, 3 particles plus 2, totally 5 particles, fuse, okay, 4 over here, 1 here, again 5 particles. That's it. So this is a fusion reaction. They are brought together with lot of pressure and at a very high temperature together. That's what happens. There are many examples. This is just one such example what a fusion reaction is. In fission, look at this. This is such a bulky element. A neutron goes and hits it like you strike a coin in a carom board, and that's it. It breaks apart. Happens, right? Even in a pool or snooker table, all right? You hit it, all those balls get separated out. So same with this, neutron is bombarded onto that heavy nucleus. It splits into smaller daughter nuclei. Okay. Oh, is it Prem Kumar? I don't know. Maybe you should tag me or send me. Maybe give the translation also. Yes, fusion occurs in the sun, fission occurs in nuclear plant. Oh, by the way, remember, now fusion reaction is possible at a very small level. I'm pretty sure if you have seen Iron Man, he has this fusion reactor right at his chest, right? So fusion is the next level technology. When we use nuclear power plants, right, in that there is fission happening. So there is uranium is disintegrating, and then it gives you smaller elements and releases energy. So that is fission reaction. Till now, we have not been able to use fusion so well. It happens in the sun, but the day that happens, our level of energy will be next level. Right now, we are dependent on petrol. Now, slowly people are like, okay, we should use wind energy or we should use solar energy and we can use electric vehicles, not polluting and all of that. But electric vehicles, no, it's not the future. It's the fusion vehicles which are going to be the future, where you will have fusion technology, fusion reaction happening inside your car, inside your house. Just imagine there is a nuclear tiny reactor, just like Iron Man has it on his chest. You have such a reactor and it is creating energy. You don't need to fill it, you don't need to charge. Who is going to put that plug over there and charge it? Not required. You have a fusion reaction. So that's the new technology, and it was just done successfully by a lot of scientists, and I think that's going to be the future. No need of petrol, no need of anything else, no need of solar, guys. It's going to be crazy. Now, in any fusion or fission reaction, there is some energy involved, like the one over here. Look over here. Where did that problem go? This problem. This was a fusion reaction. Did you see that? 2 hydrogens meet to form helium. Energy is released. That's a fusion reaction. So you got some energy released. This energy which is released is called, or absorbed, depends what is happening, is called as the Q value of the reaction. Q value of the reaction. So guys, This is called as the Q value of the reaction, which is binding energy of product minus binding energy of the reactant. So I'm just going to put it over here. So the Q value of the reaction is basically that energy which can be either released or taken in, that is binding energy of the product side minus binding energy of the reactant side. That is what the Q value of a reaction is. If the Q value is positive, that means it releases energy. It releases energy. If it is negative, it means it takes in that energy. That's all. Okay? I hope this is clear. Very nice. Excellent. Let's do some questions based on this. In the given reaction, from this to this, this to this, this to this, which are the particles which are emitted? Alpha, beta or gamma? Come on, figure this out. Come on guys, figure this out. What's the answer? Video is blur. Why is that happening? I hope it is fine now, bacha. Also check your settings of YouTube. Option B for sure. Let's have a look whether you guys are correct. Yes, you guys are correct. Perfect, guys. I think you can see that over here. Atomic number is increasing. Obviously, it is beta reaction. Atomic number increasing. There is no change in atomic mass number. Here, atomic mass and atomic number are decreasing, so it's emission of alpha. Here, there is no change, so it is gamma. So beta, alpha, gamma. Beta, alpha, gamma. Perfecto. Perfecto. Very good. Proud of all of you guys. I think there was nobody who answered it wrong. I think there is. Oh, the moment I said, somebody answered it wrong. Yeah, guys, it is option B. Let's see if you can solve this. Binding energy of A and B are EA and EB. What is the Q value of reaction if 3 atoms of B meet to give 1 atom of A? Interesting. Interesting. Let's see. So we have 3 atoms of B. So 3 atoms of B combines to give you, fuse together to give 1 atom of A. Question is, what is the Q value? I just told you Q value is the binding energy of the product minus binding energy of the reactant. Here, what is the product? What is the reactant? Obviously, this is your product. This is your reactant. So, for the product, the binding energy will be EA, correct? It's EA, that's the product, minus binding energy of the reactant, that's EB, but there are 3 of them, so put 3 times. That's all. Do I have the answer? Yes, perfect. Amazing, guys. Very good, Sampath, Madhumita, Prem, Varsha, Deva. Come on, guys. I want to see all your names. I want to get to know you, and the more you answer and more you attend my classes, I think the name will get stuck in my memory. And others will also know you. And I will remember you when you meet me during the felicitation function. Like, oh, sir, I am Salva Kumari. Sir, I am Sampath. Sir, I am Chandana. Sir, I am Dharni. Sir, I am Murshida. Sir, I am Reena. Sir, I am Diva. Sir, I am Varsha. Sir, I am Prem. Sir, you remember I used to answer this. Sir, I told this dialogue in your chat box. And I would love to meet you guys during felicitation. You are going to become doctors, right? Or maybe someday I'll meet you somewhere in your clinic. Someday, obviously you will have a clinic or maybe a hospital, or you will be a scientist or maybe a researcher, or maybe you will teach the medical students something, and I would love to meet you guys. That will be amazing, and I will remember your names then. Alright, now let's go to the radioactive decay. Like I told you, sometimes you need to force somebody into some reaction. Like in the animations which I showed you, you had to throw one neutron, it hits the nucleus and then it disintegrates. It was a forced reaction. It was not natural. But there are some people or some nuclei where they automatically split. You don't need a trigger. You don't need any reason. They'll just split, or they'll just, undergo some reaction. That is a radioactive element. So a radioactive element like uranium-238 will split into smaller particles on its own. It does not need trigger. Thank you, Sri Harsha, means a lot. Just like I am giving you guys free education over here on YouTube. I'm so glad, bacha. Thank you so much. Means a lot. Yes, I'll post my weekly schedule. Yes, acing. Last week, like I said, I was not in town. That's why I was not sure how many lectures I would be able to take. So right now I'm back. So don't worry, I'll give you the schedule. Okay. That is a nuclear reaction. So which is radioactive, means it happens naturally, and there is a law of radioactivity. There is a law, and let's have a look at it. Just imagine this is a radioactive sample. This is a radioactive sample. It has many radioactive nuclei. It has many radioactive what? Nuclei present in it. So let's say n number of radioactive nuclei are present in it. What happens is it emits radiation. It starts decaying. It basically decays. It decays. And let's say in time dt, in some small time interval dt, few nuclei decay, they decompose, rest of them are fine, intact. Okay, so rest of them are maybe fine. So these yellow ones, those are the still active nuclei. They are not yet split, but few of them maybe over here, okay, few of them, they got decayed. So this is basically decayed. How much will decay? In dt time, obviously dn will decay. Like how your tooth decays, some black thing is there, it has decayed, rest of it is white. So this is that white part, that yellow one over here is that undecayed part. So that is still active. So still active, still radioactive, I mean, is n minus dn. Everybody agrees to this statement? Exactly, it's going to be first order kinetics, you will see that. Oh, yep. I hope too, Selva Kumari, I don't fall sick. Okay, so next point over here is that in time dt, it decayed by dn. Then the law of radioactivity states that, where did it go? That the number of nuclei, forget this, decaying per unit time is proportional to the active nuclei in the sample. The number of nuclei undergoing decay per unit time is proportional to the active nuclei in the sample. What it means is that this one, dn by dt, dn, which is the nuclei which are decaying per unit time, is proportional to the nuclei present in the sample. That means proportional to n. This constant of proportionality, oh by the way, I should put a minus sign. Why do I put a minus sign? Because it's decaying. dn will be a negative number because the change of the number will be negative. It's becoming less. So obviously it's negative. So to make it positive, I put up minus sign over here. Because dn is negative, minus into minus will make it plus positive. So for constant of proportionality is lambda, and this is basically n over here. This is the important formula, guys, which you should know. Minus dn by dt is lambda n, where this lambda is just called as the decay constant. Decay constant, and it completely depends on the nucleus. Depends on the nucleus. Like uranium will have some lambda, thorium some other lambda, carbon 14 some other lambda. It depends on that nucleus. Obviously it's a materialistic property. It is a decay constant. So this might have reminded you of first order kinetics equation which you have studied in chemistry. Is that right? Very good. Excellent. Okay. Will I take 11th classes lectures also? Yes. But first priority to 12th and then to 11th, because the exams are very close by. So important topics of 12th first, and then I'll do the important topics of 11th, and after the boards the remaining things, whatever, how much ever we can do, I will do. Okay. And see, I'm not guaranteeing you I'll do all the topics because I don't want to make fake promises, but I'll try to do as much as possible, but in the order of priority and weightage. That is very important. If I do sequentially, chapter 1, 2, 3, it's of no use because time is less. You have to think about what is coming ahead. All right. Now, I've put up all these things in the, slides also. Let's talk about activity now. What is activity? Activity is nothing but, where did it go? Yes. Activity is nothing but how many disintegrations are happening per unit time. It's basically the disintegrations per unit time. Basically, activity is nothing but dn by dt's value, modulus of that, or just put a minus sign. How many nuclei are decaying per unit time is just the activity. That's all. Simple, nothing else. So this is another thing which you must definitely know. Now there is one very interesting thing about how much element or how much sample is left after some time. There is a small derivation for that. I'll just give the important steps out of it. Like we all know, minus dn by dt is equal to lambda into n. I want to find how many nuclei are left after I wait for some time. So I don't want this derivative, I want to get rid of it. Most likely I will do integration. So bring that n over here. So minus dn by n is equal to lambda into t, correct? That's the formula. Very nice. Now I can see maybe, lambda into dt. Now I think I can do some integration over here. Yes, I can also shift that minus sign on the other side. It will be better, I feel. So I can put integration dn by n is equal to minus lambda constant integral of dt. Like, okay, fine, great. What are the limits, sir? Well, when time is 0, that means initially, there is n naught number of nuclei which are present initially. After you wait for some time, the sample left is n. So these become the limits. It should be corresponding. When this, then this. When that, then this. That's, yeah. Okay. You integrate it. So after integration, that part I'll leave it up to you. You can do it very easily. The final answer comes out to be n is equal to n naught original into e to the power minus lambda t. This is the formula. Again, obviously you are supposed to remember this formula. And guess what? You can also write a similar formula for activity. So final activity is original activity e to the power negative lambda t. E is that exponent, 2.7. Okay? So standard values. So both are important formulas, both for activity as well as the sample which is left. So n naught is initial sample, initial number of nuclei, n is after time t. That's what it stands for. Exactly. So disintegration is infinite. Actually, if you wait for a very long time only, then you will get no disintegrations further. So the disintegration keeps on happening for a very, very, very long time. I'll show you the graph in a bit. Okay, I've put up all these things over here, the units also of disintegration and all that I have put. You can watch that later on in the PDF. That is not important. Let's solve some question, and again I'll come to some remaining parts, which is half-life and all of that. A sample has some disintegration rate of 5000, okay, initially. After 5 minutes, you find it reduces to 1250 per minute. What is the decay constant? Interesting. Okay, let's do this. Guys, quickly think and tell me, what are these values? 1250, 5000, are they number or activity? Are they number or activity? Think disintegrations per unit time. It's obviously activity. So what is activity and what is initial activity? Put it up in the chat box. What is A and what is A naught? Oh, no, Satya, the A value does not come out to be equal to N. So this happens when you substitute all of that. So A is not N. Don't think like that. Sir, you replaced N with A and N naught with A naught. No. Actually speaking over here, A is nothing but dN by dt. Okay, and this over here is dn naught by dt. They are completely different things, two different things, okay? So please don't say A is n and A naught is n naught. It looks like that, but there is a derivation for that. Okay, don't get confused. Okay, oops, I think by mistake I showed the answer. Anyways, yes, so this is obviously A is nothing but 1250. Original activity was 5000 and the time is 5 minutes, and the question says decay constant, that means how much is lambda. Which formula will I use? Yes, Selva, I know I showed the answer, so maybe. So the formula that I will use is A is equal to A naught e to the power minus lambda t. A is 1250, A naught 5000, E as it is, lambda as it is, time 5. 0, 0 cancels. 125 by 500 is e raised to minus 5 lambda. I can bring that negative power below, it will become e raised to plus 5 lambda. 120 and 500 goes 4 times. 125 into 4 is 500. Flip this or cross multiply, it will become e raised to 5 lambda is equal to 4. Use logarithms. So log of 4 to the base e is 5 lambda. Log of 4, I can further write it as log of 2 square to the base e is equal to 5 lambda. Correct? Now bring that 2 outside, that's the formula of logarithms. Bring that 2 outside, so it will just become 2 log 2 to the base e is equal to 5 lambda. So lambda will be, bring 5 down, so 2 by 5 log 2 to the base e. Now 2 by 5 is 0.4, log anything to the base e is ln. ln is the shortcut for writing log to the base e. So 0.4 ln 2, which is option A, of course. That's right. Perfect. Everybody with me? Understood? So you need to know a little bit of logs. What are the different things of log that I have used? So guys, you know, log of x to the base b, if it is y, that means b raised to y is equal to x. So from this to this or this to this transformation you should know. So from this to this I have used here. And here I have used log of x raised to m is m times log of x. That is another formula that I have used over here. So this is this and this is over here. Alright, cool, very crucial. Now let's talk about half-life. Half-life. Some people you might have heard them saying, obviously none of your friends will say that, but midlife crisis. Okay, something like that. So anyways, so let's talk about what is this half-life. Now we all know, let me just draw the graph first. Okay, so we all know that the equation of the radioactive sample left after any time is given by n is equal to n naught e to the power minus lambda t, correct? That's the equation. If you draw this on n versus time graph, the graph looks somewhat like this. After a very long time, the sample becomes very small. When time value is 0, this value will be n naught. This value will be n naught. If you give me any time, at this time, what is the value of n? So I can get it graphically also or via the equation. So that is a graph of the sample present after any amount of time. Exponentially decaying graph. So it's also called as exponential decay. Exponential decay graph. Exponential because e power, decay because it is reducing. Now, if I ask you, at what time will the sample become half? So basically, when will it become n naught by 2? That time is called as the half-life of that sample, and that half-life is ln2 by lambda. Very important formula. ln2 by lambda is the half-life of any radioactive element. As simple as that. Yes, you can put the value of log of 2 as 0.69 approximately. That can simplify your calculations as well. Okay, bacha log, everybody clear about this? Very good. Now there is another thing which you would have heard, and that is basically average life. And you would have wondered, what is this average life? Okay, I'll tell you what is this average life. Imagine that you have a radioactive sample and it has radioactive elements. One of the element stays alive for some time and then it decays over here. It is alive, meaning it is basically active. It is active or it is alive. Another element stays alive only for this much time and it decays. Another element stays alive for a very long time and decays. Another atom stays alive for decent time and decays. So every element will stay alive for some time and then it decays. It's just like average life expectancy, mean life. So that is what average life is. So the average life is the time for which it stays alive. The second element, how much time it stays alive. You add all of them for all the elements present and divide it by n. That will give you the average life. Now this average life turns out to be just 1 by lambda. So that calculation part is not there for you. Don't worry. But main thing is there is no log 2. If you put log 2, what will it become? Average life? No, half life. So if you put log 2 on the top, it will become half life. If there is no log 2, if it is just 1 by lambda, it becomes average life. Okay? Clear? Understood? Very good. Let's do a question based on this. The half-life of a sample which has 1/32th of the original mass left after 60 days is how much? After 60 days, only 1/32th is left. What is the half-life of that sample? Come on, my warriors, figure this out a bit. What is the answer for this question? Well, if I give you the logic behind this, if the original mass was m, then after the first half-life, m by 2 will be left. Correct? After one more half-life, that means the second half-life, half of m by 2 will be left. After the third half-life, m by 2 into 1 by 2 into half of that is what is left. So like this, if you keep doing it, and after nth half-life, how much will be left? If it is asked, it will be m, and here you will have 2 raised to n. Correct, guys? M by 2 raised to n, that much will be left. Here 1/32th is left. That means 1 by 32 is 1 by 2 raised to n. Is that right, guys? 1 by 32 is 1 by 2 raised to n. Correcto? Great. So 32 is 2 raised to n. Therefore n is equal to 5. 2 into 2 into 2, 5 times is 32. So basically 5 half lives give you 60 days. So 1 half life will be how much? 60 by 5. 5 lives, 60 days. 1 life, 60 by 5 days. So that is 12 days of course. That's the answer. Simple logic. Option A, of course. Yes. Perfect. Many of you got the correct answer. Now, what semiconductor is? Okay, if you talk about the crude definition, semiconductor is something which has the conductivity or resistivity or resistance somewhere between the conductors and insulators. So somewhere in between. It's not as conducting as the conductor. It's not as bad as a insulator. Somewhere in between. But these semiconductors have a very unique property, and that is the resistance changes with voltage. Usually, if you have a resistor, basically a conductor, then the resistance is constant no matter how much voltage you apply. But the property of a semiconductor is the resistance varies with voltage. In fact, it is a non-ohmic device. I hope you guys remember Ohm's law. Are you writing this down? It's a non-ohmic device. That means it does not follow Ohm's law. Voltage is not proportional to the current. Alright, so keep this in mind. Okay, so let me just see if this is okay. Is this fine, Prem? I hope the screen brightness and everything is fine now. Okay, great. We are done with nuclear physics, Harshini, last lecture. Okay, now if you have written down all these pointers about semiconductors, so probably I'll just mention it over here itself. So first thing is that semiconductors, okay, if I talk about the resistance of the semiconductor, it is basically more than the resistance of a conductor, but it is less than the resistance of an insulator, or you can take the reverse for conductivity or conduction. Also, they don't obey Ohm's law, so non-ohmic devices. You can also say voltage decides the resistance, and also these two together decide the current. Okay, so resistance is not constant. That is the important thing. It is not a constant. I hope you have written down all these things, but anyways, you will be getting the PDF later on as well. Now, how does the semiconductor work? What's exactly going to happen? Let's quickly go through the atomic level description and concepts. If you take any element, let's say for example sodium, okay, there are 2 electrons in its first shell, then there are 6 electrons over here, and then there are 2 more, there is 1 more electron in its outermost shell. Correct? Great. Now, if you take such an atom or such an element and you show the energies, remember each electron has different energy. Electrons which are close to the nucleus have low energy, ground state. If you go to higher orbits, higher shells, the energy grows higher and higher. Everybody agrees with it? Non-ohmic means voltage is not proportional to current. Amido, Avogadro, wow, what a name. It is not proportional to the current. That is the meaning of non-ohmic, which does not follow Ohm's law. Okay. The PYQ of atom and duality for J is a different channel, bacha. That will be happening very soon. Don't worry. That will be happening in the next week. Great. So if you look at the energy levels, it looks something like this. 1s, very low energy. 2s, 2 electrons, and then 2p, 6 electrons, it has slightly higher energy. 3s, the highest energy. What are these arrow marks showing? They are showing those electrons in those orbitals. Plus half, minus half. Spins are there. They are forming pairs. Pairs are being formed. Here, papa, that is single. This is couple. This is single. This is like lone wolf out there. Correct? Now, this is how the energy level looks like for a single atom. But what happens? What happens if you have multiple sodium atoms in a solid? Isolated sodium atom, this is the energy level. What if multiple atoms are there? Each atom, you might think, sir, this will be the energy level of those individual atoms. But actually what happens when they are in a solid? When they are in a solid, then they will interact with each other. What happens? They will interact with each other. Acing, I'm feeling cold, that's why I'm wearing this jacket. So they will interact with each other. And they will form new energy levels. Instead of one line for 1s, there will be, if there are 3 atoms, there will be 3 lines. If there was one atom which had 2s energy level, if there are 3 atoms, there will be 3 lines for the 2s energy level. Because there are 3 atoms interacting, so 3 lines for each orbital have come. Do you see like splitting has happened? Everybody give me a thumbs up if you got this. The atoms interacted, they formed new energy levels because they interacted with each other. Give me a thumbs up quickly in the chat box. Everyone. Yes, very good, GV. Excellent. Come on guys, mark your attendance. How do I know you guys are here paying attention to Shreyas sir? Excellent. What if there are even more atoms? Okay, you only answer in the chat box. Let's see how smart you are. If there are 20 atoms interacting with each other, how many lines will be there, guys? If 20 atoms are interacting with each other, each of these things will have how many lines? How many lines? Exactly 20 lines. Perfect. Okay. Now, do you see 3p shell? 3p shell, that is empty, right? So it is empty here also. It is empty here, it will be empty here. Electrons can jump, but right now it is empty energy level. So when there are multiple atoms, there will be so many lines. Can you see those lines? Imagine 100 atoms are there. 100 lines will be there. They will be so close to each other, na? They will be so close to each other. If there are so many lines close to each other, can you see them clearly? Na. You will be like, oh, na. I am like, na. Okay, very bad PJ guys. Anyways, okay, please don't laugh. If you laugh, I will feel that you guys understand my PJ then. Anyways, okay, so if there are so many lines, then it will become so indistinguishable. You cannot distinguish them that you call it as a band. What do you call? Band. Perfect Vijay, perfect GV. So this is energy band of 1s. This is energy band of 2s. This is energy band of 2p. There will be energy band of 3s. There will be energy band of 3p, and so on and so forth. Very nice. Now, what does this band got to do with anything? What has this band got to do with anything? Yes, it obviously Devon Corona. Corona in China, Corona in India, same row. Same Corona. Very good. Excellent. Now, what has these bands got to do? Okay, I'll tell you what. See, those bands which are completely full, like in this case, which were the complete bands? 1s band full, 2s band full, 2p band full. These bands, they are called valence bands. What are they called? Valence bands. But these bands which are empty or partially filled, those are called unfilled bands. They are basically conduction bands. What are these unfilled bands called as? Conduction bands. So all those bands which are not filled are there on the top. All those bands which are filled, they are basically at the bottom. They are called as valence band. Now, what happens is that when you apply your battery, when you connect a battery to such a solid, like you have sodium solid over here, you connect a battery to it. The battery will give voltage, electric field that will pluck those electrons. It will pluck those electrons and it will push them into conduction. If those electrons are in the conduction band, easily they can flow. Conduction because they are not filled. So atoms, either they are stable when the pairing is formed, or they are completely empty. So these electrons can be easily plucked. If you ask this electron to come out, you'll be like, no, I have a husband or I have a wife. I'm not going to come. This, if you ask, hey, come man, let's go out. This has a boyfriend, Pandu Champa. I'll be like, no man, I can't come. Sorry, I have a girlfriend, I can't come. This, hey, come man for party. Oh, it's okay, I'm single only, I'll come. So that's why they're conduction electrons. Understood? Oh? They are conduction electrons, single people. Here the no people only are there. If this electron jumps here, it will be like, what is the use? If I stay here also, I'm single only. Like, I'll just move. So that's what happens in the conduction bands, guys. So now another interesting thing over here is that if the electrons are there in the conduction band, it is going to help in the conduction, but you might have to make the electrons jump from the valence band to the conduction band in case this was empty. Maybe there is no single person. You go and ask, is there anybody for party? Oh, couple here, couple there, Pandu Champa. Nobody is there for me to party. Then deliberately, zabardasti, by force, you pluck out one Pandu, you pluck out one Champa, you pluck out one electron from here and you push them over there in conduction band. You basically break them up. You break their pairings up. You break them up. You create a breakup over there. That's it, guys. You need some force, you need some energy. So from going from valence band to the conduction band, you need to give some energy. You need to put in some effort. So that effort is given by that band gap. Band gap tells you the minimum energy an electron requires to go from the valence band to the conduction band. Minimum energy required to go from the valence band to the conduction band. Is that clear? Everyone with me on this? So energy levels are discrete, okay, between the highest occupied and the lowest unoccupied levels. Let me just show this to you over here. Highest occupied means this one. This is highest occupied. If you talk about the unoccupied lowest level, that is this one. So the energies are different, they are close to each other, but there is some gap. That band gap is the minimum energy. Now, this energy bands and band gaps, etc., are always given to you at 0 Kelvin. This is given to you at 0 Kelvin. 0 Kelvin, lowest, coldest temperature. I'll have to put in 100 jackets if the temperature was 0 Kelvin. What happens when there is temperature? 300 Kelvin, 200 Kelvin, 250 Kelvin, 270 Kelvin. These atoms will vibrate. Dug, 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 dug. They will vibrate. They'll say vibrate, right? And they vibrate. What will happen? When they vibrate, think, imagine what is going to happen. These atoms which are there, they will collide. And who is most vulnerable? Who is most vulnerable? These people. These people, because they are on the outer shell. They might get knocked out. They might get excited to the higher energies. Yes or no? Vulnerable people, outer shells. They are on the periphery. They are on the border. So they are vulnerable. So they will get affected. And because they will get affected, they will get energy because of the collisions, because the temperature is there, vibrations, kinetic energy, rotational energy. They will jump from valence band to conduction band. Yes. The moment valence electron moves to the conduction band, it becomes conducting. It becomes conducting. Great. So it is possible that an element may not have anything over here, at low temperatures, but as the temperature goes up, they will go into the conduction band and they might become conducting in nature. Great. Remember, no electron can stay here or here or here. It's like you stay here or you stay here. You stay here or you stay here. If you stay here, you will fall down. Not allowed. Stay here or stay here. Like it happens, no, from one period to next period. Teacher will tell, okay, sit in this class or sit in that class. Don't roam around in the corridor. So this is that corridor. You cannot. Forbidden. Do you see this? This is forbidden energy. This is forbidden energy. You cannot stay over here. Singles were vulnerable. Even some of the couples were vulnerable, Prem Kumar. Even some of the couples will be vulnerable. What if there is no single? If these doubles only are exposed. Police mama comes, police inspector comes. Police inspector comes and he is like, come on, out, out, out. Who will get out first? These people. These people are inside. They are deep inside. First, these people will get caught. Okay. Keep this in mind. Okay. Great. Singles so will pakka get caught, but doubles also. Okay. Couples. All right. Great. So now, having said this, what has this got to do with, conductors, semiconductors, or even insulators? Okay. So here is the thing, guys. If this energy difference is very large from valence to conduction, even if you give it thermal energy, even if you shake it, hey, wake up, wake up, wake up, wake up, just like your mom wakes up, wake up, wake up, wake up. No, your band gap, your forbidden zone is so large. From sleeping to awaken, it's a lot of energy. You are like this only. Wake up, wake up, wake up. Nobody is waking up. That's it. You will not go into conduction band. In that case, you are an insulator. Doesn't go. No matter how much energy you give, it doesn't go. Electron only. Push, it will go like this and it will come back. It will go like this, come back. It will go like this, come back. Okay, got it? Very good. If it is semiconductor, you wake up like this. You wake up like this. Okay, what happened? Okay, where? So, little bit of temperature, the electrons jump into the conduction band. So, small conduction is there. Some electrons are there in the conduction band, so conductivity is there. So, that's why semiconductor. Some electrons are reaching. Band gap is typically of the order of 1 to 2 electron volt. Okay, 1 to 2 electron volt. Sometimes, best things can happen here. There is no band gap only. There is no band gap only. Some people, have you seen them? They sleep with their eyes awake in the period. Like this they will be. You don't know whether they are sleeping. And sometimes when they are sleeping, their eyes are open. It is so scary to look at those people. You don't know whether they are sleeping or whether they are awake. Just like virus, you don't know whether it's alive or dead. Same way, if the conduction band overlaps with the valence band, it's like, I can go here also, I can go here also. Oh, I'm dead, oh, I'm alive, oh, I'm awake, oh, I'm asleep. Ah, very nice. So that is a conductor, guys. That is a conductor. Prem Kumar sleeps with his eyes wide open. Very good, Prem Kumar. That is what conductor is. Understood the difference? Simple, no? No difficulty here. Very good. Excellent. Now, in the semiconductor, what happens? Yes, Sampath Kumar is also demonstrating to us using some emojis. Thank you, Sampath. Sampath, representing emojis, representing conductors using emojis. Very good. I like your talent, guys. So, this over here, this forbidden energy, this band gap from conduction to valence or valence to conduction, it's typically, like I was telling you, somewhere close to 1 electron volt. If the energy gap is 5, 6 electron volt, pakka, gone. It is an insulator. Okay, pakka, it is going to be an insulator. Very, very important things. So this is going to be always at absolute zero temperature. So there is no electron at, absolute zero temperature. But as you give some temperature, so you will see the electrons gain energy and overcome this energy gap, forbidden energy gap, and they enter the conduction zone. That's what a semiconductor is. Very, very important. Now, that we have spoken about semiconductors, okay, which have conductivity between insulators and conductors. There are two types of semiconductors also. Wow, this is crazy. There are two types of semiconductors, huh, sir? Yes, there are. One is called intrinsic, second is called extrinsic. Intrinsic means because of its nature, because of its make, automatically it is its internal property. Intrinsic, internal, because the way it is. Correct? Okay. This one, external, extrinsic. You do something, you poke him. Hey, come on, do something. You also get poked, no? You also get poked, yes. Luxury Hitler, wow, what names, yeah? From where do you get such names? That external factor also can be of two types, P type and N type. The moment you hear this word P and N, what is the first thing that comes to your mind? P, N, charges, positive, negative, exactly what it is. P, like positive, it's not exactly positive, but just keep in mind, it's like positive, and N is just like negative. There is some negative element in it, P has some positive element in it. So this is the flow chart, this is the chart which will help you remember the different types of semiconductor. Okay. Now, all the properties of whatever I have talked about semiconductors, I have mentioned it on this slide. This will be available to you in the PDF also. Okay. Yes. Okay. So you will be getting this. All the pointers, whatever I have given. Okay, you can read through it later on. I don't want to go through it now. First, let's have a look at one question which is coming up on your screen. Which of the following is correct? Forbidden energy gap is the gap between valence band and conduction band. I think one or more options might be correct. Are correct? Come on, guys, figure this out. What do you think? So I got it when my newspaper it torn apart. Oh my God, why was your newspaper torn apart? Forbidden energy gap may be empty or may have partially filled with electrons. No electron can exist in the forbidden energy gap. Bands cannot overlap with each other. What do you think? Okay. A and C says Madhumita. Prem also says A and C. You guys are correct, yeah. Perfecto. Forbidden energy gap is the gap exactly between the valence band and the conduction band. So this gap which is there, that is basically your forbidden. Obviously the electron can either stay here or it can stay here. It cannot lie in between. Correct. It is definitely the forbidden gap. Exactly. Moving on now to the next question. Semiconductor at 0 Kelvin behaves like 0 Kelvin, the lowest, coldest temperature. What does it behave like? Thank you, Archini, for putting that C for Capto. Excellent. Every time you answer C, you should always think of C for Captain Shreyas. Okay, Priya says A, KP Bharat says, Vikram says A. Oh, we have Vikram, we might also have Veda somewhere. Okay, A for Capto. Okay, A for Ames actually. Alright, very good. Answer is A, insulator, correct. Because whatever bands we draw, the conduction band and the valence band, the electrons are here at 0 Kelvin. The electrons reach here at room temperature, because at 0 Kelvin they are in the valence band, there is nothing in the conduction band. That means it is going to be an insulator. It is going to be an insulator. At room temperature, it becomes a semiconductor. It becomes a semiconductor. Very good. Excellent. Very nice. Perfecto. Now let's talk about both the types of semiconductor. One is intrinsic, internal. Second is extrinsic, which is external. How do these semiconductors exactly behave? What makes it different? So in the purest of the purest form, when nothing adulteration, there is no adulteration. I hope you understand the word adulteration. You have not mixed anything. Like when you get milk, some people put water in it. It is adulterated then, correct? So if you get the purest of the purest form, then it is called intrinsic semiconductor. The best examples of semiconductors like that are silicon and germanium. These are the two most commonly used semiconductors. Now, if you know the atomic structure, you know that there are 4 valence electrons in either germanium, silicon, or even carbon-like atoms. And we know, just like carbon can form 4 bonds, even silicon or even germanium, because they have 4 valence electrons, they can form 4. What kind of bonds are these? Are they covalent or are they ionic? Are these covalent or are they ionic? Come on guys, you know organic chemistry. Definitely they are covalent bonds. Yes, Prem Kumar, just like 24, nice, carat gold. Very good. Now you can see these electrons are getting shared, and there can be an infinite chain like that. There can be an infinite chain like that. Like this might form a bond here, that might form a bond here, this might form a bond here, this might form a bond here. A big chain can form of such silicon or germanium atoms. Now when you have such a big structure, of covalent bonds, things can definitely go wrong. Okay, I'll tell you what can go wrong. Okay, observe now carefully. Let me just probably mark it over here only. Imagine that this is one atom, this is one atom, this is one atom, this is one atom, this is an atom, this is an atom, this is an atom, done. So many atoms are there like that. Okay, I'm just showing few of them. Okay, each of them are sharing basically electrons, between them. Now let's say these are all like your neighbors, neighboring aunties. Your auntie, this auntie, that auntie, so many aunties are there in the neighborhood, in the society. They are forming covalent bonds like this. I know I should draw a double line, but just ignore that for now. Each blue line corresponds to sharing 2 electrons. Just visualize it that way. Now just imagine there is friction between them. There is energy, thermal energy. What will happen when there is thermal energy? The bonds will get broken, yes or no? Imagine there is shaking, there is movement, there is kinetic energy, there is rotation, there is twisting. These bonds will get broken, yes or no? Exactly. So at some temperature, maybe this bond just gets broken. The moment the bond gets broken, what happens? 2 aunties fight. It might have happened in your society also. 2 aunties fight. What will they do? Your mom will say, hey, listen, you don't talk to that auntie and her kid. Come here. And that another auntie will say, you listen, you don't talk to that woman, don't talk to that kid over there. Bring this kid over here. That's it. So the 2 kids over here are electrons. Who are these 2 kids? Electrons. Understood? Yes or no? Papa, these 2 kids were playing cricket with each other. These 2 aunties fought because of thermal energy. Gone. These 2 kids are now back to their aunties. Very nice. Now what will happen? These electrons are now free. Papa, these kids will now start roaming around. This kid will start roaming around. Somewhere else, some other 2 aunties have fought. Maybe these 2 aunties. Now this kid will start roaming somewhere. This kid or this electron will start roaming somewhere. Understood? Yes or no? Very good. The moment the electron leaves, what has happened is the kid is like, Mommy, why? I don't want to fight. I am leaving the house. Gone. The kid went off. There is a vacancy. The kid left the house. There is a vacancy. That vacancy is called as hole. vacancy, hole. There is a hole, void left. So the moment that kid has gone, left the place, okay, so what is left over there is a hole. I'll just put it in a different color maybe. There is a hole created, hole. Okay, so this electron went here, this electron went here. So these green ones are nothing but the holes. Okay, now as these electrons roam around, suddenly maybe this electron which is roaming around like this, it will find a vacancy. What will it do? It will go fill it up. Maybe some other electron roaming around somewhere, from somewhere might just fill this hole. It's like your mom found a new cousin. Oh, my kid left me. It's okay, one cousin came. This auntie also found one cousin. Now these two people become friends. Understood? These two people become friends. Crazy, no? Look at the relationship, guys. This is all what is happening in atoms. You thought only you people fight? Look at these atoms fighting like dogs and cats. You go there, I go here, you find a bond, you don't stay with me, I leave you, void is created. So they are fighting like cats and dogs. Bond will be again made over there. So they fill the hole. This is filling the hole. This is also basically filling the hole. And again a bond is formed. Somewhere else a bond is broken, somewhere else a bond is formed. Somewhere bond is broken, somewhere else the bond is made. This is happening continuously. Okay, you cannot stop. So that is what is there in the next diagram. I want you to see it. It might look intimidating initially, but that is exactly the love story, the relationship story which is happening here. You can see bond is broken. Dotted line means bond is broken. Electrons got free. Vacant electron means hole. You can see vacant electron mean hole. That electron will go somewhere. And fills somewhere else. It will fill the void somewhere else. This void will be filled by some other electron. That void will be filled by some other electron. That electron will go fill somebody else's hole. That's what is going to happen. Okay. Now, when basically all these things are happening, you should also understand holes are created in the valence band. Where are the holes created? I am repeating. Where are the holes created? That's a vacancy in the valence band, because thermal energy has broken the bonds and pushed these electrons into the conduction band. So the free electrons were the ones in pink. Look at this, free electrons. Those free electrons are in the conduction band. From valence band, they jumped into the conduction band. Clear till this point? Okay, very nice. Now, if you understood it till here, let's now go to extrinsic semiconductor. Sir, when is the class of JV? Praveen, I will let you know on the JE channel, bacha. Let's concentrate on this channel now. Okay. Natasha, will. Yeah, I have given you that also. Yes, others. Looks like you were there in the JE channel. Now, this flow of electrons is completely dependent on germanium. But I can create some spicy environment like it happens in reality show. Suddenly there is a new contestant, or suddenly something changes in the serial or in the movie, a new villain or a new hero comes and entire dynamics change. So that is what is going to happen in the next episode. That means now only, don't worry. So we are going to do something externally. We are going to add some impurities. We are going to add some country fellow. We are going to add some villain or some hero who is going to change the entire dynamics of that society. Twist will be there. Now what is the twist? There are two types of things which we can do. P type, positive, you can call it him like the hero, and N type, negative. Okay, you can also call him like the villain. Or you can also think N is like one attractive girl who has entered the society, and P is like one boy who just wants one girlfriend. Okay, P is like one boy who wants a girlfriend, and N is like one very attractive girl in that society. So let's see what is going to happen. Let's start with N type. Are you guys ready? Just light up the chat box. Yeah, ready to see the twist? I'm pretty sure you have not seen semiconductors like this before. You would have seen it in a very boring way, and you would have slept off even before you reach P and N type of semiconductor. Is the number of electrons equal to the number of holes? I'm going to come to that, Sadarshan, but yes, they are. But not in all the cases. Not in all the cases. Okay. Now, what you do is you add N-type material in that big crystal or big compound, or that entire solid. When I say N-type of material, that means, look over here. All these were having 4 valencies, 4 valence electrons. 1, 2, 3, 4. What if there was one extra electron here? That is called as pentavalent. So there is one extra electron. This guy will form a bond here. 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 Oh, there is one extra electron. Like, imagine an auntie having 4 kids. One kid, you play with him. One kid, you play there. One kid, you play there. One kid, imagine these days having 4 kids, okay? One kid, you play there. Now, 5th kid also comes. This auntie has 5th kid. Extra electron. Now, that kid is going to change everything. He will be like, whom do I go play with? These 2 are playing, these 2 are playing, these 2 are playing, these 2 are playing. I will find somebody who has their bonds broken. Oh, their bonds are broken. Zoop, it will go and it will fill up that hole. And not just 1 or 2, but there will be many such pentavalent impurities that will have that extra electron. These electrons will go zoom, find those extra holes, or just find the holes in their neighborhood, and they will go and fill it. The moment they go fill it, that kid will be like, what the hell? You took my place. I just left it, man. Like, sorry boss, I am the new member in this society. I just filled this hole. You do whatever you want. I don't care. Now, Papa, this electron which was staying there, now it will go. It is like musical chairs, guys. Musical chair, everybody has played, no? Like, the chairs are the holes and that extra person is the electron. You will be like, where do I go? Where do I go? No, there is a bond broken. It will go running and fill that up. And that electron will be like, hey, you took my chair, you took my hole, now where do I go? Now it will go searching. So this musical chair will continue. This musical chair will continue. So when you add a pentavalent impurity then to the pure semiconductor crystal, you will see it is called as the N-type because of the extra electron, negative charge. Negative charge. Correcto? Very good. Amazing. So you can see how the dynamics change. Look at this. Extra electron, guys. This is that extra kid. Okay, this is like that extra kid out there. This is going to form a bond. Oh, breakup happened. This N, Natasha, attractive girl, she's going to come here. Like, okay, you can be my boyfriend. Now that guy will be like, okay, I have to find a new girlfriend. That keeps happening over here. Okay. Now, if you look at the energy diagram, there is one interesting thing which is going to happen, guys. Look at this, valence band. We all know there is a hole created in valence band. We know in the conduction band, the electron jumps, right? From the hole, it jumps, right? From the hole, it jumps. When you create N-type, this extra electron which is there, this actually comes up over here. This actually, basically, you will see there is one extra electron which is going to be in the conduction band. And you can also think of it this way. There is one extra energy level, extra conduction level which is created, which basically lowers the gap. Adding this extra electron lowers the conduction energy band to a smaller level, so the gap which was larger will now be reduced. That means it is now easier to make the jump. It is easier to make the transition. So you will see the conductivity will go up significantly. Earlier you had to jump from here to here. That extra electron will create an extra layer of conduction band which will make it easier to jump. Obviously you don't want to jump so much, you just want to jump this much. Exactly. Awesome. I hope this much is clear. Oops, what did I just do? Oh my god, just one second. Okay, I hope it is there. Yes, it is there. Now, I will ask you one simple question, and I have seen this many times, people get this wrong. Is the N-type semiconductor positively charged? negatively charged or neutral? Answer in the chat box, spam it. Come on. Is a N-type semiconductor positive, negative or neutral? Quickly answer in the chat box. Bharat says neutral, Prem says negative. What about others? Aishwarya says negative, Hamsini says negative, Harshini also says negative, Vijay says negative, Navya says negative, Dharun, Anger Queen, everybody says negative. Guys, everybody gets negative marks. Most of you get negative marks. I think only one person gets positive marks. That is KP Bharat, Vikram. Very good, Bharat. It is neutral. Mind blown, na? Like, what, sir? I thought, sir, in school they told electron negative charge. What is this you are telling? It is neutral. It is neutral, guys. Why is it neutral? Think carefully. I know this is extra electron, but did you forget that there is an extra positive charge in the nucleus? Understood? See, when germanium was there, 4 electrons are here. There are 4 equivalent positive charge in the nucleus, no? When you have a pentavalent impurity, extra electron is there, but that is extra for the bonds. For the atom, it is neutral. Atom is neutral only because there is an extra positive charge also. Understood, everyone? So it is actually neutral. It's an excess electron for making the bonds. Mind blown, everyone? Very good. But you will see that if you compare the number of electrons versus the holes, because this electron is excess in number. This electron is excess in number as compared to holes, because like musical chair, it's like musical chair, everybody agrees. So you will see the number of electrons is much larger than the number of holes. Number of electrons is larger than number of holes. Holes are like chairs, electrons are like the people. But in case of intrinsic semiconductor, one can say the number of electrons is equal to the number of holes. The concentration is same. It is definitely going to be the same. Keep this in mind. Now, can you guys quickly think for p-type, what will be the case? P-type, what will be the speciality? What will be the speciality of p-type? P positive, one less electron. It's like having more chairs than the people. It's like you have 5 people and you have 7 chairs. These 5 people like, what is this? Is this called a musical chair? It's like the chairs are now fighting for the people. The chair is like, hey, come, please sit on me. That other chair, hey, no, please, come sit over me. It's the reverse of the musical chair. Okay, crazy, right? Trivalent, very good. More holes, you can see one extra hole. One, it's like that auntie who has 3 kids. One kid play here, one kid play there, another kid play there. No kid here. That auntie is like, hey, you have a kid, I can send my kid. No kid, sorry. Okay. No kid, vacancy. What will this auntie do? Oh, you come here, you electron, come here, come, play with that kid. Play with that kid. So that electron will come running. There the bond is broken. So the conductivity increases because of the holes. Because of the trivalent impurity. Because of the trivalent impurity. Understood, na? Simple. Very good, very good. Excellent. Awesomeness, guys. Great. Very nice. Now, let's look at the energy levels also. Let's look at the energy levels. So in the p-type, you add trivalent impurities like this. You can see there is one extra hole here. When you create that extra hole, what happens is the valence band energy level goes up. The valence band gets an extra layer of energy. So the band gap reduces not from the top but from the bottom. Remember in N-type what used to happen? The band gap reduced from the top. So this was the gap, it reduced from the top. Here the band gap reduces from the bottom. So the jump becomes easier because of the hole. Where is the hole? Hole is always in the valence band, remember that. So if the hole is in the valence band and extra holes are created, that extra hole creates an extra layer of energy in the valence band, reducing the band gap, creating more conduction. And over here, you will see that the number of holes concentration is much larger than the electrons. It's like having more chairs and less number of people, and the chairs are now fighting for the people. Exactly. Oh my God, Harshini, salute. Thank you very much. That is a perfect name for the chapter. It is called Aunties and Kids, Love Story by Shreyas sir. Very good. Now, there are certain formulas which you are supposed to know. There are certain formulas which are supposed to know. So, believe me, these electron and hole concentration are related to each other. They are related to each other. And what is the relationship between them? The relationship is like this. If I have the number of electrons in any semiconductor, intrinsic, extrinsic, whatever, p-type, n-type, you multiply it with the number of holes. You multiply it with the number of holes. Then what you get is the number of electrons or holes in intrinsic semiconductor. If you recollect over here, in the intrinsic semiconductors, Ne is equal to Nh, which is equal to Ni. But if one goes up, the other must go down. If this goes up, this must go down. So what happens over here is that you will get, let me just show this to you. Yes, this will be number of charge carriers in an intrinsic semiconductor whole square. This is the formula. Ne into Nh is Ni square. This is basically the charge concentration in the intrinsic semiconductor. This is the charge concentration in the intrinsic semiconductor. Very, very important. So you can clearly see that if electrons go up, holes goes down. If electrons comes down, holes go up. That's the logic behind this. Last important thing over here before we go to the next part is that the conductivity of a semiconductor is going to happen because of two reasons. You will see electrons going one way and holes coming the other way. Electrons going the one way and holes going the other way, meaning something like this. If there is a hole is nothing but like a positive charge, vacancy, deficiency of a electron. If holes go like this, then you will see that the electrons, the free electrons, go like this inside the conductor, because of which the current will go towards the left side or right side, or no current. Come on, answer in the chat box. If holes go like this, electrons go like this, which direction will the current go? Right, left, or not go? Answer in the chat box. I want to see how many of you are going to answer this correctly. Thank you, Vijay. Right side, very good. Positive charge is going that side. If electrons go left, conventional current goes towards the right side. Perfecto, guys. You guys are too good, yeah. Too good. Very good. You guys play along with me. Very good. So the current goes this way. In a normal conductor, tell me, normal conductor, why does the current flow? Because of electrons or because of holes? Or both? In a normal conductor, the flow of current is only because of electrons. Correct? That's what you have studied in current electricity. Electrons flow, that's why electricity flows. But in semiconductor, electrons are flowing only, but holes are also going. That's why the flow happens. Hence, the conductivity of a semiconductor is the conductivity of the holes plus the conductivity of the electrons, both of the electrons. And the conductivity formula is given by mobility into number of charge carriers per unit volume into the charge. So it will be mu h nh into the charge of the holes, which is E. Okay, what is mu? I'll come to it. Mu is basically called as the mobility, which is nothing but the drift speed upon the electric field below. Okay, upon the electric field below. So that is called as the mobility of the charge carriers. Mu, drift speed, the speed with which the charges move upon how much electric field you apply to cause that motion. That is what it is. Okay. Now over here, what will you put? Mobility of electrons into number of electrons into the charge. So this is the formula for the conductivity of the semiconductor. Very, very crucial, guys. Very, very crucial. And also this is the formula of mobility which you have studied back in the day when you learned current electricity. All these are important things. Okay, everyone? So conduction happens because of electrons also and holes also. Both their conductivities need to be added. Mu is mobility, which is drift speed per field. N is the concentration, and E is the charge of an electron or a proton, which is 1.6 into 10 to the power minus 19. If you want, I'll put that also over here. E is nothing but your 1.6 into 10 to the power minus 19 coulomb. Usually, who will be more? Mu H and mu E. Who will be more? If you compare mobility of electrons and mobility of holes, who will be more? Answer in the chat box. Charge with the sign or magnitude? Only with the sign. Only with the magnitude. So this is exactly with the magnitude only. Don't put sign because it has been already accounted for. Only magnitude. Electron will have higher mobility. Correct. Holes are very difficult to move. Electrons can move easily. Vacancies are very difficult to be filled. Holes are very difficult. They shift with great difficulty. Okay, very good, guys. Excellent. Now let's go ahead and basically, yes, this was exactly an animation to show you how this works. Just have a look at this animation, the way the electrons are moving. The way the electrons are moving. Look at this. You have applied an voltage. You can see the electrons are going there towards the positive charge. And you can see the vacancies which are created. The vacancies slowly shift from here to here. Vacancy is created here. Slowly that vacancy will shift here somewhere. So the vacancies keep shifting this way. The electrons will keep moving the other way. So this is just a small animation, but I'm pretty sure you have visualized this with aunties and kids. In a pure silicon, which has intrinsic concentration of 10 to the power 16, the crystal at 300 Kelvin, 10 to the power 21 atoms of phosphorus are added per cubic meter. Then the whole concentration will be phosphorus. This is pentavalent. This is pentavalent. If it is pentavalent, that means there is an extra electron. Hence, that will create the electron concentration to exactly 10 to the power 21. Extra electrons are there. Come on. Okay. Let's have a look at the formula and use it over here. We know Ne into NH is equal to intrinsic concentrations square. Ne is 10 to the power 21. NH I need to find. Ni is clearly 10 to the power 16 whole square, which is going to be 10 to the power 32. So NH, bring this guy down, so it will be 10 to the power 21. So NH will be nothing but 10 to the power 11. That is the final answer. 10 to the power 11. Very nice. That's the correct one. Option C. Okay. Anant, learn the transistors today. I know transistors you are getting scared, but I'm going to teach you transistors also today. Okay. Don't worry. Attend this class. Guys, I'm telling you, 4 marks in your pocket because you are going to attend my 2.5 hour class today. I don't know. It might be more. Hopefully, we'll try to complete as much as possible. Let's go now to PN junction. What is this PN junction? P type, N type. Interesting. Imagine one society where there are aunties which have 3 kids mainly. Okay, few aunties have 4 kids, but some aunties have 3 kids. Neighboring society, there are aunties with 1 extra kids, matlab 5 kids. Many aunties are there with 5 kids, some aunties are there with 4 kids. Imagine both these societies are next to each other. Tell me guys, what is cooking in your mind now? There is one society where each house, each auntie has 4 kids or 5 kids. Another society where each auntie has 4 kids or 3 kids. One society more kids, one society less kids. This society, these aunties need kids to play around. Basically, holes are there, that means p-type. And the other side, n-type, that means more electrons are there. They are looking for holes. Electrons are going to jump onto the holes, right? Correct? Electrons are going to jump, right? Immediately. Aunties call the extra electron, aunties will be happy. Yes, you will be like, sir, it is a win-win situation. But that is what creates the problem. Like, sir, can't all the kids go, sir? Can't all the kids go and, play, and they can form bonds, they can make friends? That is what you are thinking, but something else is in store. There is a twist, guys. So p-n junction is formed by placing, p-type and n-type close to each other. So one side you dope it with p-type, that is trivalent. The other side you dope it with n-type, that is pentavalent impurities. You can see p-type has many holes as compared to electrons. Hole concentration is more as compared to electron concentration. In n-type, the electron concentration is more as compared to the holes type. Now you can obviously guess the electrons are going to immediately jump from here to here. That's what is going to happen, but that itself creates a problem. See what is going to happen now. Okay, oops, yes, over here. Now I'm going to show this to you. There is going to be a very good war fight which is going to happen, and I want you to see this. So this is n-type, this is p-type. Okay, n-type, p-type. Everybody with me? The moment these electrons jump, these electrons try to go and basically form bonds, make new friends over here, there comes a problem. I had told you p-type and n-type are neutral. There is no net charge, neutral, correct? But the moment the n-type loses the electron, what will be the charge on the n-type? Answer in the chat box. Prem, exactly opposite. N will become positive because electrons are leaving. Electrons are jumping over here. So P will become what? Negative. Crazy this is. Exactly. So in the next step, I'll just show the charges being formed. I'll just show the charges being formed. Look at this, huh? So there is basically P will become negative, right? So basically there is negative charge over here and there is positive charge over here. So where will the electric field be? From positive to negative. Electric field will be like this. This is the direction of electric field. So if there is now another electron which wants to make a jump into this hole, think which direction will the force on that electron be? If the electron wants to go here, electric field is here, the force on the electron, which direction will it be? Answer in the chat box quickly. Left side or right side? It's a negative charge. So force is opposite to the field. If it was a positive charge, it is in the direction of the field. Exactly, my dear students. There will be a force like this. This is the force on the electron. Oh, that's bad. Papa, this electron wants to jump over here. But you know, such evil kids are there. These kids jump, no? But they are saying, hey, I found my friend, but I am not going to allow you to come here. But that guy is like, Papa, listen man, there is a hole. This guy wants a friend. These electrons are like, we made a field. We have created a field of ourselves and we will not allow you to jump over us. Papa, so many electrons are waiting there. So many holes are waiting here. They want to jump, but this force will stop them. This becomes like a barrier. This becomes like a barrier over there. So there is a very nice barrier which is created. In fact, I can also say Because the field always goes from high voltage to low voltage. High voltage to low voltage. So this side is at higher voltage. This side is at lower voltage. If there is high voltage and low voltage, what is created? There is a potential difference. Potential difference, which is called as the potential barrier. There is a potential barrier which is created. Electric field creates potential barrier. Barrier because these kids are not allowing them to climb to the other side. There's a barrier. That is also called as a potential barrier or barrier potential, whatever you want to call it. This zone where the barrier is created, it's like no man's land. No man's land, it's like border. People going back and forth. Okay, anybody comes, shoot him. Anybody comes, shoot him. That's it. Nobody can come over here. So this is no man's land. That is why it is called depletion zone. No man's land. This is also basically your depletion. What is it called? Depletion zone. Understood, everyone? Very good. Now, because the electrons initially they jumped from here to here, where is the direction of the current, my dear students? Because the electrons are jumping from here to here, current will go like this. The current will go like this. This process of the electrons jumping from here to here, this process is basically called as diffusion. What is this called? Diffuse. The moment these electrons see, oh, there are holes, they'll go running like this. That is called diffusion. They diffuse. That is why this current is called as the diffusion current. What is it called? Diffusion current. Very good. Excellent. So you can see, don't worry so much about the diagram. This is just an animation to show you, like how the electrons basically jump from one side to the other side. So you can see N type has a lot of electrons. These electrons are slowly going to go to the other side, P side. From N side to P side, they are slowly moving. So the moment they go, they will satisfy the holes, but they will create a barrier. They will create like a barrier. Electric field will create like a barrier which will prevent the further flow of electrons. That's what happens. Okay. So the diffusion current is created when the electrons diffuse from the N side to P side. N side becomes positive, P side becomes negative. The diffusion current is from P side to the N side. Very, very important. Okay, keep this in mind. The diffusion current, because the electrons go from N to P, current is the flow of positive charges. So it will be towards N side, from P towards N. Okay, everybody should be knowing this. So difference in the concentration diffuses. So you can see the motion of charges gives rise to diffusion current across the junction from P side, from P to N. Keep this in mind. Very nice. Okay, now there is another problem which is going to happen, and that is called as drift current. Okay, so I'll tell you what exactly happens over here. So this is our junction. This is our junction. Okay, this side was P side, this side was N side. We saw that on the P side there was negative charges which was created because the electrons jumped, and over here from the N side there was holes, or I can say positive or vacancies created, we can say, because the electrons have left. Now we also saw that there was electric field like this. This was your electric field. In this depletion zone, okay, in this depletion zone, there will be some kind of fighting. There are many aunties here also, okay. This is at microscopic level. There are many germanium atoms, silicon atoms over here also. There will be fighting which is going to happen here also. So some point of time, due to the thermal energies, because of the collisions, because of the twists, bonds will be broken. The moment a bond is broken, what will you see? You will probably see a free electron, and probably you might see a hole. So this electron hole pair will be formed. What is this? Looks like a traffic signal. What is this? This is electron hole pair which is formed. Where is it formed? In the depletion zone. Everybody fine till this point? The moment this is formed, everything goes haywire. Where will the force be applied by the electric field? This electron will be obviously pushed here. So the force on the electron will be this side, but the force on the hole, because it is like a positive charge, it will be this side. So guys, think and tell me, if electron is going here, hole is going here, which side is the current flowing? Negative charge is going there, positive charge is going here. Which side is the current flowing? Obviously this side, because of the positive charge it will go here. Negative charge going there, current is going here. Perfect. So there will be a current which will flow from there to here. This phenomena is called as drifting. This is called as drifting, and this is called as the drift current. What is it called? Drift current. Exactly. Now, is the direction of drift current same as the direction of the diffusion current? Let's have a look. Where was our diffusion current? Diffusion current was this side, from P to N, but drift current, look at this. Drift current is exactly opposite. Diffusion is this way, drift is that way. Both are opposite each other. What will they do? Okay, I know there is some text over here. I'll shift this diagram later on, or maybe if I can shift it now. What will they do, guys? Okay, meanwhile answer it in the chat box. What will they do? Oh, I can't shift it now. Okay, okay. I'll shift it later on. Okay. So KP Bharat, what happened is basically, observe this. See, electrons will be formed even inside this depletion zone, electron holes. That process is there every time. It will be done here also, here also, here also. The moment electron and holes are formed, what will happen? Because there is an electric field, that electric field will apply force. So it will force the electrons there, force the holes here. So because of which the current will be towards this side. Because electrons are going there, current is this side. This phenomena where the electron holes are formed inside the depletion zone, that is called drifting. That's why this current is called as the drift current. So the net current will be zero. They'll cancel each other. Correct. So you will see, usually in a PN junction, N type, you will see the electrons jumping from the P type. But in this depletion zone, these electrons will be jumping back from here to here. From N side, they will be jumping over here to the P side. Simultaneously, an equilibrium from the P side, or there will be some electrons where the pairs are formed. You will see that they will be jumping towards this side. So an equilibrium is achieved. So the net current will be zero. Understood? Exactly. This is called as unbiased. Very crucial, guys. So in an unbiased, do you know the meaning of unbiased? Unbiased. Like some teachers are there, they are biased. That kid, no, he always says good morning to me in the corridor. I'm going to give him +1 mark in the composition. That kid, very naughty, always keeps smiling. He doesn't deserve so many marks. -1, I'll not give 5 marks, I'll give 4 marks. That is called bias. You're partial. Unbiased means, it's okay, whatever he does, he has written so much, I'm going to give him that much marks. That's all. Okay. So in an unbiased, why is this unbiased? Because you have not done any partiality. You have just left P type and N type to be as it is. You have not said, hey, no, electrons, listen, you go there. Hey, listen, you come here. You have not done anything. You have just left them to themselves. So that's why it's unbiased. So in an unbiased PN junction, you will see that the diffusion current will be equal to the drift current, and because of that, they will cancel each other, and because of that, the net current is going to be zero. Very crucial stuff. Very nice. Don't worry, I will move this later on, okay, on the next slide or something. Don't worry about it, okay? You will get that clearly. Let's see, which current does not depend on minority charge carriers? Most are biased. Okay, thank you for letting me know. Even I felt the same when I was a kid, no? I was on the worst part of biased. Yes, definitely Gogsdar. Definitely, definitely. If I follow, can I completely do full revision? So Goxler, I won't be able to do full syllabus before 24th, but I'll be doing all the important topics. Okay? Okay. No, I said I was a victim. Like when I was a student, that time teachers were biased towards me. Not on the better side, for the bad things, because I used to be very mischievous. I used to always get called. My parents were always like, see, your kid was laughing. See, he was not attending the class. See, he was throwing, he was hitting somebody. All these things. Okay, anyways. The correct answer is drift. Which current does depend on the minority charge carriers. That is drift. Yes. Which current does depend on the minority charge carriers, because that is on the very few number of charges which are created inside the depletion zone. Depletion zone. See, in this depletion zone, bichara, these are small number of charges which are created, not like diffusion, which happens because of the majority charge carriers. Now let's talk about biasing. Bias means everybody knows. You are creating partiality. Now you tell, hey, listen, P-type, I will give you higher potential. Hey, listen, N-type, I'll give you lower potential. Biased. Or reverse. P-type, listen, I'll give you lower potential. N-type, I'll give you higher potential. How do you create potential difference? By connecting a battery. This is the bias. You connect one terminal of the battery to one side, other terminal of the battery to the other side. That is creating a bias. Okay, Bharani, like I have put up on the pinned message also, this is going to take quite some time. It's a very long chapter, so stay tuned with me. Because of the bias, you will see what will happen is that depending on how you connect it, current will be either higher or it will be lower. Now you guys only think and tell me that if the higher potential or positive plate of the battery is connected to the P-type, negative terminal is connected to the N-type, what will the battery do? Battery will be like negative, repel. See, it's pushing. Push those electrons, tuck, karke. It is forcing. Hey, you go man, go, karke. This positive, what is this positive doing? Think about it. This positive will pull the electrons. Now, did I not tell you, from N side to P side, the electrons jump. Now, those electrons which jump here, what will happen? They will get pulled by the P-type, or sorry, the positive terminal of the battery. Yes or no? From N-type, when the electrons jump over here, the electrons will get pulled by the positive plate of the battery. And similarly, when these electrons jump here, there is some vacancy created here. That vacancy is being fueled by the negative plate. The negative plate will give the negative charges. So that's a good thing. That is helping the current. But there is a problem in that. See, just because you connected positive negative does not mean the electrons will be happy to go here. Remember, there is a barrier created here. Remember, those kids were there. They're like, no, you cannot cross this depletion zone. So you need to increase the voltage a little bit. Then also this barrier will be strong. It will become weak. It's like a fortress. It's like a wall of people. They're like, no, we are not going to allow you. We are not going to allow you to cross over us. Then when you apply little bit more voltage, the barrier voltage is broken. The barrier potential difference is broken. The barrier is gone. The depletion zone completely vanishes. That's it. Poof. You will see all these electrons can freely flow. There is no barrier. There is no border. Can freely flow. So sudden shoot up of the current. So the bias should be such that it is able to overcome the barrier voltage. Then you will see the conduction increasing significantly. That's forward bias for you. So when the biasing voltage is increased, the barrier voltage decreases and the width of the junction, or basically the depletion zone, also decreases. And finally, they overcome and cross over to the other side. So something like this, when you apply forward bias, I think the animation will show you. The electrons were going here, they are filling the holes from N side to P side. Now they can easily go to the other side. Tuck. The voltage difference has been reduced. You have we have made sure that there is negligible barrier over here and it is easily able to fall over to the other side. That's what it does. Now in reverse bias, exactly opposite, guys. See what is happening. You are connecting the negative plate to the positive, p-type, the positive terminal to the n-type. It's like saying, if the electrons which have jumped from n-type to p-type, do you see these electrons have jumped from n to p? Okay, these electrons are not pulled by the positive plate. In fact, they are repelled. There is a negative terminal here. This is saying, hey, you stay there. Stay there. Keep quiet. Don't come here. And there is a positive charge here because from n to p there were electrons jumping. This positive is being pulled by this positive. Sorry, not pulled, pushed. You're like, listen, you don't come here. In fact, I'm going to push you. You stay there. You don't come here. So this negative plate is pushing these electrons here. This positive terminal of the battery is saying, listen, you stay here. No current. Hardly some current will flow over here. Hardly some current will flow. In fact, you are adding to more troubles. You are saying, okay, let the negative charges accumulate here. You are increasing the fortress. You are increasing the depletion zone. The positive charges will go over here. It will add to the width of the depletion layer. The depletion layer actually increases in size. So in the reverse bias, you see hardly any current will flow. Hardly any current will flow. Very few negative charges will jump over here and they will go like this. They will hardly, because this negative is repelling, is forcing these electrons to jump over here. It's forcing these electrons to jump over here and go like this. Because the electrons go like this clockwise, current will go that way. It's a very, very small amount of current. So finally to conclude, in the forward bias, the net current which is there is because of the diffusion minus the drift, but this drift is negligible, is generally negligible. Okay, so diffusion current is higher than the drift current. So you can see the diffusion, I diffuse, will be higher than the drift current. So that's why you will get the net current in that direction. I know electrons are going like this, but flow of current will be, conventional current will be like that. Okay. But in the reverse bias, you are going to see that the drift current will be like this. The diffusion current will be small. The diffusion current will be small. So the net current will be the drift current, which is higher, minus the diffusion current, but usually the drift current only is so small. If you subtract the diffusion also, that's it. This is negligible totally. Negligible in total. The net current itself is very, very small. Okay? Everybody with me on this? Everybody has understood till here? Everybody with me? Great. So how does the graph look like when you plot it for different voltages for different currents? This is the graph. Observe carefully. Forget this part. First look at this part. This is forward voltage. This is the current. You can see as you increase the voltage, there is hardly any current, forward bias. But suddenly there is a shoot up. Why there is a shoot up? By the way, that is also called as knee voltage. That is also called as the knee voltage. Why is there a shoot up? Because here you are overcoming the barrier voltage. You are overcoming the resistance, and then once that barrier is destroyed, that depletion zone is destroyed, free flow of electrons will happen. Electrons will flow freely. So that is what knee voltage is. After that, the current shoots up. Also, do you see voltage is not proportional to current? Voltage not proportional to the current. Do you see that? So therefore, is the resistance constant? Definitely not. No, voltage is not proportional to the current. It is definitely not going to be following Ohm's law, nor is the resistance constant. If you want to find the resistance at any point, just find the current also find the voltage at that point. So the value of the resistance will be nothing but, because V is equal to IR, R will be nothing but voltage by I, which will not be a constant at any given point. It will be a non-ohmic device. If you go the reverse way, observe what is happening. Observe what is happening. Very, very small current is there. That's why it is called leakage. Why is it called leakage? Because this current in the reverse bias is very teeny meeny because of the drift current. So that is why it is called as the leakage current. It is hardly noticeable. This is crazy. If you connect the PN junction in forward bias, it gives good current. If you connect the PN junction in reverse bias, hardly any current is there until you give so much voltage that it breaks down. It's like, okay, just, it's okay, man. Let's just flow. So there is a sudden surge in the current, but that is after breakdown. That happens after a long time. After a lot of voltage, it breaks down. It finally is like give up. Okay, please don't think that, sir, this point and this point are identical. No, it's not symmetric. This is not a symmetric graph. This knee voltage is 0.3 volts, 0.4 volts, 0.5 volts. This breakdown voltage can be 10 volts, 5 volts, 20 volts, like that. So be careful about it. Okay. So my dear students, the reverse voltage current is very, very small. It's called as a leakage current. The breakdown happens after a large amount of reverse voltage, and you will see that the resistance in either of the cases is not going to be constant. That's why this graph, by the way, is also called as the voltage current characteristic graph. You tell me the voltage, I'll tell you the current. You tell me the voltage, I'll tell you the current. That's how this graph tells me how things are going to be affected by the voltage. You can also see only in the forward bias, the current flows significantly. In the reverse bias, hardly any current flows. It's like a valve, I feel. It's like a valve, I feel. Have you seen walls? Do you know where are the walls in your day-to-day life? Have you seen walls? V-A-L-V-E. Walls. Yes, no, come on, put it up in the chat box. Do you know where are the walls used? Tap, okay, great. What if I tell you it's there in your human body only? In digestive system, yes. In your arteries, near the heart, is it there? Is there some kind of a wall? Is there some kind of a wall? Yes, to prevent black flow. Very nice, arteries and veins, perfect, perfect. Look at you guys, biology students, you will definitely know it. So what is the function of a wall? It allows the flow in one direction, prevents the flow in the other direction. Are you getting the same feeling looking at this particular graph? It allows the current in one direction. In the other direction, it's like leaking, hardly anything. Yes? No? So that device which allows the flow, not of blood or of food, but of current in one direction, is called as a diode. Diode is a device which allows the flow of current in one direction. In the other direction, it's like one way. Sorry, traffic police is there. No, 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 no entry. Go back, turn back. That is what a diode is. Now, how did you make this diode? Using what did you make this diode? If you forgot, let me remind you. What did you make this device which allows the current only to flow in one direction? Using P and N junction. So that is why it is called as a PN junction diode. What is it called? PN junction diode. Understood the nomenclature, where this name came from? Very nice. How does it look like? It looks like this. It's very small. It's probably the size of your fingertip. That's small it is. It's very, very small. Okay, this is a zoomed in image of a diode. Inside that there is a semiconductor P side, N side, and these are the two terminals of that diode. It allows the flow of current only in one direction. So this is the symbol. This is what is there inside of it. This is the actual photograph. The symbol of a diode is a triangle. Now the triangle points in the one direction. That is the direction in which the current is allowed. If the current goes this way, it will be opposed. So this is allowed This is like one way. This is not allowed. That is the meaning of the triangle. Cool? Everyone with me? Great. Let's see if you guys can solve this. The current voltage characteristics of a PN junction diode is shown. Approximate resistance of the PN junction. Oh, I forgot to tell you about dynamic resistance also. 1 second, guys. Let me just tell you over here. This resistance over here, usually which you find, that resistance is just called as the static resistance. This is just called as the static resistance. But there is one more thing which you should know. If this is voltage current graph, okay, and if you measure voltage and current at some point, and then at some other point you measure the voltage and current, let's say this is the difference of the voltage, let us say this is the difference of the current, then instead of V by I, if you measure delta V by delta I, that is called as the dynamic resistance. Dynamic resistance, very, very important. Usually when we calculate resistance, we usually calculate static resistance. This change in the voltage per change in the current, that is called dynamic because it's the change. This is static. At that voltage, this is the current, static. Change in the voltage, change in the current ratio, that's dynamic. Okay, very important. Great. Let's try to solve one question on this. The current voltage characteristic of a PN junction diode is as shown. This is voltage graph. This is current in milliamperes. The question is, what is the approximate dynamic resistance of the diode when in the forward bias as shown when 2 volts is applied? Yeah, it's like instantaneous and average. Yes, you can think of it like that. Okay, come on my dear students, what do you think about this question? Dynamic resistance. Dynamic resistance is basically delta V by delta I. Difference of the voltage, you can see it is 2.1 minus 2. Difference of the current is 800 minus 400. But careful, this is milliampere, so 10 to the power minus 3. So this is just going to be 0.1. This is going to be 400 into 10 to the power minus 3. So this is going to be 0.1. And you can see this will just become 0.4, correct? Because 2 zeros goes and one more decimal. So this is 1 by 4. That's it. 1 by 4 is nothing but 0.25 ohms. 0.25 ohms. Very nice. That's the correct answer. Very good. Excellent. Understood? These kind of simple problems also come. Let's move on now. Of the diodes shown in the following diagrams, which one is reverse bias? Come on, this is a tricky one, logical one. You will have fun solving this. Diode, voltage, voltage. Diode, ground. Ground means 0 volts, voltage. Ground means 0 volts and voltage. Voltage, voltage, diode. Look at the direction in which the diodes are connected. One of these diagrams is reverse bias. Figure that out, guys. Which is reverse bias? Which is reverse bias? Both B and D? No, not B, not D, it's C. Let's understand why. Some of you got it, perfect. Let's see. Hey guys, this is -5, this is -12. Okay, so if you mark the points, this is at -5, this is at -12, this is lower, right? This is basically higher, right? This is P, this is N. P, N, that's what the symbol is. In the diode, that base of the triangle is P, the pointing arrow mark is towards the N type, positive and negative, P, N. This is at higher, this is at lower. This is definitely forward bias. This is definitely going to allow the current to flow in this direction. Got it? Perfect. Similarly, look over here, this is 0 volts. This is, maybe some drop will be there, but approximately you can say -10 volts. -10 is obviously lower. This is lower. This 0 is obviously higher than any of the negative number. This is P, this is N. P to higher, N to lower. current will definitely flow over here. If you look at D, this is 5 volts, this is 5 volts, this is 10 volts, 10 volts, this is obviously higher, this is obviously lower, this is P type, this is N type, P to high, N to low, so obviously current can flow. But in this case, you will notice one interesting thing, this is 0 volts, this is 5 volts like thing, this is lower, this is higher, this is P type, this is N type. That's the problem. It will not allow the current to flow. P to high, N to low, then only current will flow. This is wrong. Very nice. Oh my God, we are now coming close to the applications. We are coming close to the applications, guys. Ready for checking out the applications? Now, the first application is this 3-terminal device, which we are going to see in a bit, that is called as a transistor. Another thing is logic gates. That's also what we are going to see now. Also, we are going to see different applications like photodiodes. You will also see, solar cells and all these things. You will see semiconductors are being used. We'll see all these things one by one. But this characteristic graph is so important. It's so important that you will see different applications based just on this graph. Just knowing the current and voltage, there are different things that you can apply. The first thing where did it go? Yes, is basically of a PN junction diode. So the first application, remember a diode symbol was normally a triangle with this as the P side, this as the N side. Look at this, P, this is N. So the first application is LED. You might have heard about LED mobile screens or LED TVs. What is this LED? It stands for light emitting diode. It emits light. You will be like, wow, sir, how does it look? It looks something like this. But in your TV, this is even smaller. Even smaller. There is a small PN junction. And we know what happens in a PN junction. The electrons jump from one side to the other side. Do you remember atomic structure, guys? What happens when electrons jump from one energy state to another energy state? From one energy state to another energy state? If they go from high energy to low energy, what happens? What comes out? Light. Yes, photons come out, right? Exactly, that's the same thing which is going to happen in a light emitting diode. So when the electrons go from one side to the other side, you will see they go from high energy to low energy. That creates the emission of photons. So high energy to low energy, the electron jumps. So that is going to, this is your electron. So that is going to create basically light. So you can also say E1 minus E2 is equal to HF, which is the energy of the photon. If you change the energy difference, you can change the frequency. If you change the frequency, you can change the wavelength, you can change the color. So this frequency decides the color of the LED. So if you are ever wondering how do you get blue color, white color, red color, yellow color LEDs, what they do is they change the energy difference, because of which the photon's frequency changes or the color changes. That's how a LED works. A LED is always used in forward bias or reverse bias. Come on guys, answer this question in the chat box. A LED will be used in forward or reverse. Let's see how many of you can get the answer quickly. Obviously LED should consume the electricity. It should allow the passage of current. Only then the electrons will flow from higher to lower energy. Obviously it is used in forward bias. What is it used in? Forward bias. Keep this in mind. Next thing is photodiode. Oh, by the way, I forgot to tell you the symbol of LED. The symbol of LED looks like this. You just put the triangle. Okay, this is your P side, this is your N side. Current will only go like this, forward bias, right? But you show two arrow marks coming out of it. What is those arrow marks? That is the light coming out of it. That's the symbol of a LED. The exact reverse is a photodiode. What it does is it takes in the light, senses it, and converts it into current, which you can later identify to find out how much light was falling onto it. Have you ever seen in nice hotels where you go to wash your hands, automatically the tap opens or the water falls from the tap? Have you seen those automatic washing machines wash basins, there you will have a photodiode. What happens is, basically there is a light over there, or there is a sensor of light, and when you put your hand in the path of that light, the light does not fall on the sensor, it obstructs, that triggers the electrical circuit, and that's when it opens, that mechanism opens up the valve, and the tap is open and the water comes out. So there they use photodiode. You might have also seen these days in the cars, there is suddenly these lights which turn on, they are also called as automatic headlamps. As soon as you are driving, suddenly there is a tunnel. You go inside a tunnel, you don't have to turn on the light. Automatically the lights have turned on. Have you seen that? Yeah, even in sanitizers. So that is one of the beautiful applications of photodiode. It senses light falling onto it. So in fact, the symbol for such a photodiode is exact opposite of a LED. You will see the arrow marks going this way. But there is a catch in photodiode. Photodiode is always used in the reverse bias. And I'll be like, what the hell? Why do you use photodiode in reverse bias? The reason for using photodiode in the reverse bias is from the graph, the current versus voltage graph. Like I was telling you, this graph gives you a lot of things where you can apply for different applications. See guys, what happens is, when light falls on a basically photodiode, okay, on a photodiode, there is sudden increase in that current, or basically the conductivity changes. Now here, what happens in the forward bias is that you will see that the current changes. The current changes are, from this value to that value. It reaches maximum very soon. But in the reverse bias, you have a lot of smaller values of current, and it becomes more sensitive to small changes in the light. Here, just imagine if more light falls. Just imagine more light falls. This graph will probably become like this. More light falls, this graph will become like this. More light falls, this graph will become like this. Hardly any changes. But in reverse bias, you put more light. Already there is hardly any current flowing through it. You put more light, you will see the graph will go like this. You apply more light, the graph will go like this. You apply more light, the graph will go like this. So what does it tell you? It tells you that the sensitivity of current is higher in reverse bias than in forward bias. So if you want to measure the current dependence on the light's intensity, better measure it in the reverse bias, because you can see how intense the light is. Here you will be like, oh my god, is it on this line or this line? I don't know. Here okay, it's on this line or this line, because they are clearly different from each other. Is that clear? Everybody with me on this? Yeah, even the brightness sensor, GV, very good, very good. So this diode is basically used in reverse bias. That's only because of the sensitivity of the diode's current towards the light falling on it. Very, very crucial. Cool? So it changes very easily. If the changes are small, then you cannot see it easily. But when the changes are large, then you can find it out very easily. That's the whole logic behind it. The next type of diode. Yes, they give us electrical energy. No, Prem. It's not the same as solar cell. Solar cell is completely different. Solar cell gives you electrical energy. That is completely different. Don't confuse photodiode with the solar cell. Okay, that is different. Okay, here when I say it is connected in reverse bias, that means you are connecting a positive terminal here and negative terminal here. That is the meaning of that. In solar cell, there is no battery connected. It is the battery. Understand that. There is no biasing in solar cell. Do you understand the difference? So photodiode does not give you electrical energy. Photodiode is connected to something. Okay. Next is Zener diode. Okay, next is Zener diode. All right. What is Zener diode? Zener diode makes use of the reverse bias voltages, like I'll show you over here. It in fact uses this region of the reverse bias voltage, where you will see that after the breakdown is achieved, no matter what you do, the voltage does not change. It has become constant. The voltage has become constant. That is the use of Zener diode. You'll be like, sir, okay, fine, I understand the voltage does not increase, but how does it benefit us? I will show that to you. By the way, the symbol of a Zener diode is you basically twist that line like this and like this. That is basically Zener diode. Without them, that is just a normal diode. You bring it down and bring it up. That is called as a Zener diode. Again, it looks very small. You can hardly make out the difference between a Zener diode and a normal diode. It's very small, looks identical only. Okay, now what is going to happen in a Zener diode is it works in the reverse bias, specifically in the breakdown voltage. And if I show a Zener diode maybe like this, because I'm connecting it in reverse bias, and we know this is P side, this is your N side, I will connect this to the positive terminal, this to the negative terminal. This to the positive terminal, this to the negative terminal. Correct? Imagine I tell you the breakdown voltage is example 5 volts. Breakdown voltage is 5 volts. Example. That means after 5 volts in the reverse direction, that's it. It breaks down. It suddenly conducts. The voltage remains constant. You cannot increase the voltage beyond a point. So that is a good thing for me. I'll tell you why. Because I can use it like a voltage regulator. How? Observe. Just imagine this. Just imagine this. If I give 6 volts here, okay, 6 volts here as compared to this, I know the breakdown voltage is 5 volts. No matter what you do, across this diode, only 5 volts can be dropped. So you will see only 5 volts will come up on this diode, and the remaining part of the circuit, maybe there is a resistance here, you will see 1 volt being applied over here. Out of the 6, 5 comes here, 1 comes here. If by chance you make that 7 volts, this will still remain 5, 2 volts will come over here. If you make that, let's say for example 20 volts, you will see out of the 20, 15 volts will come on the other parts of the circuit, only 5 volts will come over here. What it means is, if I take out 2 terminals from here, the voltage across this will always be 5 volts. Isn't this like a regulator? It is telling only 5 volts can come out, nothing more, nothing less. So this is acting like a regulator. It is acting like a regulator, guys. So irrespective of the voltages, if voltage is more than that breakdown voltage, you will see that across this I am just going to get the breakdown voltage, which is just going to be constant. So hence it is used for regulating the voltage. Yes, a fixed voltage. So it is called as a voltage regulator. Keep this in mind. Okay, great. Okay, I'll just remove that diagram later on. Don't worry about it. There is another use of diodes. Okay, and that is rectifier. So a lot of new names and new terminologies you are learning, okay guys, today. So you learned about Zener diode, you learned about photodiode, you learned about LED, which is light emitting diode. Another thing is rectifier. Yes, Nick, you can definitely watch my lectures. NT-Abhyas, MTG, PYQ is more than enough to score 150 plus. Yes, definitely. Now, what is a rectifier? You all have used a charger, no? Definitely. You would have seen a charger like this. Okay, I don't have a charger now. Oh yeah, I have. Yeah, but I've seen a charger like this, correct? Great. So, on one side, you have AC where you put it in the plug point, but your mobile, your laptop, or whatever device you're using, that is on DC. AC is there, DC is there. AC is alternating current. Sometimes this way, alternating current. DC, direct current. Current only flows in one direction. How do you convert a current which is going in both ways to one way? Two-way to one-way. So that device which converts two-way to one-way is called as rectifier. Exactly. So what is a rectifier? Rectifier is nothing but a device which converts AC into DC. That's all. Now there are multiple types of rectifiers. Let's understand two major types. First one is called half wave. The second one is called full wave. What is the meaning of half wave and full wave? It's exactly what you can imagine only. In an AC signal, you have the positive cycle, you have the negative cycle. You have the positive cycle, you have the negative cycle. That means current flows this way, current flows that way. Current flows this way, current flows that way. In half wave, you only rectify, meaning convert AC into DC, only half of the wave. The remaining half, you just shoot away. It's like saying cars are coming from this side, cars are coming from that side. You make both the cars go in that road, that is full wave. You say no, only the cars coming from this way can go that way, that is half wave. Remaining half of the cars, you're like, show off, get lost, I don't care. So that is half wave. So in half wave, you can see if AC signal has positive cycle, negative cycle, positive cycle, negative cycle, you will see the output will only have the positive cycles, the negative cycles will just go away. But in full way, I'll explain you the working, don't worry about it. But in case of full wave rectifier, you will see the positive cycle, negative cycle, positive cycle, negative cycle, the entire thing is converted into unidirectional current or DC current. So traffic was going this way also, that way also, this way also, that way also. You now made it only this way. Only one way it can go, it cannot go the other way. So you have converted the entire wave into a DC signal. That's why it's called full wave rectifier. Is that okay, my dear students? Now how does it work? Great, great. Thank you, Moonlight, so much. See this. This is a transformer. Okay, don't worry about it. Transformer is just going to step down the voltage. That's all. Forget this. There is only one diode needed. That's all. In the positive cycle, what is going to happen? In the positive cycle, this diode is going to be forward bias because this is your positive cycle. So this is P type, this is N type. P is connected to positive, N is connected to the lower voltage. It's forward bias, it will allow current. So if whatever current is flowing here will flow through the diode, and if you have some resistance, obviously I into R will give you the voltage across it. So definitely there will be some voltage which is created because of the current flowing through it. There is some current flowing through it. It is allowed in forward bias. But the moment you go to the negative cycle, that means now the current is flowing the other way. This is positive, this is negative. You can see in this diode, this is P, this is N. P is connected to minus, N is connected to plus. This is obviously reverse bias. Reverse bias. Obviously no current will flow. There is no current, no voltage. So only when current is flowing this way, it will allow the output. When current is flowing the opposite way, it will just shoo it away. That's how it gets rectified. You can see that this is unidirectional current. I know it is not your favorite constant current. That's okay, but at least it is flowing only in one direction. That's why it is half wave rectification. I've explained the working through this diagram also, which will be available to you in the slides. Okay, you can see the complete AC signal, only half of the signal is coming out. Half of the signal is coming out. rest half is just shooed away. Okay, observe this. Okay, input also DC, no, input will be AC bacha. Look at this, this is AC, this is nothing but AC, this is nothing but AC signal, this is nothing but DC signal. This is AC, this is DC, because it is only flowing in one direction. All right. Now there is another type of rectifier, like I was telling you, full wave rectifier. Usually for these kind of rectifiers, you need 3 terminal transformers. They are called as the center tap transformer. Center tap transformer. So in these transformers, basically there are 3 terminals. Usually there are 2 wires coming, but here you take out 1 more wire from the between. So because of that, what happens, you can get a full wave rectification. How? I'll tell you. You need 2 diodes also. So you need 2 diodes, one diode this way, another diode this way. So it's basically saying cars are coming from here also, cars are coming from here also. There is one traffic police to tell, okay, you guys are coming from here, okay, go carefully there. Another diode, another traffic police asking these cars coming from the other way, okay, listen, you turn like this and go there. So both the cars will eventually go in the same direction. That's the job of the 2 diodes here. So observe what is happening, my dear students, again. Okay, so when you are in the positive half cycle, this is relatively positive, okay, as compared to this side. This is positive, this is, let's say, 0, this is negative. This is relative scale. If this is minus 5 volts, this is 0, this is plus 5 volts. So this diode becomes forward bias, because this is P side, this is N side. P is connected to positive. This diode will become reverse bias, because the P is connected to negative. So this will not conduct, this will conduct. So the current will flow from here to here to here to here. So do you see through this resistor, current is going from right side to left side? Current is going from right side to left side. Okay, so that current will definitely come out over here. Everyone, cool? Next, when you talk about the negative half cycle, then what happens? This becomes minus, this is 0 only, this becomes plus. Plus is connected to P, so now this becomes forward bias, and negative is connected to P, so this becomes reverse bias. This becomes reverse bias. So now this will not allow current, this will allow current. So the current will flow from here, because this is forward bias. It will go like this, it will go like this, it will go like this, it will come out like this. Do you see whether positive cycle or negative cycle, through this guy, the current is only flowing in the same direction? Not like this and then like this and like this. No, it's always flowing in the same direction. So that's why you see the current flows in the same direction. Yeah, it increases and decreases, that's fine, but it always goes in the same direction. That's why it's called as full wave rectification. Okay, everybody with me? AC to DC, it's like modulus function. You're taking this guy on the top, you just bend it on the top, that's all. Cool, shall we do some questions? Shall we do some questions? Here comes a question. Okay, a Zener diode having a breakdown voltage, this is a Zener diode, breakdown voltage 15 volts, connected to 20 volts across 250 ohms and 1 kilo ohm. Question is, what is the voltage across 250 ohms? Come on, let's see how many of you can do this. Very direct question. I want everybody spamming the answer in the chat box. Everybody spamming the answer in the chat box. Come on, my dear students. Figure this out quickly. B, sure? D? The answer is D, guys. I'll tell you why. Okay. See this. See this. This is a Zener diode, and a Zener diode operates in reverse bias, and the voltage is basically constant. It is 15 volts. That is basically your breakdown. No matter what you do, this is always going to be constant, even if this is 20. So if this voltage is 15 volts, the total voltage the total voltage is 20 volts, which is the sum of voltage across 250, there is some drop here, plus voltage across the Zener diode, across Zener it is 15, across 250 ohms, how much will it be? Obviously 5 volts, right? So that is why the answer is 5 volts. Everybody got it? So the total voltage was 20, 5 here, 15 here, 5 plus 15, 20. That's all. Great. Now I am thinking of one thing. Okay, instead of overloading you, I will take a separate class on transistor, or maybe I'll just try to make a very conceptual short video for transistors, which you can understand maybe in 15 minutes or something. Okay? Instead, what we'll do is we'll do logic gates, because logic gates you will enjoy also, and you will learn it through live session easily rather than transistor. What say, guys? Let's do that. Okay, so probably let me just go to logic gates quickly. Just 1 second. Don't worry. Okay, I'll go to logic gates now. Okay, so let's understand logic gates, because you're going to enjoy this to the core, and guarantee I've seen many times they ask questions from semiconductors from logic gates. Even last year, if you see, there was a question in logic gates. So 4 marks are there in your pocket. Now, have you used the regulator of your fan to try to increase the speed of the fan? You turn it like this, like this. The speed of the fan increases or decreases. What is it changing? Basically, it's changing the current or the voltage, right? Of the fan, correct? It's changing the voltage or the current of the fan, right? Very good. Sometimes you might have seen some fancy hotels or some fancy systems. They have something like a touch to button. Yeah? You press that button, tuck, tink, tink, some noise will come and it shows some digits, 25, 50, or you can change the temperature like that on, like in your AC remote, like the one I have here, right? You can change. You press this button, you see some values over there and something happens, the speed changes. You can increase it in steps. So that's exactly what is the difference between analog and digital signal. In analog, you can get any value of voltage or current that you want. You can just turn it around. You can just, just like pressing the accelerator of your car or your bike, you can accelerate it how much ever you want. But if I tell you, no, listen, I'm going to give you switches over there, or I'm going to keep some buttons or some kind of, buttons like this. You press this, your speed will go to 5 kilometers. Then you press this again, 10. You press it again, 20. You will not be so happy about it, 100%. Like, what is this, sir? I can only go 5, 10, 15, 20. I don't like this. But that is digital signal. Okay, that's a very crude way of explaining what is digital signals. Okay, so they are just like this or that or this or that. But in analog, you can get whatever values that you want. Yep. Now, you will be like, sir, so digital is bad. But that's the beauty of digital signal. Digital signal is not going to be affected by some external factors like noise or some loss of voltage or some external factors which change the current, drop in the voltage or drop in the current because of the resistance. Here, it is either high voltage or low voltage, more voltage or less voltage. You understand only this or that. There is nothing in between. There is nothing in between. That creates more clarity and it reduces the noise. Like if somebody tells you, will you come out for this party? That's a person says, yeah, listen, I will do one thing. I will see if I can go there and then I will pick up that. I will drop that person and I will see if I can come like that. I don't know. Be like, are you coming or not coming? You just tell me that. So digital signal is like that. It's like a clarity. 0 or 1, true or false, yes or no, high or low, 5 volts or 0 volts. Analog, so many shades of gray. So many shades of gray. This is also possible, that is also, that this, so many values are possible. And our computers, our mobiles, our AC remotes, this remote which I use, it understands not analog, digital signals. 0, 1, 0, 1, 0, 1. And you might have heard or you might have seen in fancy movies, some programmer is programming, or in some animation, 0, 1, 0, 1, 0, 1, 0, 1, everywhere on the back of the screen. What are these 0, 1s? These are the only things that these stupid machines can understand. That's all. They don't understand anything else apart from yes or no. Yeah, even clocks, digital clocks, nothing else they understand. True or false, 1 or 0, all of them mean the same thing. High, low, on, off, yes, no, high, low, 0, 1, on, off, all are the same thing. Many circuits are digital. You will be like, sir, this is crazy. I mean, how can just 0, 1 decide so many things around us? But that's the beauty. It can. And the way you interpret these 0 and 1s can change the definition, can make you transmit so many messages, it can mean so many things, the pattern in which you send these 0s and 1s. And that's how everything around us works, be it computers, remotes, whatever. But to do that, you need a logic. If this is happening and this is happening, then turn this on. If that is happening, that is high, that is low, then do this. If this is off, this is on, then do that. There is logic inside your processors. You take anything like this or the remote, you will see a small circuit inside your phone, tablet, TV, whatever. Have you seen that? Yes or no? All of them have logical processors. There are processors, these have some logic in it. So they work only under certain conditions. When these conditions are met, then it will give this. When these conditions are met, then that will happen. Ifs and buts, ands and ors, no's and yeses, that's what is there inside these chips. It's a brilliant brain of all the devices around you. And it's not so simple to explain also that what is exactly the logic of this entire chip, sir. It's a combination of lots and lots of ifs and buts. But at the basic level, there are only 3 major operations which are happening. Or, and, not. Or, and, not. That's it. These 3 logical operators can build up the entire logical system of your chips. You'll be like, wow, that's great. That's cool. Or, and, not. Or, exactly the same word in English, and, just like you use it in English, not means no. What do they mean? I'll come to that, but before that, let me tell you the smallest building block of any chip or any logical circuit is called as a logic gate. It is called logic gate. What is it called? Logic gate. It will have some inputs, it will have some output, it will have some input. So that input will see, oh, this is high, this is low, so output should be low. Oh, this is true, that is true, then this should be false. Okay, this is 0, oh, this should be 1. So it's called as a logic gate. It's like a gate. This, that, then this. There is a condition to that. So first is a OR gate. So OR means if this is true or this is true, then the entire thing is true. I'll give you a best example of that. Okay, just come up over here. Yes. Imagine, oh, by the way, you need something called as the truth table for all these gates, which gives you a certain set of conditions. If this is there, then what should happen? If this is there, then what should happen? That is called as the truth table. So let me just show that to you. here you have the inputs, and here you have the output. This is called as my truth table. Truth table. Champa decides that she will marry Pandu. She will marry Pandu if Pandu is rich or intelligent. What did Champa decide? Put it up in the chat box so that everybody can read. Let's see if you are hearing properly. Champa decided she will marry Pandu if he is rich or intelligent. If he is rich or intelligent. Let's see what is the output. Let's see what's Champa's output going to be. Crazy, rich or intelligent. She finds Pandu is rich. Pandu is rich. Pandu is also intelligent. Very good. Champa will get married. Yes or no? Champa will get married. She sees Pandu is very rich, but he is not intelligent. Okay, he is rich now. Fine. True. True, false, true. Pandu is not rich, but Pandu is intelligent. Okay, no problem. Pandu is not rich, Pandu is not intelligent, she will not get married. That's what is the truth table. Understood? This is what a truth table looks like. You can also put 1, 1, 1, 0, 0, 1, 0, 0, or you can put true, 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 false, false, true, false, false. Whichever you want. Or high, low, on, off, whatever. All of them mean the same thing. This is the Kundali. This is basically what Champa is going to see. Rich, intelligent, whatever. Example. How do you show it in expression? You put a plus mathematically. This is your truth table. 0, 0 gives 0. Both are false, false. Either one of them is true, then it is true. Any one of them is true, it's true. Diagram wise, symbol wise, you put a D-shaped symbol, but you curve this, that is called as an OR gate. This is one of the input, this is another input, this is your output. You give 0 here, you will get 0 out. You give 0 here, 1 here, you will get 1 on the other side. The plus means OR. The plus over here is OR. So guys, 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is not 2, it is 1. Be careful. What is 1 plus 1? What is 1 plus 1? It is 1. Because here plus is not that plus. Plus means OR. Plus means OR. Okay? Yep. Very good. Very good. Excellent. Next is AND. Champa says, I will marry Pandu only if Pandu is rich and intelligent. My goodness. So let's see what the table is going to look like. Rich and intelligent. Let's see what the output is going to look like. She sees Pandu is rich and intelligent. She will get married. She sees Pandu is rich but not intelligent. Here the word used is and. Both he should be. Nope. Pandu is not rich. Pandu is intelligent. No use. Pandu is not rich nor intelligent. No use. Gone. Understood? Clear? This is the truth table for AND gate. And logical gate. Here the symbol used is dot. Very good, Anger Queen. Yes, these are like PNN. The symbol for that is a proper D. If you bend it, it becomes OR. If you keep it straight, it is AND. This is very easy to remember. AND has the D, na? The D looks like this. So AND gate. The symbol is dot. So just to give you mathematical expressions, 0.0 is 0. 0.0 is 0. 0.1 is 0. 1.0 is 0. 1.1 is 1. Exactly what the truth table tells me. Perfect. Next is NOT gate. Next is NOT gate. I mean, just imagine this. What will NOT gate be? It's like, you know, exactly whatever is there, opposite of that. Imagine, Champa says, let's say she sees if Pandu is rich. If Pandu is rich, okay, this is the output. She sees that if Pandu is rich, I will not marry. If Pandu is not rich, then I will marry. Exactly opposite. She's checking something, or you're checking something. If that is true, then the outcome is false. If that is false, the outcome is true. If this is off, that is on. This is on, this is off. Exactly opposite. That is called as a NOT gate. Exactly negation. The symbol for that is just a triangle with this dot. Yeah, it looks like a diode. It looks like a diode, but it is not a diode. There is a dot over here. Okay, please understand, in a diode you have that bar. There is no dot. Okay, so don't get confused between a diode and this. Okay, great. So this NOT gate exactly negates. The symbol for that is a bar. You put a bar over on the top. You can see the truth table, 0 gives 1, 1 gives 0. So if I say 0 bar, it will be 1. If I put 1 bar, it will be 0. If I put 0 bar bar, what is the answer? 0 bar bar. What does the dot mean? Dot means it's not like multiplication. You can think of it like AND, like I showed you over here. The dot means AND. Symbolically, AND means that dot. Okay. Plus means OR. So what does the bar mean? Not. 0 bar bar means 0 bar is 1, 1 bar is, so this will just become 1 bar, which is again becoming 0. 1 bar bar bar, 1 bar bar bar, 1 bar bar bar. Is it not like 1 bar? Is it not going to be 0? Very good. Excellent. Got it. Perfecto. Now, there is something more what you should know, that is called as NAND and NOR. NAND and NOR are also additional gates. You can use these NAND and NOR gates and make any other gates. In fact, they are also called as universal gates. Let me tell you what NAND is. NAND is NOT and with NOT is NAND. So NAND gate is nothing but you take a AND gate and put a NOT gate in front of it. So it is AND with a NOT. That's why you see a dot over here. Do you see that? There is a dot. That dot was not there in case of a simple AND gate. That is not there. That is a simple AND gate. But when you put a dot, the moment you put a dot, it is a NOT gate. Basically, what is it? NAND gate. Okay. Now, what is a NAND gate going to do? If you are expecting 1, you will get 0. If you are expecting 0, you will get 1. Look at this. 0 and 0, 0, right? But the output will be 1. Because it's a NAND gate. 0 and 1 should have been 0. 0 and 1 should have been 0. But the output you will get is 1 because it is negating it. 1 and 0, you should have got 0, but you are getting 1. 1 and 1, you should have got 1. You are getting 0. It's exactly negating it. So A dot B is AND A and B, the NOT of it. So that's why you put a bar. Dot signifies AND, you put a bar, it becomes a NOT. Got it, guys? Everybody understood this concept? How these gates are working? Similarly, can you tell me what is NOR gate? What plus what is NOR? Put it up in the chat box. What plus what is a NOR gate? Which logic plus which logic is a NOR gate? Obviously, it is going to be an OR gate plus a NOT gate. OR plus a NOT gate will give you a NOR gate. So this is actually A or B, the NOT of it. The NOT of the negation of A or B. Think 0 or 0, rich or intelligent. Okay, both are false, false. But what you will get is exactly opposite. False, true, true, but opposite. You will get false. True or false is false. Or you will get basically, true or false is true. So you will get opposite, which is false. True or true should be true, but what you will get is a false over here. Is that okay? That's how it works. Very good. OR and NOT. Awesome, guys. Now before going ahead, let me give you two important theorems which will help and save your life, and those are called as De Morgan's theorem. It is nothing but A dot B bar is equal to A bar plus B bar. Very simple. A dot B means A and B. So the knot of A and B is basically the knot of A or the knot of B. That is what it is. The other statement is A plus B bar is A bar dot B bar. Oh, sorry. My bad. I have to put it. Yeah, correct. Fine. It's fine. Yes. So A plus B whole bar is, separate them out, but put, instead of plus, you put the dot. That's it. So this is basically the knot of A or B is equal to the knot of A or the knot of B. This theorem will help you at times, depends, but I'm just giving it to you. Okay, these are called as the De Morgan's theorem. This is called as a basic algebra. Let's see if you guys can solve this. There are some signals. You can see it's 0, suddenly it becomes 1 or high. There is low, it's high, it's low, it's high. This is the output. These two are the inputs. This is the output. Looking at the inputs and the outputs, can you guess which gate it is? Which gate it is? Last two questions, guys, then we are completing the syllabus. More 2 minutes, 3 minutes. Come on, figure this out. This is 0. Observe carefully. This is low. This is low voltage. So 0 or off or false or no. This is also low voltage. Output is also low. Correct? Okay. This is 0. This is 1. This is 0. This is 1. This is 0. Low. The output is 0. This is high. This is high. This is high. Acha. 0 and 0, 0. 0 and 1, 0. 1 and 0, 0. 1 and 1, 1. Acha, this should be AND gate. This should be AND gate. Very good. Very good. Very good. That's the correct answer. Perfecto. Understood, guys? This is like an AND gate. Why is it an AND gate? You can put up the truth table. 0, 0 gives 0. 0, 0, sorry. 0 and 1. 0 and 1 gives you 0. 1 and 0 gives you 0. 1 and 1 gives you, 1 and 1 gives you 1. So this is the truth table for obviously AND gate. Is that clear? Perfect. Moving on to the next question. There is some logical circuit written over here. Can you figure out what will be the best way to represent this logical circuit? Best way to represent this logical circuit in the algebraic mathematical form? Go step by step. Name each of the gates, you will get it, guys. This is basically AND gate. This is basically NOT gate. This is basically OR gate. This is basically NOT gate. 3 inputs are there, huh? 3 inputs are there. Look at this. This is B. So what will this point be? This will be B bar, right? This is B. This is negating B. So this is B bar. This is ANDing it. So at this point, what should you get? At this point, what should you get? B bar and this C. Because this C is coming as an input. So AND C, that means B bar dot C. Correct? Very good. The same input is going over here also. Next, this A is going as it is over here. This point is just nothing but exactly this B bar dot C. Sorry, not C bar, B bar dot C. Correct? Everybody sees that? So what will be the output of this? You have to OR this A or this thing B bar dot C. OR means plus. So A plus B bar dot C. That is what you are getting over here. What will the final output be? What will be the final output? Basically not of this. That means A plus B bar dot C not. That means you put a bar over all of them. All of them. Where is it? Where is it? Option D, right? Option D. Can you see that? Very nice. This is how you have to think. These are logical gets.